Good morning, good morning, good morning. Hello. Wow, it's a bit of an empty room down here. I assume we're all still downstairs eating instead of coming up after we yelled out 10 minutes. Come on, everyone. How's everybody here doing? Hey, you the good ones. I like you people. How you all doing? Yeah. Well, that is more excitement than I've ever had at this time in the morning. Have you guys been getting good on the coffee? What's going on here? Yeah, I mean, I'm the broken one today. You can hear my voice is a bit rough. So, yeah, at some point, Razvan might, in fact, take over for me. So don't be surprised if I suddenly look like, thinner, slim, more attractive and all that, All right. Yeah. So, really need these people up here for the housekeeping. Come on. Come on. Oh, I can see some people. Yeah, let's see how many people employed by the D Language Foundation are still downstairs. Let's run that one as a litmus test. So, hey, we've got a lot of out-of-towners. How was your flights in? Was it better than mine? No? Are you sure? Because my voice went really bad on the flight. How's your voice doing? Good? Yeah, okay, I think I heard that from here. Yeah, a lot of familiar faces, a few that I haven't seen before, probably many more downstairs that I've never seen before, but I wouldn't know, they're downstairs. Ooh. This is better, we got people now. All right. If you're downstairs, well, you're not welcome. So I'll just get, rolling with all the, yeah, I mean, look at this. We've got a new stage set up. Isn't this great? There's no chance of an Ali maneuver this year. I think we're going to miss out on some prime comedy here, unfortunately. So, congrats on the upgrade, but yeah. All right, so the housekeeping parts. You might remember the other year we had a bit of a problem with a notorious, nefarious laptop thief. Same security setup as last year. Guy on the door is going to stop you if you don't have your name tag on, and it is, you can see on your little, what do you call this thing, a lanyard? Yeah, it's printed with the D language thing. So if you're not wearing your name tag and you're not wearing the correct lanyard, dude's going to have a problem with you. So make sure you're wearing that at all times on your way in and out. What do we got? Fire exit. The fire exit is either there behind the AV desk or out the front door there. No, there's one around the corner, sorry. If there is a fire alarm, there are no scheduled fire tests today, so it will be the real deal, and we will meet behind the building in Finsbury Park. Okay, so what else have we got? Toilets, just back there if you need them. Disabled toilets are just over there through the fire exit door. There's also the disabled elevator down to the food. I don't think we have a problem with that. Everybody seems to have found the food just fine. Water dispensers, if you're thirsty, there's one up the back there, there's one out in the lobby. Catering downstairs, Wi-Fi if you need internet. I'm not going to read out the details for security reasons, but you can find dotted on the walls there, Wi-Fi login details. So go ahead and get yourself on the internet. And hey, look at the time. It's 9 a.m. That means, wow, who's the person we're all here for to begin with, right? Walter Bright. I'm glad I didn't have to say applause then. I like you guys a lot this year. All right, so Walter, take it away.
I think I need your mic. Oh, I already got one.
Yeah, you got that.
Okay. I'm going to talk about an Arch 64 code generator. I do not know why they call it Arch instead of ARM, but whatever. So who thinks this is a really dumb idea? So what the heck am I doing thinking about writing Arch 64 code generator? Well, I do agree it's a bad idea because, we already have two fine professional compilers working on the ARM. Why am I bothering to do this? But I'm going to do it anyway. I've implemented code generators for the x86 family, as you all know. And How many of us are on the spectrum? I definitely am. My whole family is. I was in the grocery store once, and one of the guy who was putting groceries in the bag asked very quietly to me, he says, "Are you on the spectrum?" And I said, "Oh yeah, my whole family is." So anyhow. DMD's code generator does have some advantages. For one thing, it's very fast. It turns out that DMD has kind of fallen into a niche of when you want to do rapid development of your algorithm and code, having a fast compiler is a big deal, and DMD fits the trick. The other thing is, you're not really a compiler writer if you haven't written a code generator. Now, there's been an explosion of languages since the optimizer and a code generator was kind of outsourced to free software, so anybody and everyone can write a language. And one thing that's not well known, it's not that hard to write a code generator. A lot of people think it's some deep, mysterious thing, but it's not. I've done crazy things before. Writing a C compiler into the D compiler was not a popular idea. People suggested I should focus on something useful. And it turned out that it had a lot of really neat consequences. One of the most interesting ones was and this was discovered, I swear, I did not think of it. It did not even occur to me, but I think it was Stephen who discovered that you could use it to convert C code to D code. Now, who would have thought that that was something that would just fall out of this? Do we have a question? Oh, you're just pointing? Okay. So it turned out to be very valuable, and import C turned out to be a very useful thing. So, sometimes I do things that other people think are crazy, and they work out okay anyway, but that's not a guarantee that this is going to work. Okay, I'm a nerd, I've already admitted that, and this is going to be fun, because I like writing code generators. It's just fun. And I want to do it by adapting the existing code generator. So I'm going to say that sort of a precursor to this talk is the one I gave last year about how the code generator works. So I don't want to repeat myself, so I'm going to be kind of assuming that you've all seen that. I want to reuse and recycle as much of the existing code generator as possible, which means looking through the various sections of it, there are parts I can recycle from the x86-64 code generator with almost no changes. Things like the register allocator, it turned out that that was very adaptable. The general layout and how it operated, how it dealt with common sub-expressions, the stack layout turned out to not be quite the same. Because of the way the instruction set works on the ARM, you kind of want to do it differently than on the x86. The intermediate code is the same, and the object file generation is the same, and the existing test suite. A lot of people underestimate how valuable a test suite is. Well, I've been running our test suite on the new Arch64 code generator, and it's finding an awful lot of bugs. So the test suite's doing its job and is an invaluable asset. I started on this knowing nothing at all about the ARM, except it was an outgrowth, or about the Arch64, except it was a 32-bit risky architecture. And no matter how many times I read through my slides, I still forgot to insert the picture that goes with this. Doesn't really matter. What I did was I bought a couple of books on, how to write assembly language for the ARM, and those books turned out to be useless because they didn't really explain anything about it. Things I don't need from the existing code generator is made an executive decision that 32 bits are the pass, so I'm not going to bother with that. Of course, I don't need XMM instructions. The more interesting thing here is the Arch64 instruction set. The only thing it does with memory is reads it or writes it. It never does a read-write on a memory location. So a large chunk of what's in the detail of the x86-64 can just be skipped. There's a lot of kludge instructions in the x86 that we can get rid of, like the wacky string instructions. There are several different methods of passing parameters to functions, and fortunately with Arch64 there's only one way to do it, so that simplifies things. On the x86, the floating point FPU cannot talk to the registers, so it would have a fake floating point register that can be used to transfer data between the floating point unit and the arithmetic unit. Don't need that anymore. And the last one is who doesn't know what the LEA instruction does? Okay, the LEA means load effective address, and the hardware has a heavily optimized microcode or whatever is going on inside the chip that makes it very fast. So certain kinds of arithmetic instructions can be executed very quickly with an LEA instruction rather than doing a separate multiply add. And so that optimization is actually used all over the place, and I can just snip that out because that kind of instruction doesn't exist. Some things we can't leave behind is complex numbers. That's going to cause me a bunch of trouble because the complex numbers seem to require a lot of implementation effort, and I'd rather everything was switched over to using the import of complex numbers. But that turns out to be impractical because of import C. So import C is kind of holding me back. I'm still going to have to implement complex numbers in the back end. Okay, godbolt.org is God's gift to compiler developers, and who never thought it was useful for compiler development? Turns out it's extremely useful because I didn't know how the instruction set works. So I would spend a lot of time writing one-line functions and run it through Godbolt and see what instructions dropped out the other end. And one thing I really like about Godbolt is not only does it give the mnemonics, it gives you the hex bit pattern. Now, why would I be interested in a hex bit pattern? The reason is the str mnemonic has a large number of implementations of it in hardware, all with different bit patterns. And so that was one thing wrong with the hobbyist books, is they would have these str instructions. By the way, str means store register contents to memory. And I couldn't tell which one it was, and it didn't give me the hex dump, so the books are useless. So anybody love fiddling around with 32-bit hex numbers? You take the small font on the screen and those hex numbers, and it makes my eyes bleed looking at those hex things. So I was desperate to find a better way to deal with this than deal with hex bit numbers. So the idea was, the first thing to create was a disassembler, which would read those awful hex numbers and would produce the mnemonics out of it. And this is all built into the compiler. If you compile with the -v switch, it will not present to you the generated instruction mnemonics. What it does is it takes the actual binary generated by the compiler and disassembles the binary. So that way, it's a wonderful way to check that it's generating the right hex numbers, and I know which instruction it is. So I did that part, and also put it into my object file disassembler. Now, there already is a disassembler as one of the usual tools that come with your dev system, but I wanted to write my own disassembler as a great way to understand the instruction set. Okay, so what I can do, now I have the tools, I can convert binary to assembler, because with the Godbolt thing, I'll take that hex value and just type it in, and it will, my program will give out the correct assembler for it. Binary, I can also go to that to the specification URL. It turns out the Arch64 specification is online, and spec URL, so binary. But the only thing I'm missing in all this is going from assembler mnemonics to binary, which needs an inline assembler, and I have not written that yet. And I believe Emmanuel is working on creating one. So, but I had to proceed. I thought many times I should stop and build that inline assembler because it will speed up the back-end development, but finally decided not to do that. It turns out that the Arch64 is not a simple instruction set in any way, shape, or form. You know, I programmed the PDP-11 back in the old days, and the entire instruction set fits on one 8.5 by 11 sheet of paper. The whole darn thing, including the floating point instructions. There are something like 2,000 instructions in the Arch64, and there's not much of a pattern to it. It all looks like, you know how evolution does not create anything in an organized fashion? It's just everything is a massive kludge that's adapted to do something else, like our hands and fingers are actually flippers that were readapted to be fingers. And that's what the Arch64 thing looks like to me. Fortunately, it's divided up into groups which have a specific bit pattern, and those bit patterns have variable parts, and those are the individual instructions. So you have a tree that's 2 layers. There's the group and then the instruction. And the end result is generating a 32-bit value. So here's an example of a group, the LDST_pause group. And those are the list of instructions it generates. And if you look at the bit pattern at the top, some of the bits are fixed and some are variable. And with the fixed bits, that sort of defines the group. And if you'll notice, none of those bits line up on hex boundaries, which makes it working with the hex numbers. You know, I can see Maria squinting at the screen. I know exactly what you're thinking. You're going, my eyes are bleeding. I'm looking at those bit patterns. And I would actually write it on graph paper, the bit patterns. I would take the hex and manually convert it to bits, and then I would hold it up to the screen and try to line it up with the... I mean, the whole thing sounds stupid, but it was agonizing. So I wrote functions that would match what the spec called it. So I wrote a function called the LDST pause, which has arguments which are all the variable parts of the instruction, and then it assembles the instruction out of the bits. Oops. And here's one of the stir fpsymd, which is a store immediate floating point value. And that sort of refines the bit patterns to a smaller subset, and still with some variable aspects to it. And this one, you know, the size of the operands, and an offset, and a source register and a destination register. And so we have another function, stir fpsymd, with those variable bits to it, which then it adds extra bits and calls LDST pause. So why did I do it this way? And that's because the names of the functions line up with the URLs in the spec. If they didn't, I guarantee you will be driven mad if they don't line up. So one feature of Godbolt that is missing is for each instruction, there should be a link to the spec page for that function. But Godbolt is missing that, so I wrote my own. In the disassembler, it will not only give you the opcodes, it will give you the URL to the spec page, which turns out to be extremely valuable and an enormous time saver. The disassembler just simply does that whole thing in reverse. You give it a bit pattern, and it checks the load store register group, which is the LDST pause, and then the specifics for each of the instructions are decoded from the field, and it then prints out a string. I don't know what that was. You don't need to read the code. That's not the point of the slide, just sort of what the purpose of this function is. Okay, so now we get to some of the dirty details. Registers. Everything in the x86-64 code generator fit in a 32-bit bit mask. So all the register allocation, all the tracking of register contents fit in 32 bits. And it actually worked out extremely efficiently. The register allocator works that way. The selection of registers for arguments on the stack works that way. Everything works that way, so I wanted to continue with that. And the problem I ran into was there are 3 register sets in the ARCH64. The first 32 are the general purpose registers. The second 32 are the floating point registers, and the third 32 are the 128-bit registers. And the floating point and general purpose register masks are disjoint. There's no overlap. So I was looking at, my first step was I had to increase the register mask to be 64 bits. And that actually enabled me to use more registers that were now available in the x86-64 code generator. And there are a few special values in there, like there's the FPU top of the stack, PSW is the status word, no reg means not a register. Underneath that is a list of the ARCH64 general purpose registers and what they do. And this is, came right out of the spec. And then the floating point registers. The important thing that here is the V8 to V15 floating point registers are callee saved registers. Oh, the AI image generation is fun. Draw me a picture of floating point, and that's what I got. Okay, the types are 6 that I'm going to support. Well, not quite yet. You have the 16, 32, 64, 128. And that's the half float type. Sorry about that, I had to do that. Every time I see half float, I think, hobbits. 16-bit floats are not supported by D, but they are well supported by other ARCH64 compilers, so we're going to have to modify D to support 16-bit floating point types. Fortunately, it falls out of the instruction set. So as I go, I just, have the backend supported even though there's no support elsewhere in the compiler. Then there's the Q factor. Remember I said the 128-bit floating point registers. Well, they actually do overlap with the general purpose floating point registers. So now I'm stuck because the when for the calling convention, only the floating point, the bottom 64 bits of it are saved, and the top is not. So that means that every time you call a function, your queue registers are going to have the top half of it trashed. And so how do I deal with that when my register mask cannot distinguish between the regular size floating point registers and the long ones? And I thought, I'm in deep trouble with this. And then I kind of had an epiphany, as the only problem is the floating point registers that are supposed to be saved when you do a function call. And I go, what if I just simply do not use those registers for the queue registers? And yes, I give up 8 registers, but the whole thing works. And it's not like I haven't done this before, because not all the registers on the x86-64 are available because they don't fit in the register mask either. So I think this is a reasonable compromise. Also, it turns out that the Arch64 has no instructions for the 128-bit floating point except load and store, so everything has to be done as library functions. And I plan to use the existing library functions to implement it. Function calls, fortunately, there's only one function call sequence to deal with it. And interestingly, it's very much like the Windows 64-bit function call syntax. So the neat thing is I already have the code to make that work in the code generator. So, ta-da! It's kind of fun. You can pull various pieces out from the various code generators and patch it together, and you have an Arch64 code generator. And wait for the mic.
If you could go one slide back, is that meant to say by value?
What?
Because using structs less than 2 registers are passed by reference, and larger structs are passed by pointer.
Oh.
That seems odd.
Well, you are correct. It's embarrassing how many times I go over the slides and wind up with the inverse of what I meant, but very good catch. Unless they have constructors, then they're passed by ref. The people who come up with how to deal with variadic function calls, I think their motive is to punish anyone who uses variadic argument lists. Because you get this ridiculous amount of code generated just to deal with it. And even worse is every platform and every compiler has a different scheme for it. They can't decide on, we're going to follow this scheme. So you don't really need to understand this. This is stuff I have to deal with. I just wanted to show what the complexity of it is. And you'll see the code that reads these data structures is in the varargs.d import. And here's the kind of code it generates. Every time you have a variadic function body, this is kind of what you get. And the code generator code to do that is, I hate it. It's ugly. I can't think of a better way to do it. Unfortunately, the kludginess of the instruction set shows up as the kludginess in the code generator. Bye-bye. If anybody has questions, just feel free. Okay. Now we get into some differences between the instruction sets that matter. the x86-64 literal encoding is done using variable length instructions. So x86-64, there are instructions to load an 8-bit value, a 16-bit value, a 32-bit value, and a 64-bit value. All have different encodings, and it's all done in line. Floating point constants are loaded from memory because there are no floating point instructions that have embedded floating point values. Literals and addresses can be easily coded into the instruction. So we have the ARCH64 literal encoding problem. 64-bit address does not fit in 32 bits. A 32-bit value does not fit in a 32-bit instruction, neither does a 64-bit value, and a floating point value does not fit into an instruction. So even though all the instructions are 32 bits, there's, well, I wonder how they deal with this problem. And of course, God bolt to the rescue. It turns out that I said earlier that the ARCH64 was a very complicated instruction set, and it's complicated, weird, and wacky in a completely orthogonal way to the weird and wacky x86 64-bit instruction set. So I kind of think they failed to actually improve it. It's just different. My favorite, of course, is the PDP-11 instruction set, which figured out how to do literal encodings in a completely, extremely simple manner. But that's why the PDP-11 instruction set is a gem that has never been equaled or exceeded. So it turns out what you wind up with is multiple kinds of instructions depending on what your integer value is. It turns out that there is no instruction to load an integer value. What there is an OR instruction. You OR it with 0. The W31 is usually the stack pointer, but it turns out you never need to OR the stack pointer with everything. So in the ARCH64 instruction set, the stack pointer is actually interpreted as the value 0. So they can get rid of a load of a value by simply ORing it with 0, which, you know, I reluctantly admit is very clever. Wish I had thought of that. And so 0, of course, does fit into 32 bits. So does 1, 2, 3, 4, 5. Well, that fits into 32 bits. But what are you going to do with large values like negative numbers? Well, it turns out there's an instruction called move negate. So now you can have small negative values that will also fit in 32 bits because the instruction negates them. But that's not a complete solution. And at some point, you're going to have to use 2 instructions to load a value. Now, I was puzzled when I was first reading the instruction set is why is there's this load in immediate value that is shifted left then by 16 bits. Well, I found out why. You have to have 2 instructions. One is the bottom half, and then the other is the OR's in the top half, shifted left by 16 bits, and oh, by the way, it can also be negated, shift left by 16 bits. So I had to write this function, which is load a immediate value into a register, and it figures out the optimal sequence of, you know, which instructions are going to get me into the register the value I want. And it turns out that some of those are very complicated, and it took me a long time to figure out how the algorithm to generate an immediate value actually worked so I could implement it. Floating point literals. I was looking at that and looking at it and looking at it, and finally I figured out what was going on. Is the floating point literal is encoded as an 8-bit floating point value. Now, how many people work with 8-bit floating point values? they actually seem to be used in some AI things for the weighting. Well, anyhow, you have 8 bits, so you have a sign bit, 3 bits for the exponent, 3 bits for the mantissa. And it turns out that most floating point constants are fit into that form rather naturally, so this is fairly efficient. But if you want more complicated ones, the only way to get them in is to load them from memory. So that requires 2 instructions to do it. The first one loads part of the address into the register, and the second instruction loads indirectly through the first address and adds another constant in. And those ART64 things are called fix-ups. And those are replaced by the actual location of the floating point constant. Doesn't that just make you happy seeing that? This is what you need Godbolt for, because Godbolt will actually, in its disassembly, point out what the relocations you need are. So it turned out that I had to spend an hour trying to figure out what are the relocations for the ART64, and I would see all these descriptions of them, but none of them ever gave the values for the fix-ups, and so I'm still working on that. That's why I need a disassembler. Oh, that's the bit pattern for these names. Taking the address of something is something similar. It's also done with 2 instructions with 2 fix-ups. And notice the LO12 as part of it. There's the high 21 and then the LO12. Well, you can guess what that is. You have one gives 12 bits and the other gives the next 12 bits. Okay, the current state of play is my first target was the Raspberry Pi, because I'd had that for years and never found a use for it, and I finally found a use for it, which was generating a code generator for it. So I've been working on that and actually got a bunch of programs to compile and run on the Raspberry Pi. But I don't think that's really going to work as a target. So in the last week, I bought myself a new Mac Mini and spent 3 days trying to get it to compile anything. And so I'll be working on that from now on, and that's the new target. I have not implemented complex numbers. I have not implemented SIMD. I don't know how any of those instructions work yet. I have a partial implementation of half floats, no inline assembler. My goal is to get it to work and not pay any attention to optimization. You can really go down a bad path if you start optimizing too soon. And there's also the implementation problem of the 128-bit floats. Okay, it turns out that mastering the instruction set is not very easy, because although you can understand the bit patterns, how the instructions play together is not really easy to figure out, and that's where Godbolt comes in. And having an existing code generator that I can reuse much of has been a great accelerant for getting this done. So, I guess we have time for questions.
And applause.
Thank you. Well,
yeah, I wonder if you have a SIMD support with a Neon extension, you could have a floating point 128-bit arithmetic with those instructions. Is it possible to do without the functions that you implemented?
yes, because, well, That's also possible with the SIMD instructions on the x86-64, but it's done with completely separate code because although it's the same idea, it's a totally different scheme used with it. So I don't really know anything about the Neon instruction set. It's just I'm not going to worry about it till everything else works, but I will make it work one way or another. If I beat my head on the wall long enough, I will eventually figure out a way to make it work, just like I did with those Q registers.
How far off? Sorry. How far off are you getting to be able to compile DMD with itself on Arch64?
Okay, here's the order in which things go. One is to get hello world to compile and run, and yay, we've got that working. So the next thing I've been doing is trying to compile the test suite, not run it, just get it to compile. And you'll find, well, I find all kinds of things I've missed. So the test suite is invaluable. Once that works, then I need to get the runtime to compile. Not going to try to execute it, just get it to compile without error. Once then I've got that thing working, then the thing to do is, and this is why I've been so adamant about the test suite not requiring Phobos to work, is then I can start running the test suite with the compiler. Once the test suite passes, then I go to Phobos and get Phobos to work. Once I get Phobos to work, then I can get the compiler bootstrapped on it. So I've done that order before. It works. It's the most straightforward way to do it. If you try to do everything at once, you're just in for nothing but misery.
My main rig is a Windows ARM64 machine, and once you've done all of that, could you please add the ARM64X linker format and ARM64E code gen, which is a way to mix and match x86 function and Arch64?
Oh,
the same binary thing? Because the Windows situation is quite complicated.
Oh, that doesn't sound enticing at all. Unfortunately, because it sounds like a major project, I don't want it to interfere with getting the rest of this language to work. So yes, I want to do Windows support, obviously. I want to do Linux support, obviously. But you know, it's kind of a critical thing getting the Mac stuff to work, because right now it's working in emulator mode, which cuts its speed in half. And I know that the Intel architecture seems to have reached a dead end. And if DMD is going to survive, it needs to support the Arch64.
Okay, this is not a question, but in the beginning you said we don't know why it's called ARM Arch64. And if you compare it with, I asked an AI about it, and I don't have a site for this, but I believe it 100%. So if you compare it with x86, you have the Pentium, the 386, which is an x86, and then you have the core 2. But if you look at ARM, you have ARM 4, ARM 5, ARM 6, ARM 8. And it would have been very weird to say, now we have ARM 8, which is ARM 64.
Okay, yeah, that makes sense. Yeah, the nomenclature for the x86 family tree is completely crazy. So they failed to avoid that with the the Arch64. They walked into the same tar pit.
Yeah, so I think in addition to Windows, Mac also has universal binaries that work with x86 and ARM. So I'm not sure if that's on your roadmap as well.
I did not know about that. I don't know even if that's a compiler feature. It may be a linker feature.
It could be a linker feature. I'm not sure.
Yeah, if it's a linker feature, I'm not going to worry about it. You know, linkers are supposed to be simple programs, and for the original PC, they were trivial programs, and they've just turned into these monsters. Anyhow, we got 4 minutes, so now's your big chance to humiliate me.
Come on, he's waiting. Anybody got a question? Should check if we got an internet question, actually. I'm checking Discord and YouTube today. Oh, say something, somebody.
I think that the RISC-V would be easier.
The what?
RISC-V would be easier than this.
I don't know anything about the RISC-V. Sorry.
I have been working with the MIPS architecture, which is very similar with also having 32-bit instructions and loading immediate values with first the upper half and then the ORing in the lower half or something. And as far as I know, that's because there's a fixed instruction size, so you cannot fit a 32-bit instruction or immediate value in a 32-bit instruction because there's no opcode left.
But you can do it on the PDP-11.
Yeah, so I was wondering, how does the PDP-11 do it? Does it have variable instruction length, or does it have some genius way? Or
It has some genius way, which is why the PDP-11 is the greatest instruction set ever. The program counter is a general purpose register, which means that you can move values into it, you can increment it, you can auto-increment it. So you know where I'm getting at? What happens when your source operand is the program counter auto-incremented? It reads the next 32-bit value out of the instruction scheme. So it requires, things like, branching to the thing that require no new opcodes, because the branch is just simply moves the program counter into, or moves the target value into the program counter.
the immediate value is kind of intertwined with the instructions, and with clever program counter manipulation, you read it and then continue. Oh, that's actually, I have never
It's brilliant.
that.
And if you look at the assembler books, you don't see any of that. You just see move this register, this value. And under the hood, the macro assembler generates the extra things, but it's not actually a separate instruction. And the pre-increment and pre-decrement and post-increment work their way into the C programming language, as we all know, was plus plus and minus minus 1. So that's where it all came from. It came from the 11 instruction set.
I want to study that instruction set now.
Okay, well,
PDP-11.
I'll send you a copy of the one-page. You're looking to go, oh my God, this is so simple. Oh, the PDP-10 had an even funner one. They saved on addressing modes by the bottom 16 memory locations was the CPU register set. So if you wanted your code to be really fast, you fixed it so it fit in the registers, then you execute the registers. It's too bad all that stuff has died and disappeared. People always say, when they developed the 68000, oh, we're building an 11-like instruction set. And no, that's not 11-like. It's they couldn't help but try to fix it and made a mess out of it. So.
Yeah, I think we can do one more question, but you guys know the rules. It needs to be a good one. The back there.
Yeah, Walter, you know why the PC as a general purpose register isn't a great idea in terms of making things go fast. I mean, basically, it creates havoc in the microarchitecture. I mean, it's great. It's great from an ISA. It's cool. I mean, we both grew up on DEC stuff and 11s, and I actually remember people who were in the game of putting things in the registers on the DEC 10, but I sympathize, but I'm just noting that there are reasons why they actually are not in current modern architectures.
I have heard that reasons, and they do so many clever things with microcode in the x86 I don't believe it. It sounds like excuses to me.
Okay, it's interesting.
Yeah.
All right, so that's it. Let's give it up for Walter. My main takeaway from that is that we're getting 16-bit floats, so yes, good work.
Yes, at least for the Arch 64.
All right, so a little bit of housekeeping before we send you off for a 10-minute break. Lightning talks, you all know what those are. They're fun, 5-minute talks, any topic, as long as it's relevant to the D language. Talks are as fun. We have 8 slots in total, 2 have already been filled. If you have an idea for a talk, and well, I mean, we do still have the gong here, so I suppose we can do another one of those rounds of bad jokes. But if you have something other than that, please fill them up. Fill them up now. Go now. Yeah, come back by, we can give you 15 minutes. But yeah, go fill up some lightning talks, guys. So back here in 15. Yeah. Yeah, this setup looks tight. I want to work out how to do an Ali maneuver this week, but I'm not seeing any weaknesses. You've done a good job back here, guys. Can't fit my foot down here or anywhere. All right. We got a minute remaining, so I'm sure you people downstairs can hear me. We do have another loud Australian here today, as you would have worked out. So, yes, thank you, Nicholas. Come on, applause. Applause the loud Australian. Now, what's the point of being loud and Australian if you don't get applause, right? Anyway, we've got a seasoned pro of the D conference circuit here today. Once again, going all in on D-Lang. He's done it a few times now, but now he's doing it even more. So, Mike, would you please come up onto the stage and take it away?
All right. Thank you. Thank you. Thank you for having me, everybody. Hello, everybody online. Thanks for joining. It's great to be here. And as Ethan mentioned, I am all in, even more all in on D-Lang. And I want to talk about why I've pivoted to D for some things like web, teaching, graphics, in 2025 and beyond. And really, I'm just going to be showing a bunch of projects, things that I've been working on in many different domains. There'll be some snippets of code you can dive into later. They might be interesting to just take a peek or flip through the slides. So feel free to do that now or later when I have the slides posted. So anyways, let's go ahead and get started. You've read the abstract, you know about that. My primary role, I'm teaching faculty at Yale University. So that's kind of the main point of this, and talking about teaching in D. And some other things I've been involved with, a lot of YouTube. So if you don't know, or you're learning or watching online, we're at episode 136 now of the D language series. So, and counting, I think we'll make it to 150 by the end of the year. So really excited to be doing that. So anyways, enough about that. Let's get on to the talk here. So again, I'm going to be showing you some highlights today and talking about some different projects and codes and snippets and things that I've been working on in a bunch of different domains. So from web, scripting, game engine projects, mostly for my students, graphics projects, again for my students, teaching. But I think what the real thing is about this talk, or at least for me here, is kind of ignoring the noise a little bit. There's a lot of fun things to program in, a lot of different systems languages, and this is a great thing. I mean, we really are in a sort of golden age of programming, I think, where there's lots of options and people are exploring different things. But I've just found that the D programming language has been the right sort of signal in the noise, or whatever analogy you want to use, for me. It's been a great tool, and I want to choose the best tool to be the best software engineer, the best computer scientist that I can be. So again, I just want to talk about how D fits in these different domains. So the very first one, web development in the D programming language. So a little bit of a story here for part one here. My web programming needs, since I'm teaching, are to, well, build a faculty page with the same picture from 7 years ago, never update it, and course websites, these types of things here. It needs to be reliable. There can't be any crashing, especially during class. There's kind of bursts of users who jump in, if I'm teaching a 100-person lecture room, so there's lots of students clicking on things, there's some dynamic updates. And it does need to be cost efficient and secure, right? I don't want to be spending tons and tons of money on this. Or get hacked, these types of things. So I need to build a Web 2.0 sort of website here. Something that's dynamic, can be updated, and folks can work with. So when I think about web development, or search around for web development, what type of website should I build? You usually run into these types of things. A LAMP stack, Linux, Apache, MySQL, PHP, or Mean Stack, or Flask and Python, or Django, or an infinite number of frameworks that exist. And these are all very popular, and also great technologies on their own. And I probably wouldn't get critiqued if I told someone, oh yeah, I chose Flask and Python to build my website in. They'd say, okay, yeah, that's great. Tell me about that. So I did that. I mean, I kind of chose the basic stack. I started writing some PHP around 2022, 2024, with a MySQL database. And, you know, if you read this code, I'm just kind of echoing out some HTML. I mean, at this point, you can, you know, throw the peaches or tomatoes at me and say, that's bad code. But I didn't really know what I was doing. You know, I was more focused on trying to figure out this new language. And again, I had learned some web stuff. Back in the day, I did ASP.NET and C# and some of these things. But, you know, it's just kind of a classic mistake of, I'm trying to learn a new technology. I'm so focused on the syntax, learning the library, what the right PHP function is this secure? I don't want to get hacked. You know, all these different things that I'm working on. And then I end up with something kind of like this. You know, in the bottom picture, just echoing out my HTML with a function and saying, oh, yeah, that's dynamic, right? I can, you know. And anyone who looks at this just says, hey, OK, so you're doing PHP. Just use WordPress or just use Drupal or, you know, one of these other frameworks that exists. And I don't really want to do that because that's just another tool that I don't understand. I don't feel like I have control over. So, you know, what kind of happens is when I, you know, look at all these frameworks, I don't get as curious. And then I just have this sort of cognitive overhead of, OK, I'm teaching a class in this technology. I'm doing a hobby project. I'm consulting in this language. And now I'm also managing, you know, a totally different tool stack here. And it's very healthy to learn a lot of different programming languages. I love doing this. I've probably explored about 30 or 40 languages in the last year just for fun, and that's documented on YouTube and such. But you know, I'm not feeling like I can leverage my D knowledge here where I'm trying to build some expertise. So there's this other example that sort of sticks out in my mind when I think about web development. This is a project by now is several years old, 12 years old. Hip hop for PHP. Has anybody heard of this? I think there's variations of this. Yeah, this was kind of famous, or you know, one of those projects that probably popped up on Hacker News many years ago from Facebook, now Meta, where basically they said, OK, we've got all this PHP code. Why don't we just transpile it into C++? Right? A compiled language. Compiled languages are typically faster, and that just kind of seems like common sense to me, right? Why aren't we using a compiled language here? You usually get more speed. I understand there's, again, trade-offs with scripting languages. So I want to do that. But I want to skip the transpiling part of my PHP into some other compiled language. Why don't I just write my code in D and get native code? This seems a lot easier. And the other question I had, too, with this, again, that seems sort of like common sense, is, well, if a compiled language is faster, and I can serve my pages with maybe less overhead or these types of things, do I save money by doing this, right? Is there less compute if I'm running this on the cloud? And somebody actually beat me to this in the D community. There's a nice blog post about this several years ago about saving money by switching from PHP to the D programming language. So I said, oh, that sounds great. Of course I want to save some dollars here. So I did it. I built my website in D. It looks exactly the same, effectively. You know, you can see me moving around and clicking some things and accessing some, you know, records in a database to build this page here, and that's great. And my web tool stack here primarily consists of Handy HTTPD by Andrew Lawless, who built this, and it's basically just a simple HTTP server. It's relatively lightweight, well documented, and I could abstract on top of it. So that's what I went with to kind of build this Web 2.0 website. I also used a Postgres SQL database, DPQ2, as a dub package. It just worked. Again, it's a wrapper over the C library for doing database stuff, and that was great. OK, so you know, you can see some code here. That's part of my website here. But again, what was kind of nice is now that I'm just in this D world instead of PHP is, well, I can start leveraging the tools that I'm used to. I have Phobos. I can use the date time, you know, module that I'm used to using. I can use the same abstractions, data structures. And I start leveraging, you know, even some of the same code that I've written before for networking, things like, you know, working with socket libraries, getting IPs, these types of things. So it becomes very handy to just not have that cognitive overhead of learning the whole new language and just working in something that I'm experienced in and I'm comfortable. And I'm also, by working in a different domain than I'm usually working in, graphics is usually what I'm here to talk to you about, I started thinking about other parts of the D language that I'm not always exposed to. So handling exceptions, these types of things, other parts of the language that, again, expand my D knowledge, which is great. And other things start to happen, too, which are interesting because, well, now that I'm in a systems language, I start thinking about things like, well, just using associative arrays or maps for creating logs of visitors that refresh over time. Or maybe I can cache pages, because now I'm thinking about things in terms of memory. And this is exactly what tools like Nginx and other server tools do for you. But again, I've got my systems hat on. And I couldn't really think of a better analogy. Maybe I'm just a little tired. But it's kind of like when you're playing an instrument, you have a guitar in your hand, and you think about playing guitar. But if you access some different tool in a different domain, well, now you're playing guitar, and maybe you say, hey, I'm going to take a violin blow and see what it does, or play the guitar like a drum. So that's how I kind of felt here. I'm in this different domain, web programming, and I've got my systems programming language doing systemsy things that I would think of. So I thought that was kind of neat side effect of just switching to and just working in D, which I was comfortable in. Again, no wrestling with other languages. Now, most of this website, if you actually want to look at the implementation details, is using things that, again, are like a builder pattern, these types of things. And again, this is nice because I'm echoing out, less HTML, like I was doing. And I can start thinking about doing the sort of D things that, we like doing. Maybe compile time function execution. I can start reserving memory. I can use appenders, these more sort of efficient structures here for building up strings of information. And I can even go further and start doing things with templates for code generation. These are the things that, for those who are using Vibe, already do, right? And do that well with the diet templates and so on. I'm just, again, sort of doing this from scratch. So I did my website. I did it in D, and I saved money. I'll admit this isn't a super controlled experiment. I'm not getting millions of users to my personal page, which is totally fine. That's a good thing. I'm not ready for that. But my cost now is effectively free for hosting my website. It's not even registering like a penny a day for my traffic versus it was doing about 24 cents a day for various traffic and compute costs that we're running. So it's not a rigorous study, but if you want to say it's 24 times better, we could say that today. But it was kind of cool or encouraging to see that, hey, the time put into this made sense. And there's still more to go here, using some of these already existing tools like Nginx and so on to get more experiments with caching and saving more money here. So we'll see when the semester starts and students visit the page how it goes. OK. And I do want to give a note here on Vibe, because that's probably the most well-known D framework, as far as I know, for web development. And I just wanted to give it a shout out, because I think it's really cool that on the D language tour, there is a tab for Vibe.D. Maybe this is something we should think about, having some of our popular packages in different domains there to say, hey, D can do a lot of things. It is a system language for reading, writing, and running fast code. But you can do that for web, system stuff, games, and so on. And there's lots of other great web frameworks if you're thinking about checking them out. Again, Vibe, Handy HTTPD, Servino is another great one, and so on. OK, so that's on the web. What's next? So I'd like to document this, again, with the whole YouTube thing here. I think it should be shown in the space how I did this on the cloud, so that's something I might consider doing for our hackathon on Friday. Maybe these will be one of the projects to just sit down and do a little screencast of how I set everything up. There is also some interesting stuff here, too, thinking about D on the web that folks have already known about for, again, over a decade. I stumbled upon a DConf 2014 talk by Fanatics, which is a game company doing their mobile backend with the D language. So again, some cool stuff there. OK, so the next part here, scripting with the D language. So we've already done web development with the D programming language. It can also be used as a scripting language. Again, those of us here know this, I think. And I think I've said this before, maybe in different venues, but I'll state it officially for the record. D has replaced every Python 3 script that I have. I don't use Python anymore. It's a lovely language. It's got its uses, but I use D for everything there. And I think that's a real superpower. Again, I want the compiled speed. I find as fast as DMD compiles, or RDMD in these cases, it just serves my needs. So I'm going to flip through just a few utilities, scripts that I've written that are kind of fun, and you'll kind of get the idea of what I'm using it for. And my other main point of it is, if you're not using D in your daily life, but you like to, often for these sort of command line utilities and these types of things, usually you can pick whatever you want at work for those, one-off things. So again, I use D. Again, as an academic, I'm a little bit more free, but that's something to consider here. Okay, so script number one, you'll kind of get the idea here. Having access to curl right within Phobos is really, really neat. And JSON libraries, no dependencies, I just go, right? I have Phobos ready to go. So I use this for hitting various APIs, like REST APIs for YouTube. So I can just make a quick website with my newfound web programming skills to list out all my videos on one page. And then I can do Control F and find everything, or you can find everything. Okay, so that's one script. One day's work, less than that. Same idea. Writing little web crawlers. The Game Developer Conference has an awesome vault where they host a bunch of talks, but it's really hard to search through, so I said, enough of that. I'm going to write a 110-line script and just download every talk and a link to it in a description. Done. Pretty much the same exact code, okay? Because we know how to use those few D functions. And what you'll see there when you do want to explore the slides is basically the crux of what you need, or at least how to structure things. Okay, same thing again. GitHub API, another RESTful sort of interface here where I want to ping GitHub. And again, I'm using this to do things like make an API call to GitHub, run some commands to push new assignments to students, download their assignments, run their assignments, all these sort of things. I built a little command line interface for that. It's about 430 lines of code with error checking, security checks to make sure I don't override stuff, but all done in D. Again, translated from my old Python stuff. I wrote an auto grader, again, very, very useful. 141 lines of code. And again, beautiful thing about using D in my classes is basically I just search for a dub.json file and run dub, and then I'm running my students' assignments and can grade them. Very, very nice here. The other nice thing is, I have things like process isolation, my running with std process and these utilities. So again, just nice little things that you're used to having in your script utilities. I'm also showing this script to either make fun of myself or also just document the first time that I've used a goto in maybe 10 years. So if you notice at line 108, I have goto label, very nicely named here. If I want to rerun the assignment, yeah, it's probably it's in the language, so, I can use it there. Not since I probably was writing BASIC did I do that, but for whatever reason, I was like, this will work, and it does, because I'm within a loop and I need to jump somewhere. Anyways. All right, so some other cool stuff. Scripts, markdown to HTML transpiler. So I want to start doing blogs and these types of things on my website, so I wrote a little transpiler here for this use case to say, okay, I've got a markdown file, write some HTML. So again, simple enough. This is one day's work to write this little tool here. I'm going to document about it in a blog post eventually. Okay, so then I graduated from blog builder to book builder. And I said, hey, I should start documenting some of this stuff that I'm working on and write a book. And if you're writing a book, it's probably time to use some tool. Something like Pandoc is a popular tool where you basically can translate markdown files to generate PDFs or websites or these sorts of things. And what ends up happening is I sort of start writing one chapter of each section here, and then I've got a whole bunch of chapters. And then I've got to build the book. But a really great feature in D, of course, I think many in this room will know, is just doing dot parallel within a for each loop. And all of a sudden, I can start building all these Pandoc, or run Pandoc rather, multiple instances, converting markdown files to PDFs and then glue them together. You can see the use case going from 12 seconds to 1 second. Again, iteration time is everything, but again, just adding dot parallel in a for each loop is perfect here. I just learned this on the forums. I think some folks were posting about it who are here. You could do .parallel with, play around with the work sizes, but you get about the same results here. Okay, so that's great. Just another nice command line utility we have. Script number 7, last one I'll talk about here, is a little SDL3, which is a graphics library, a C graphics library that I use in my courses. There's many bindings available for this, sort of building C bindings. So I thought I'd have a little bit of fun with this and try to write my own. I would recommend that folks just use the bind BC SDL bindings for this. But I had this idea that I said, hey, if I use NM, which is this tool for looking up names of symbols, and I just run that on the shared library, I'll get a list of all the symbols. And then similar to what Walter was just talking about in his talk, the documentation is just libsdl.org/ whatever the symbol name is. So I said, oh, okay, then I can have all the symbols, generate a URL, and then I'll have that and be able to click to it. So if I have my nice D binding, or this sort of translation of the C binding into a D interface, then what I can do is see the symbol, URL, and then I can actually look at that page and then grab, using my HTML skills, the documentation, and just have it all in sort of one file, just so I can see everything and sort of grep around it. So anyways, that was the result of this script that took half a day to finish. It's not perfect. This is exactly the type of thing that you'd probably want to, again, either use bind BC, the more mature C bindings, or maybe play around with import C and see if that would just do the task. But anyways, it generates a file like at the top here with all the function names, what it's trying to do, and then another pass to put some documentation in. And it's doing some other stuff to try to find all the symbols and do some translation of SDL types to the D types. So anyways, that was just another fun little script. Let's see, this one was, I didn't have the line count here, but this is just a few hundred lines of code again. 1 day's work for this. Okay, so that was on scripting here. And perhaps if these tools are useful, this is the type of thing that will, again, get a web interface as they grow. But I feel like using D in this use case gives me the ability to scale. Another reason why I really like using the D programming language for my scripting needs. OK, next topic here. What else am I doing with D? I'm teaching with D. Well, we know this at university here. And from Ali, who I think is on the live stream somewhere here, from his book that he wrote, Andrei Alexandrescu also wrote the foreword for it, and he states, I've long suspected D is a good first programming language to learn. It really scales with the learner, and I really believe in that. I think D is a language that scales from beginner programmer to expert. As we can see in this room, we've got a variety of folks in. And I've got a quick list of other academics I know using the D programming language, including folks who are in the room and going to give talks later this week. So they are here and using the D programming language. And I keep finding more and more folks using it. They're not as vocal about it, but in great universities, great places, top institutions in the world are using D and teaching it, or at least introducing it. So it is there. And I even found this. I'm going to leave this for you, maybe for lunch, an Ode to D by Luther, who's over at University of Illinois, Urbana-Champaign. That's how much he loves the D programming language. He wrote an ode to it. So you can read that for fun later. Do you write D, a colleague said. I do, was my reply, and so on. OK, so I've been on a bit of a well, I'd like to pretend I'm a rock star, but a speaking tour, let's say, talking about the D language and why I'm teaching it. So earlier this summer, I was at the New Jersey Programming Language Symposium, which is hosted by Jane Street. And then also the University of Illinois Urbana-Champaign hosted a computer teaching workshop where I talked about why D has been my sort of secret weapon for teaching. I call it my 2 to the X language, sort of making fun of this 10X thing. But you can watch the full recording of it there. And the highlights of it for my exponential gains in teaching are, some of them are just simple things, like having a package manager and a build system. It doesn't matter, just a simple one does the trick. So we know about Deb, for instance. Other little things like modules, having multiple paradigms, unit testing, all these little features add up because they work up in harmony so nicely from a teaching perspective and just a real-world engineering perspective. So teaching's been great. And I've pretty much, again, since spring of 2023, been converting my courses from C++ to D, in which I was teaching modern C++. So this is software engineering. Primarily these days, I'm teaching real-time graphics and building game engines, which I'll show you about. But again, this is going on and has been a huge win in terms of what I see students building, how far they're getting, and I have data points for this, which has been awesome. And this is all a little bit of old news, but a conference talk from 2 years ago. Again, you should hear it from the students. They came and talked about it. They get their honest opinion. That was all I asked them to do here about how they feel about using D. So what's next for D in teaching? It's probably time for another D programming book to start getting drafted. It's actively on my mind, and I'm working on a book right now. I can't give you a title, but it is going to have one chapter at least of D stuff in it. And then it's probably time to put something else out there. So I'm really excited about that. That's been long overdue. Okay, so as far as, while we're still on this academic thread, research in D-Lang, what's going on? Well, I had about 12 research students this past year, and they get to choose whatever they want, and 5 of them, which I've highlighted here, chose to do their projects in the D programming language. Others were doing things in like game engines, so there wasn't really a choice there. And they did some really, really awesome work. And I do want to shout out Razvan, who supervised one of our students together. Matthew and really Razvan took a lead on that and deserves a round of applause for all the work he's been doing there. Because it's been awesome. And it made my life a lot easier, and our students all had great outcomes. So anyways, they're doing some really cool stuff. A few students, doing graphic stuff. And why am I highlighting, some of this? This is a student, Simon, who built some graphic stuff. And when I taught graphics before, this is just an intro graphics class, but he's already getting into stuff where he's doing Fresnel equations and all these sort of like advanced things, level of detail algorithms, he's messing with Perlin noise and water reflections and normal thing. This is the kind of stuff we don't usually get to, and he's getting to it in a semester. So, it's, sometimes you get some great students and they do some great stuff, but I'm seeing this as a trend. Everybody's getting further in the course. So, what is it? I think the D language has a large part of this that's going on. Matthew, the one student, also was working on some really cool stuff. Again, he was working on some of the coupling semantic routine from AST nodes for the D compiler. But he also got into, for his final project, doing mesh simplification, which is getting into really interesting data structure work, doubly connected linked list or a half edge is sort of the data structure. And again, these are things that students don't normally touch or just like run into when I'm teaching graphics in other programming languages, but somehow they keep getting into it. And it's more than one student, right, who's running into these things, which I'll show you in a moment. So anyways, I'm going to be getting more students working on their senior theses every year with me. And if you want to collaborate, if you have real-world projects, these types of things, my students are coming out with a solid year of D experience. So come talk to me if you think there's a good project. Maybe it's a package you're working on. We're looking for real-world stuff to collaborate on. So I'm going to continue marching along with research in this direction. And you saw, again, a bunch of other researchers using D. OK, so a few other things here. Game engines, one of the courses that I'm teaching with the D language. So again, I'll just show a few samples of the types of stuff that folks are building, again, in a semester without any prior D programming language. This is what they're starting with. So this is a project by Eric. Basically, what you're looking at, just the top animated GIF, and then there's some images below. He built this entire game engine for building rhythm-based games with a node graph, where you could basically program games by just using nodes. And that was super, super cool. This is all in D and SDL, which is the graphics library that I mentioned binding earlier. So this was a really cool project. I'll just highlight a few of these, and there's videos for them. Another game engine by a team of programmers full editors for building 2D games. You can see them building blocks. And they're using some pretty clever algorithms to do things with bit masking for automatically generating the tiles and these sorts of things. And level saves between runs, some of these things like hot reloading and so on that we see in game engines and might learn about later today. This is a cool project from Alexa. It was pretty cool because they actually found on their own dlang GUI and downloaded it, modified it, and said, okay, this is going to be the basis of the game engine. So you can see some of the stuff they're doing with the sort of space invaders. And they've got their scene tree and manipulating it with all the different entities. So if you're interested in some of the game stuff going on, feel free to watch the full videos where they highlight exactly what they did, how they use the D language. And I asked them to sort of show at least one technical thing that they did in D. So you might learn some tricks from these students. And at least one of those projects, I won't say who just to give pressure or to avoid giving them any pressure, is still working on this and hoping to publish their project. Okay, so on graphics, so yeah, it's still more D. So this is the other stuff, again, I've been sort of advocating for. I was at ACCU earlier this year, talking about the case for graphics programming with D, why I found it really nice to work in. And if you've seen my previous DConf talks, this is sort of the full 1.5 hours of all those talks plus more, talking about graphics stuff. But as far as my students and teaching and the sort of game framework that we build up, here's some of the projects that they built. I'll go ahead and advance, and you're going to see these animate in a second, so just kind of keep an eye on it. Most of them are going to animate. But again, these are the types of things that just wasn't getting to in previous courses. So stuff like constructive solid geometry. You're going to see this house get sliced in a moment, which is really, really cool. You got a full simulation here running in real time here, simulating physics. Minecraft, fireworks simulations, nice reflections. Folks getting into compute and tessellation shaders for a bunny. This particular student built a full 3D modeling tool for sculpting, where you can bevel and extrude things. So again, really, really cool stuff. Painting on textures and so on that aren't assignments, but students just got curious and really pushed the envelope here. And for my own notes, just using D, teaching it, building my own little graphics framework along to support the students here, I'll just kind of share a few useful snippets, anecdotes, things going on here. In the language, again, you can kind of look at some of my abstractions for a graphics pipeline later on. But even simple things like there are many linear algebra libraries out there, but again, with D, I'm easily able to replace some of the popular like C++, GLM libraries. It's just relatively easy and it feels more understandable. Things even just like grepping for the operator overloads are just things that I actually really enjoy in the D programming language. And I've got variations of this where I can template the library and use mixins to generate various operations, which is really cool. Of course, unit test, a favorite feature, using it with the code coverage tools, but for correctness and documentation. Again, a win for building real-world tools and documenting this stuff to distribute. I've leaned into using classes and these types of things in my graphics engine. Ultimately, students again build something like this themselves. So this is just a little sort of interface for the materials. So if you have different objects, they should look different. That's what a material is. Because I just kind of like the class semantics here. And I really just care about the malleability when we're being creative and building things while I'm trying to solve a problem. And then we can always sort of optimize it if we want. And just for completeness sake, again, if you want to sort of dig through this sample, you can see if you're doing some OpenGL programming, how I use inheritance here to implement something on top of, to create a different material, basically. But again, if you don't like that, again, because I always hear folks say, but what about performance? You're a graphics programmer. I say, okay, don't worry. I can do stuff like create interfaces with structs. So this is just a sort of small example I have of using user-defined attributes to say, hey, here's a struct at line 38, and I have this UDA that says, okay, I want to treat this like an interface where it has to implement the member functions here. And I'll have a full sample of that posted so you can see how that works. But anyways, you can build these things because, well, it's a programming language. You can do whatever you want, and D's metaprogramming features are awesome. Inheritance, same story. If you want to use structs with inheritance, here's me doing a minimal sort of vtable type of thing here, so you can use that. But you get the basic idea. It's all available, so you can go as low performance as you want or as high performance. I also, this is another thing I get questions on. I say, hey, I want to use better C. I don't want to use the built-in array. And I say, okay, here's my dynamic array implementation. So I have this that's better C available. It works with slicing, all these different things. Mine's a little bit weird because I have a little Boolean that tells me if who the owner is, because they want to sort of keep track of slices and stuff. But again, I don't really use this. I just learned not to fear the garbage collector, and I don't allocate in my graphics loops anyways, so it's not really a problem. So anyways, just want to point that out as a few graphics things and snippets that might be interesting. So anyways, and then when the code is very malleable like this, where I can just kind of change things around, you come up with some silly ideas. So again, here's just a snippet of me using the sort of modern graphics API for OpenGL to create a dynamic geometry where I'm just using old school. By old school, I mean like 1990s OpenGL, GL begin, GL end to just push stuff in a vertex buffer object because you can. And this is kind of cool, and this is something I encourage students to do to create these abstractions if they find them useful, because they find a lot of code or AI generates this code and they say, well, I didn't write it, but anyways. But they say, what's GL begin? And I say, well, this is how we would implement it in our modern API. And we have dynamic arrays, things that just expand and you can pack info into. So anyways, this isn't an efficient example, but it's a playful one where you can come up with some nice ways to either prototype, or if you have dynamic geometry, like we were looking at earlier with Matthew's example, where you want to do these level of detail type of things, this might be something you try to do. So anyways, those are just a few of the notes on graphics programming and the malleability that I've found with some samples. So some conclusion here, some things I've been thinking about just in the last year here. I worked with this colleague when I was an intern, so again, this is like 10 years ago, at PlayStation, and he said, most people, Mike, overestimate what they can do in a day or a week, but underestimate what they can do in a year. And he told me that. I was like, hey, that's pretty wise. I think I believe that. So I kind of took that to heart, and I've kind of, adapted that to, the far worse problem, versus overestimating what I think I can do today is just underestimating how much you can actually do in a year, because that knowledge really compounds, and slow and steady wins the race. So I kind of committed to the D programming language over the last year. Last year I came on stage and said, I'm going to teach at Yale and this course, I'm going to do it in D. And that knowledge has really compounded to all these awesome things where I'm writing out a lot of code, which has been really fun. And it really is sort of this slow and steady wins the race, right? How many folks know this story, Aesop fable? Yeah, it's a good one. You can place your bets on the tortoise or the hare here. So I went all in on D in the last year. I'm going to continue working in the language. D is a tool, for providing, I think, a competitive advantage in programming domains for computer scientists. And I sort of, I think it's more akin to a rocket ship heading to Mars. While everyone else is shooting for the moon. So, use the right tool for the right job and, see where it lands you when you commit to it. So anyways, that's been my year in D. I'm happy to take questions or comments, and I'll be around all week. So thank you.
Hello? Yeah. You were talking about estimating how much you can do a day or a year. Well, I found I regularly run into slumps. I think that's something to do with the phase of the moon where, nothing's happening. And I found that if you just promise yourself, I'm going to work exactly 1 minute today on my project, 1 minute, no more, and then it'll be good. And amazing things happen. It's amazing how much you can get done if you work on a project 1 minute a day. And you'll also discover that you're working for 1 minute and an hour's gone by, and you actually get a lot done. So to complement your strategy on that, when you're feeling a slump and not productive, just tell yourself, I'm going to work for 1 minute on this today. It's amazing what you can do.
100%. I wore my running shoes because I'm a runner, and they say the first steps are the hardest. So just get the shoes on, the steps out the door, and you'll get your run in, even if you just say, yeah, go for 1 minute. I love that. Yeah, another question?
In one of those slides, you've got a simulation of a cube moving through water. Is that smooth particle hydrodynamics? And
It is.
That implemented fully in D?
It is, 100% in D.
Cool.
Yep.
And the code is out there?
The code is the students, so it's theirs to share. But it is 100% in D.
Oh, cool.
Yep.
Awesome.
Yeah. I think it was inspired by a Sebastian Log video, who's a YouTuber who does a few things, and also the paper in like 2008 or something around then, maybe from NVIDIA. They did that, and yeah, he implemented it. It was awesome. Yeah. Yeah. Ben.
Yeah, what's the response that you've gotten from educators or graphics people that you've been evangelizing D to that hadn't seen it before?
Yeah, most usually say, "Oh, D, yeah, I've heard of that. That's a cool language, right?" So it's always a mix of if I'm at the Game Developers Conference or something and trying to convince some AAA company, oh, you should use. I mean, I just don't do that, right? That's not my place. But usually they'll say, yeah, for tooling or these types of things, great, but converting a whole code base or something in a new language is high risk. Most folks, and this is still my opinion, say, if they don't know what D is, they say, oh, does it have pointers? And I say, yeah, it's a systems programming language. And I say, oh, okay, that's great. So if they interview or something, there's some happiness, I guess, for them. I think what's really opened the door too for D is in the game industry, right? C# is very popular. So that's often a sort of comparison when you hear oh, garbage collection. So there is a space for it. And again, some of you who are doing game development are going to know more about this as well. But generally, it's positive. As far as students go, there's always a little bit of hesitation at the start of the semester to say, okay, we're learning D. We heard games is all in C++. But again, I think I've convinced them that by the end of the term, if they want to use D as a C-like thing, if that feels better, because that's kind of how you'll use C++ anyways in the industry, they're usually pretty happy. They usually forget, because again, they get great results. And I show them that your projects are, I don't want to say on camera, doing very well versus others, right? So it's been a pretty positive response. But you have to really support it, though. That's why I'm doing all the YouTube stuff, all that, to make sure it's supported.
We do have an internet question from Sergin. Let me know if I've mispronounced that, if they're meant to be hard Gs. But he's asking, the students that are talking about D, do they compare their experiences with other languages that they've learned at university? And do they have any interesting findings with their views?
Most students, especially the ones that I've highlighted today, really love D comparatively because it's the first time that they experience doing stuff at compile time or doing metaprogramming, and that's very new to them and very exciting. So it kind of gives that advantage. It also helps that I'm working in a very fun domain, so they usually say, oh yeah, I love this class, graphics. So it's a little bit hard to compare in that regard. What I will say, and to kind of piggyback on both these questions, the students who are working on these graphics projects in D or the game class, they're getting the same rate of jobs that the other students when I was teaching this in C++. So they'll go to Riot Games or Meta or these sort of companies. They might end up working in C++ there, but it's about the same rate of those students. So they tend to really like D. They just end up going into industry and then not having the opportunity to use it more.
Thank you. Great talk. I have two questions. So about the web part, what do you do for the part that runs in the browser? And the second part is for the graphics. I'm really out of domain, but I guess these days you want to generate CUDA in the end. Can you do it with D?
Let's see. So second question, as far as APIs and stuff, so in the spring, it's probably about time to move on from OpenGL to Vulkan, DirectX 12, or Metal, those APIs, which you can do in D. Folks are doing it. I think we'll hear about it. There's libraries and bindings to Vulkan. So that's certainly possible. Your first question I missed. What was it?
So for the web programming, these days you need a part that runs on a server, generates HTML, and D is perfectly capable of generating HTML, but you also need a part that runs in browser. And what do you do about that?
Yeah, so the browser part, I mean, I'm deploying my D program as a web application running an HTTP server. So I can generate the HTML, no problem, just like I was doing, sort of echoing out. And then I'm running using basically Cloud Run, a custom runtime, which is running in a Docker container. So I can do any computation there. Does that make sense?
What about JavaScript? Do you write?
Oh, if I want to...
Do you write JavaScript?
Yeah, I don't have any real JavaScript, but I would just omit the JavaScript from D if I want any client-side code there, yeah. But as far as, again, doing any compute stuff, that's all just happening in D in a sort of Docker container in my web app, so to speak. Yep.
Just mentioned comment to this. We have made a hacked version of D runtime and Phobos in Wasm. But it's not complete. It's just worked for us. So, yeah.
Awesome. Awesome. Yeah.
Yeah, so I don't know if the previous questioner was alluding to this, but are you doing any shader code from D?
Yeah, so I'm still, as far as D code, students are still writing in GLSL. There is, let's see, where's Nicholas? Yeah, so D-Compute is the project to look at, probably as far as if you're going to do like compute sort of stuff and write it straight in D. Yeah, otherwise it's a traditional, you're still writing GLSL. Now in the framework I'm doing, those shaders are, it is acting like a game engine where you maybe write a snippet and then it generates, many shaders or permutations of shaders, so to speak. So in that way, D is sort of taking, again, snippets of, okay, you need this function or these values and putting together a shader. And then it'll run the, GLSL compiler, the, appropriate functions to compile the shader. Yep.
All right, I think we can do one more question. You know the rules. A good question. Who's got a good one? Okay, what about an ordinary question? Yeah, Walter, here we go.
I've been admiring all the fantastic projects your students are writing, and all the outreach you've done is fantastic. But there's one little thing missing from that, and that is I watch Hacker News all the time, and there's all these articles about, I wrote tic-tac-toe in language X, and they always get hundreds of upvotes. And it's just crazy that we don't have that stuff going on for D. So I'm wondering if you could encourage your students to not only create a little video of it, go on YouTube, which they're already doing, or you're doing for them, but to also just make a short article. I mean, it only short and simple articles about this stuff. You're doing fantastic work evangelizing D. I just want to take advantage of that, because you've already got all the material. It just has to be converted into a textual form. So I would surely appreciate that, and it would give your students some visibility too, because they get their name out there. It's a good resume builder for them, and I think it's kind of a win for everybody. So
absolutely, I'm going to do that as an action item, and I'm going to write to them after this and say, hey, write a D blog. Absolutely.
All right, I think that's it. Give it up for Mike.
All right, thank you. Thank you.
All right, we've got time for a, 10 or so minute break before our last talk before lunch, a first-time DConf talker. Woo! All right, so go have fun. Hello downstairs, can you hear me? This is the voice of your D language gods. Get upstairs. I hope they heard that. Oh, Bruce is coming out, but I think it worked. It looks like it's working. Oh, I got to pull out the voice of the D-Lane gods a few more times this conference then. That's great. How are we all doing? How are you enjoying the conference so far? Yeah, this is our fourth time at this venue, yeah? I think so. We came back from Corona. We missed 2020 and 2021, so it was 22 here, 23, the year of the great laptop heists. Your laptops are going to be good this year, unless Ian shows up, and then all bets are off. So, all right, let's kick this off. Like I was saying, we have a first-time DConf speaker. He's talking about my favorite subject, game development. So please take it away, Lewis.
Sweet. Thank you so much for the warm welcome. I'm Lewis. I'm here to talk to you about the 3D game and engine that I built with D over the last 5 years or so. Yeah, so that's me. I'm Lewis. I'm a video game programmer specializing in rendering. I've been working in AAA worked for about 5 years. At kind of a bunch of studios in the Vancouver area, Capcom, EA, and Relic. And more recently, I've been specializing in rendering, which is why I tried to build a 3D renderer from scratch. I would never have attempted that otherwise. I've worked on a handful of games that you may or may not have heard of. Yeah, so the last 5 years has been just me as a solo developer working on a indie game called The Art of Reflection, which is basically a 3D puzzle game. If you've ever played Portal or Viewfinder or games like that, it's kind of in the same vein. Take something interesting or weird about space or time or some concept of the world around us and bend it in some way and see what happens if you make that the new reality, and then build a bunch of puzzles to kind of explore the different parts of that. And that's what this game is. So in my game, it's what would happen if you can just pass seamlessly through a mirror. Let's take a look now, and if the live demo gods are smiling upon us, I think we might be able to actually run around here. Yeah, there we go, perfect. All right. So this is the game. You can just kind of imagine the sound effects in your head, just make like swishy, whooshy noises and stuff as things happen, footsteps and whatnot. So it kind of looks like a regular first-person thing. The main mechanic in here is that you can at any point kind of zoom in like this and find one of these totems and then press a button and you will teleport to the totem. Doing this kind of like, if you have a film background, you know what a dolly zoom is. I'm doing a dolly zoom in order to teleport you, which is basically correcting the field of view and moving you at the same time to hold a subject constant. And the crux of the whole thing is that, let's run over here, this dolly zoom works in mirrors. So if I zoom in on this thing in here, I just went right through a mirror. Same with over here. Whoop, it all works. These mirrors are like, totally dynamic things. You can pick them up, rotate them around, find another thing, go through it, whoop, you go right through the mirror like that. You might be wondering, wait a second, doesn't that make things like become forwards or backwards or flipped? And the answer is yes. So like this, you just saw me do it. This text is forward here, and of course it's backwards in the mirror. And then when you go through the mirror, it's now backwards, and that's just like the world that you're in now. Okay. It's like the basic mechanic of the game. I don't know if it's applause-worthy. If you put two mirrors against each other, you get these like kind of long infinite reflections like this, kind of like happens with real mirrors. And of course, this sort of zooming stuff works with those. It's a little disorienting once you start to do more. Let's stress test this laptop here and do some like gnarly stuff. Let's kind of get a bunch of mirrors really close to each other so you get a nice hollow mirrors effect. And this should bring the laptop to its knees if I do this right, which is good fun to do in the middle of a live demo. But there we go. Oh yeah, look at that. But you can see the frame rate taking a little bit of a dip, but like it's broadly working. Again, you can just like pick any one of these and kind of go whoop like that, and pull it out and see what we were dealing with. It was just a bunch of mirrors facing each other. I kind of explore this sort of mechanic in a whole bunch of weird ways in the game. Let's see how well I know how to play my own video game here. If I go up into this area here and drop down over here, so if you have a mirror, see I'm adding my own sound effects. if you have a mirror in the floor here, you can see that it kind of like reflects, everything gets reflected vertically instead. And so that's what I do with gravity. So it looks like this box would be upside down here. And so if I pass through this, now that upside down box means I'm falling towards the ceiling, and I'm now on the ceiling. And there's that box, where is it? Way up there. And I can spot it down here in the mirror, and I'll go through this mirror. And now I'm falling back towards the floor again. And so I use this sort of thing to just explore all sorts of weird stuff with the mirrors. As always, with infinite looping mirrors, it kind of just works like that. Anyways, that's the game. I do a whole bunch of puzzles and kind of in-world and out-of-world, or in like puzzle chambers, kind of like Portal, but then also just like integrated into the world. Some other stuff with just a variety of puzzles throughout the game. All right. OK, so now let's talk about, OK, sorry, 1 second. I need to give this focus. There we go. How I did it and why I chose D for this project. So at the very start of this project, I had a bunch of technical goals. Basically, I needed to support this kind of central mechanic that I'd envisioned, and I needed to make sure that I could get it to work properly, and that I could get like the detailed graphics work to work properly. Like when I first implemented the passing through the mirrors, there were like 8 or 9 separate bugs that caused like a flicker or a hitch the moment that you pass through a mirror. And I needed that to not be the case. It needed to be totally seamless. So I needed something that would give me the control to be able to do that. I needed to support lots of mirrors and lots of reflections. It couldn't be an edge case to have a mirror on the screen. It had to be just like constantly OK. And I needed to be able to drop 5, 6, 7 mirrors into a level and not worry about performance. I needed to hit 60 FPS because that's the gold standard in video games. And I wanted to support reasonably old machines. This laptop is, I got it used in 2020. It's like a GTX 1080. So it's not like a top of the line graphics card or anything. And it's running this decently well at 1080p. I've gotten reports from other people that it seems to work pretty well on Steam Deck or on other like somewhat lower end machines, which was one of my goals. In terms of process, one of the big things that I came away from AAA, I learned a lot in my time in AAA, and it was a really good experience learned a lot from a lot of really smart people. One of the things that I came away with was that a slow iteration time really sucks. Like sometimes it was as bad as like 25, 30 minutes for a recompile on some of the really big projects, and that is really bad for your ability to get stuff done. And also just your happiness on a project. And so I wanted to come into my own project being like, OK, I'm shedding everything. I'm building all my own stuff from scratch. I'm going to make sure that iteration time is this pillar that I am not going to sacrifice on. And so that was a really big goal for me. I'm one person doing this, trying to build a kind of complicated thing. And so I need to do the simplest possible thing that I can at every step of the way to just be able to move on to the next task. I'm not trying to build a general purpose engine. I'm not trying to support every possible variation of this game or any game. I'm building the code that supports this game and this engine, full stop. I needed to make sure that I could dive in and fix or customize things as I need to. It's just been my experience developing like projects that are going out to an end user, is that like I need to make sure that I can have enough control, because like the buck kind of stops with me. Like if like there's a bug in the project, I can blame some library I used or whatever, but like that doesn't work for the customer or for the person who paid for my game. I have to be able to say like, nope, I've got it, I'll fix this. And so I need to give myself control technically to be able to do that. And then finally, this I've worked on this project for almost 5 years now, and I want tooling and stuff that I'm going to be happy using. And I don't want if I'm not going to be happy with it for 5 years, then that sucks. That's a bad sacrifice. As for why I chose D for this project, I mean, I had the very rare opportunity to get to start from scratch, which is why I was able to even make this choice at all. Usually you're stuck with old like legacy C++ code and you're just building on top of that. A lot of the stuff I wrote here is like were things in my that I was considering as I did this, but they're all the stuff you're familiar with, so I won't waste time on them. Just kind of all the features of the language that you all know and love at this point. I want to highlight a couple that you probably also know, but are not as that aren't always talked about as much. The blisteringly fast compile time of DMD, as Walter was talking about earlier, is one of the key things that it was a huge selling point for me when I was choosing D, because it fed into the iteration time thing that I was really trying to prioritize. The fact that D is a mature language that's been around the block and it's gone through a lot of revisions, a lot of iteration, a lot of stabilization and bug fixing and robustness passes was huge for me. And then it also means that it's got lots of libraries that have been built against it, which was something I needed because I'm not building literally every single thing from scratch. I'm using all sorts of middleware and other game libraries and things like that to make this work. And just the flexibility of D was a huge selling point to me as well. Just like knowing that I could kind of like go ahead with the project fearlessly and not have to worry about like getting backed into a corner by the language. I had a lot of confidence from my early experimentation with the language that if I needed to get something done, D would let me do it. If I needed to do raw pointer arithmetic somewhere, I could do it. If I needed to circumvent the garbage collector, I could do it. If I needed to drop into assembly, I could do it. And so like whatever I needed to do, the language was going to let me do that. And then interop with C and C++ is mandatory, just because of all the different libraries that we use. So the way that I've ended up kind of like landing on using D for this particular project is just really like keeping it really, really simple. I do a lot of plain functions and structs and just like a relatively C-like way of writing things, just hopefully a little bit less error prone thanks to the nice features of D and the stuff that it lets me do. But really, really straightforward. I do basically no exception handling with very few exceptions, very few classes, honestly, which is kind of wild for some people to hear, I've learned. But just like a lot of really plain structs with very simple, like maybe one level of inheritance hierarchy or like, you know, like a struct within a struct or something like that. But just trying to keep my data layout and stuff really, really simple. I use templates, compile time, function execution, and traits because they're super useful features, but I use them very judiciously, mostly because I don't want to run the risk of bloating my compile time, so I'm always paying attention and making sure I'm not accidentally doing something that's going to make the compile time go up. And also just because it's easy to accidentally, particularly with my relative noviceness with that sort of code, easy to write something that's like really complicated and really hard to read or debug. And so just like where I can keep things simple, it's good. But then there's just like some features where CTFE and templates and such are just so profoundly useful and let me do something so quickly or so ergonomically that like I can't ignore them. They're such useful features. Basic structure of the engine, I'll just kind of skim over it because it's not all that important. But basically, the game is a bunch of global systems. Again, this will make object-oriented folks spin, you know, like wince, but that's fine. This is the way that I ended up doing it, and it ended up working very ergonomically for me. Basically, each system gets data, which allocated however that system wants. It can be in the garbage collector, it can be not. I'll go over memory in a little second. They opt into game-wide functions like update, draw, and handle events. So say the entity manager can run entity manager to update when everybody is updating. They just opt into those. They present a public interface to all the other systems who want to use them for something. And the systems call into other systems freely, and they're all global, so they just make global function calls. There's really nothing to it. I don't use event systems or registering for callbacks or observer patterns or anything like that. It's really just like the system calls into the other system. Big advantage of this is that I can see very clearly when I am doing something I shouldn't be doing. So if the physics system is like telling the music box system to do something, I'm like, wait a second, that dependency is sort of not a great idea. And I see it very clearly in my code because I will, in the music box system, see, like physics system dot send it some information or whatever. And I'm like, wait, that shouldn't be there. So it's really easy to just see at a glance where the connections are. I talk a lot and fast, and so I need a lot of water. So in terms of memory management, the GC is something that comes up a lot in games as a worry that people have about being able to ship a game with a garbage collected language. The way that I ended up settling on this was that I used the garbage collector basically for like static global, not quite static, but like global and permanent memory. So I do a lot of garbage collection like garbage collector allocations right at the start and just kind of like pile a whole bunch of things in right at startup for the game and allocate a whole bunch of memory. And then I really don't touch a lot of it for a long time. So it turns out that in games, there's a lot that you load at the start and then you just kind of leave it all loaded there. And so that's basically how I landed on it. I allow myself to freely use the garbage collector for startup code, for debug, and for tools. My level editor and like material editor and other stuff like that is all built into the same executable. And so they're all in there just like behind debug guards. And so for all that code, I freely use the garbage collector because I don't care about a hitch. It's fine. And then in regular gameplay, I forbid that sort of GC churn, and I force myself to use a couple of simple structures that I've used or just like other means of allocating things that won't run into problems. I don't really use no GC very much, mostly because it's very restrictive. It totally makes sense for applications where you need like a really hard line that there is no GC usage and something. And it turns out, kind of to my surprise as building this is that I actually don't have as hard a line on that as I thought. Like, it's okay if I have a really occasional allocation or like a random edge case or like one hitch every 3 minutes of gameplay. It's like honestly fine. You can ship a game with that. I just can't have garbage collector churn. Like, I can't be using the garbage collector every frame to do stuff. And so no GC ended up being like, it was a very restrictive line. So like, for example, you can't index into an AA with no GC active, as far as I'm aware, and I was testing at least even with DIP 1008. And so that is more restrictive than I needed. So what I ended up doing instead was just added some debug printing. And there's already some stuff in the GC there for that. And so I just added debug printing so that at runtime, I can run around the game with this turned on and just look and see like, oh, is anything popping up? And if I'm seeing anything popping up, I go find the source, fix it, I make sure that it's not running at runtime, and then I kind of leave the rest. And that it worked pretty well for me in terms of just like getting garbage collection out of the main like second-to-second runtime of the game. So I'll go over a couple fun features here that I kind of built into this engine. This was one that was kind of like the first really big example to me of like where D is shining and is like helping me build stuff really fast. This was a thing that I kind of built on a whim to just be able to look inside the game state, which is the master struct that has a bunch of substructs in it for each system that is like all of the data that is live in the game at any time. It's like organized by system. And so what you can see going on here is that I'm just like poking into different systems and just like editing the values because all I needed to do here was write, it ended up being about 300 lines of kind of like traits code, basically, to generate this UI using ImGUI. And then I suddenly have access to everything here. If I add something to the game state, it's added to this UI. And I can just like change or view all sorts of stuff at runtime. So I barely need to like use logging anymore to monitor stuff that's happening at runtime. I just literally open the game state inspector and just take a look at the values as they're changing and can like run around the game and watch, okay, when I press pause, does the pause checkbox appear? Okay, yes, it does. And if I want to unpause, I can literally click that checkbox and the game unpauses. And it all just kind of works. Like none of the stuff that I'm doing in here were features that I wrote to be able to add a scrubber for the physics time or add a pause checkbox here. This is just naturally emerges from building this like 300 lines of code basically. And this was huge. Like this was the sort of thing that made me go like, all right, this is why I chose this language, and this is like what I am getting, because I'm paying a small cost, doing things a little bit differently than the industry standard, but this is what I'm getting in return, and it's huge. And it kind of represents like this sort of confluence of features almost. Namely, it's like a really, really good showcase of the D introspection and how easy it was for me to write this. It was like half an afternoon, I think, to get this all working. It was super fast. And ImGUI, which allows you to have this like really scrappy like one-liner UI like this, which lends itself really well to this sort of thing. And then code hot swapping, so like I can hot swap in if I'm adding or changing a few things in the state. As long as they're simple enough that they don't break the hot swapping, I can hot swap in new things and they'll show up in this editor, which is great. The scrap heap is a linear temporary allocator that I wrote. That's a really common technique that people use both in games and out of games, where you just build this like allocator that just bumps a pointer, and then whenever you realize you're done, you just set the pointer back to the bottom and erase everything. And it turns out the frame boundary in a game is a really great place to do this. And so just like you generate all sorts of like scrap memory during a frame, and then just at the end of the frame, you reset it all. And as long as whoever's using it was careful to make sure that nothing needs to outlive this frame, you're good to go. And you can just allocate all sorts of stuff and do lots of really ergonomic processing in this way, the way that you might normally with a GC and feel like you're forbidden from doing it in a game, but because of this, you can do it in a game. I ended up, I feel like maybe the slightly notable part is that you can see the way that I've set up this mix in here. I basically ended up doing this sort of scoped-based thing, where I added a little bit of a hack into the GC proxy, which is internal inside the runtime, to let me kind of store the current allocator, whether it's the scrap heap or the GC or something else. And then I can just make this one call, and it switches to a different allocator. I do whatever I'm doing, and then it switches back at the end of the function, which was super easy. Or like it helped me a lot for if I had like runtime code where I was like, this can't use the garbage collector because it will allocate. Sometimes I could just like drop this one-liner in, and suddenly it's using the scrap heap. And because it's all temporary, it's fine, no problem. Hot swapping. Okay, so I mean, in this demo, I think what I do here is I comment out the entire section of code that does the transparent render, and then once it recompiles, the glass disappears and the particles disappear because they're part of the transparent render. And so I have hot swapping in this game. I'm using the DLL approach where you put 99% of your game and engine basically inside a DLL, and your executable is just a super thin layer that basically lives to load the DLL, call a single function on it called game update and render over and over and over and over again in a loop. And then anytime it detects that a new DLL has been compiled, it unloads the current one, grabs the new one, loads the new one, and starts calling game update and render on that new one. And that's the way that hot swapping works. I won't go into too much detail. There's lots of stuff on how you can do this in, say, C++ already out there on the internet. I'll go into some of the D-specific parts of it that I had to figure out. One of the things to be aware of with this approach is DLL statics. Obviously, when you hot swap a DLL, or you're hot swapping and you're changing out the DLL, things can shift around. So if, say, you had a string constant and you were holding a pointer or a slice to that string constant, right there in the DLL, that could move, and that will invalidate things and cause you all sorts of headaches. And so the solution that I do is the gnarliest, nastiest solution I could possibly think of. I call .dupe on all DLL statics. Literally, I just run through my entire game state, again, with traits kind of style code. And I find everything that looks like it could be a string constant or a DLL or some sort of static or an array that was constant, and I call .dupe on it. If you're thinking to yourself, that sounds super wasteful and slow, you're right. But hot swapping is a debug feature, so I kind of don't care. All of the hot swapping is compiled out in release. The whole thing is just one executable in release. The hot swapping is all a debug feature for my own iteration and my own work. And so it ends up being 0.2 seconds or so to duplicate all this stuff, and a little bit of kludgy code is actually not that bad. And this, in my experience, works very stably, despite it being kind of messy and imprecise. Considerations with D runtime. At least when I was messing around, I've heard rumblings that there might be alternatives to this or work in place, or maybe LDC behaves differently on this regard. And I'd love to chat with some people about this because I feel like there's probably better ways that I could be doing some of this. But in what I was reading about or experimenting with, it seems like when you build a DLL in D, it gets its own version of the D runtime, which means I have 2 D runtimes, which is not ideal because that means 2 garbage collectors, 2 sets of internal understanding of what my live threads are and stuff like that. And really, this whole thing is basically acting like one executable. But the solution is pretty straightforward. Again, because this is debug, I can get away with slightly hacky things. And so all I do is I basically I have a bunch of function pointers that get filled out by the executable that are the calls to things that I want for the DLL to be piping back over to the executable, so that I can have the DLL stuff, which is 99% of the game's code, use the same D runtime as the executable is, and that way everyone is using the same D runtime. Everybody is happy. There's a bogus garbage collector that is sitting unused over in the DLL, and that's fine. It's slightly wasteful or a little weird, but again, it totally works and lets the hot swapping continue. And that, I only needed to do it with it's 8 or 9 function calls. It's some basic threading stuff. The GC, and the GC is actually really convenient because it already has the GC proxy built into D runtime, and so I just use that proxy to pipe stuff over. And a couple of other things. And then everything is using the same stuff, and there's no problem. Classes, because vtable, I don't use that many classes to begin with, so I actually only implemented this year 4 into the project when I finally was okay, there's a couple spots a class would be really useful. And vtables and class info sit in the DLL statics. And so because they're in the data section of the DLL, and because they're in there, when I hot swap a DLL, they might shift or move, and that's a problem because your vtable pointer inside of a class might be now pointing to trash, and so I need to deal with that. And so the solution that I ended up with was manually registering the small number of classes that I use with kind of a little templated thing that basically manually does a patch up when it gets created to point to an alternate version of the vtable. So basically what I do for that is I have the data section of the DLL, which has all the vtables in it. I copy those off into a separate storage that is stable and will outlive a hot swap. The vtable pointer for a class by default points into the data section. When it instantiates, I change it so it now points into my vtable storage, the copy that I made. when I hot swap, the DLL data section goes either like gets all mixed up or moved or is invalidated basically. And so it's fine though, because I'm pointing at the known good version inside the vtable storage. And then on top of that, even if I made a change to say that class in the hot swap that would affect the vtable, I copy everything over again on hot swap, but to the correct location that is fixed in memory. And so because of that, it gets all of the new information in the right location and is already pointing to the right place, and I don't need to worry about trying to find the new place. And classes then work with hot swapping. All right, into the kind of the gnarlier, kind of more detailed stuff about like the renderer itself and the stuff that I had to do to get the game itself working. So the renderer is broken into basically, like the mirror rendering in general is broken into 3 steps. Step 1 is pre-draw, which is basically like do the preparation work to figure out like what do we actually need to draw here. And so what it does is it figures out all of the mirrors you can see from the main scene, and then all of the mirrors each one of those mirrors can see, and so on and so forth. And it basically builds a hierarchy out of that. I'll show you what I mean. Basically, like you can see, there's like the main view, and you can see some mirrors, and then mirrors within those. And so the top level mirrors are the first node, the first level of children in the tree, and then each of the children within those mirrors is the next level of children, and so on and so forth, kind of going down the line there. And so you end up building this tree. And in order to render this, we walk this tree depth first and kind of linearize that order. And that is the order in which we need to render things. The other thing, nice thing about kind of visualizing this or thinking about this, the rendering needs of these like recursive mirrors as a tree, is that you can think about things like pruning off branches of the tree. So like really, like one of the things that I do very aggressively in this stage is I try to figure out, can I really see that mirror from here? And if I can deduce that the answer is no, I can like carve out entire branches from this tree and save myself a whole bunch of rendering time. Because each one of these mirrors not only renders a bunch of objects you can see in it, but also renders other mirrors, which in turn renders other objects. So any pruning I can do here early is a huge savings. I'll note, I might even do this accidentally, mirrors and portals are almost identical to implement. My internal renderer, or like main file for this, is actually called the portal renderer, and literally every portal instance I have has a bool on it that's just is mirror, because it's so, like they're so similar. Like you can basically think of if you imagine like an entrance portal and an exit portal, kind of like in the game, if you take those, put them on top of each other and kind of like flip it around and then do like a swap along X, you have now turned your 2 portals into a mirror. And so they're like really basically the same thing. And so I support both of them in the game. And like kind of almost hilariously, I use portals, but not for puzzles, just for like moving between different worlds. I've had someone describe that to me as like a flex, that you have portals in the game and you just don't use them for any puzzles. But I'm like, yeah, no, the game's about mirrors. We'll do that. The second phase of the mirror rendering is the parallel call. And so this is like, okay, we've got all these mirrors, and they each need to figure out what you can see in them. And that process broadly in rendering is called culling, which is basically saying, okay, there's a list of all of these objects that I know about. What can I see within those, or what are we going to actually be able to see? What do we actually need to render here? And you basically take your view and you like ignore objects that are outside of the view. And this process is one of the only times in the render, generally in a game, where you have to touch every single object that's in the game. You go through every single one of them, you check them against what you can see, and you eliminate the ones that you can't. And then from that point onward, you only care about the ones that you can see. So it's usually, this is a really, really, really tight, highly optimized loop in general in a game, because you have to touch so many objects every frame. And so I have to do that for each mirror that I can see, because each mirror has its own separate visibility list of what I can see. If you imagine I stand here, I see all the things in front of me, but if there's a mirror here, that mirror sees things behind me. So I need to have separate lists for those. And so I run, basically I end up like for each node in that mirror tree, I end up with a separate job that I have to do this culling. And I run those all in parallel. Basically, I break up those work and I run them all at the same time because they're completely independent pieces of work. And they all run through the entire entity list and figure out what you can see. The other optimization that I do here is that for a mirror, what ends up working out really nicely is that if you imagine like a mirror, like if I'm thinking of that laptop screen as like a mirror I can see from here, my view might be this, but in reality, what I can see through the mirror is that. It's a really, really narrow field of view. And so what I do is I basically like take my field of view and narrow it to the bounds of each mirror. I did not invent this technique. I think this was invented for Portal. But this ends up being a massive savings. This was like the difference between having like 3 to 5 mirrors on screen and having like 100 at once. This one optimization, because it just cuts out so many objects that you would otherwise need to render. The final stage is the stage where we actually make the draw calls and actually render everything out. So basically what I do is I take the mirror hierarchy, as I mentioned before, I run it in depth first order and kind of like run it for a little while and then stop and call that like a chunk of work and then send that off to a thread. And I have all these threads that run this kind of drawing work in parallel. And I do some like very, very coarse load balancing to try to roughly estimate how long each chunk of work is going to take so that they can all finish close enough to the same time. And we basically go off into another thread, do all of the work to like switch our view into whatever the current mirror's mode is, put our camera in the right place, do some stencil buffer and depth buffer shenanigans to like say, okay, you're only drawing within this little window in the screen, and then render all the objects, and then move down to the next level of portals and so on, or portals or mirrors. Yeah, and I break this all up and issue these draw call, or not issue them. I build the command lists for these draw calls, basically like prepare the drawing work for the GPU, all in parallel. And then at the very end, they send their work when it's done back to the main thread, who then submits them to the GPU in the correct order. Not in the order they came in, of course, because who knows what order they come in, depends how fast the threads run, but in the correct order to render the scene properly. There's probably a whole bunch of stuff that I could do to do this even better. And I just, at some point, was like, it got good enough that I could ship the game on it. So my principle of keeping things simple, this is the most complicated part of my code base by far. And so at some point, I was just like, all right, I'm done with the tech stuff. Let's start shipping this game now. So like one possible thing that I could probably do is occlusion culling, which basically means if there's a big object like a wall in front of me, you don't need to render anything behind the wall. And so I don't do that in this game right now. So like if you're staring in front of a giant mirror like that, I am both rendering all of the things you see in that mirror that are behind you, and also everything behind that mirror, and then it's just getting wasted because the mirror is in front. And it turns out to be still fast enough, even with that, that I'm not running into too many problems. And so you could probably implement that and get some pretty good savings. I don't do that sort of thing right now. The work that I do right now to try to prune levels, like figure out, can you see a mirror at a particular place on the screen? That work is coarse. It's like a CPU side approximation of what the GPU would actually do to figure out where everything is and figure out whether you can actually see a mirror or not. And it's kind of, I basically like do some geometry with an oriented bounding box and the scissor rect and some other stuff and compare them against each other. Really the closer thing to the ground truth would be to like pretend rasterize these mirrors to a really low resolution texture, just to see how they overlap and what pixels end up getting like flicked on basically for every mirror. And if any given mirror affected no pixels, then you know I don't need to draw this or any of its children. And that's like the perfect test, and that's what actually gets done on the GPU side. When you are rendering stuff in order to do it correctly. But if I did it on the CPU side, I could save the GPU from doing all this wasted work. But I don't, and it's still fast enough. One thing that you could do is you could move the culling and the mirror pruning to the GPU. I've heard of people doing GPU side culling in AAA games, where all of that work to figure out what you can actually see happens on the GPU, where you can then, there's a lot of stuff that you can do more easily when it's over on that side. For example, you could, when you're making your decisions about what you can see, you can leverage information like what's in the stencil buffer very easily from over in the GPU, whereas over on the CPU, you have to get information back from the GPU, and that is really slow. You have to stall the whole GPU, send your information back, and then start sending commands to it again. And that is super duper slow, and so I don't do it. But if you did everything on the GPU, you could probably bypass that. And it would probably be a huge savings. And again, didn't do it because at some point I was like, it's been 5 years, I need to ship this video game. Yeah. So, okay, the actual effect of passing through a mirror, this was like the kind of the most fun thing for me to discover, because I had no idea if this would work when I started. I just played around with it a bunch. So here you can see, like, this is what it looks like from first person when you go through. It should look totally seamless. Like, there should be no bridge. But if you watch that kind of yellow box there, and it bounces there right in an instant, that's what's actually happening behind the scenes. This thing where one of the balls lights up and then the other, that's not something I implemented for this visualization. That's actually what's happening right there. Because the way that passing through the mirrors works is that you fly towards the mirror, and then there's some point when your face is right in a mirror here that this image and this image are exactly the same. And in that moment, I instantaneously snap your head around and then keep you going out the other side. And you basically bounce off of it like a ray of light. And that is how the effect works. There's no two copies of the world. There's no alternate mirrored dimension. It's all the same world. It's just like a visual trick to make it look smooth as you go through the mirrors. There are a couple things that you have to do, of course, right at the mirror surface, and I've discovered all of these kind of organically because, as I said before, there were like 8 or 9 separate bugs that were like, okay, this works, but there's a black flash the moment you go, or there's like a weird depth discontinuity, or an object disappears and reappears the moment you flip your view around. So there were a bunch of things I had to fix. The first thing that you need to do the moment that you bounce off of the mirrors, you have to flip the whole screen horizontally, because of course mirror image is flipped. And so I do that with just adding a little negative number to the projection matrix to make every pixel go to the other side of the screen, basically, which flips the image horizontally. When you do that, you then have to fix a bunch of other things. So for example, if you flip the image like this, your controls are now backwards. Left is right and right is left. So I have to invert your controls. When you do that, also any audio sources that are positional, so they sound like they're coming from over there, you'll now see that thing over there. And so I have to flip the audio sources to sound like they're coming from the same place that you see them. Like it all basically, once I flip things, I just have to synchronize everything back up to the way that you'd expect it when everything's been flipped. And then more 3D rendering specific, I have to swap the winding order, because when you flip the image like this, you take every triangle that is its vertices are set up clockwise, and you now make them counterclockwise, which in D3D parlance tells it to render. D3D uses this, and most real-time renderers use this to determine whether you're looking at the front of a triangle and a back, and most of the time we just don't render the back, we only render the front of a triangle. So that means every object would then become basically inside out, which was really hilarious the first time I discovered it. And then basically I have to tell D3D the moment that you pass through a mirror, flip the winding order for everything, and then flip it back, and so on. And I do the same when you're looking inside of mirror views. It has to flip them. There's this big if statement that basically flips back and forth between mirrored or not mirrored based on where am I? Am I in mirrored mode? Am I looking at a mirrored thing? Is it a mirrored or unmirrored object inside that? And it just flips the bool back and forth the right number of times to land on, okay, yeah, you need this winding order. I did not build, well, I said that I built this engine from scratch. I didn't use a pre-built engine. I did use a lot of other code that already existed out there. So I used lots of middleware, lots of open source libraries, and a whole bunch of stuff that was already written for me in D. So lots of bindings and kind of other little libraries and stuff that were incredibly useful in just being able to get stuff off the ground without having to re-implement entire libraries myself. I wrote my own bindings for a couple of libraries that I wasn't able to find ones for in D. I have not contributed those back yet, but that's on my to-do list the moment I ship this game. Is because some of them are a little hacky right now. I want to polish those up and then toss them out on GitHub or something, or in Dub, just so that, because having a binding to the Steamworks API or DirectX text or things could be probably useful for people making games. They were useful for me, and so I'd love to be able to contribute that back, specifically given the amount of other people's code and knowledge and prior work I built on in order to make this game. It's the least I can do. So kind of looking more broadly at my experience in using D for making a video game, it worked out basically the way that my initial kind of technical inspection led me to believe. The iteration time was great. I think it grew from 0.5 seconds when I was starting with a tiny code base to it's 5.5 seconds now or something to compile the entire game and engine. And so that's my goal was keep it under 10 seconds, and it has been able to maintain that goal very easily. All of the kind of modern features and a better standard library were good. I want to call out as well that the fact that the standard library in D and D runtime are readable code was huge. So if there were times where I didn't understand how something was working, I literally just found the source file, opened up the source file, and read it, and I could understand what was happening. That was not my experience with parts of the C++ standard library when I worked in industry. I don't know if any of you have looked at Microsoft's implementation of an STL vector or even a unique pointer. They're wild. They're thousands of lines of code for something that should be 50. And so it was really nice to be able to just like really easily understand stuff because it was kind of written sanely. You know, as I was expecting, like D was flexible and capable, and it proved out that I was able to get it to do what I needed to do in the times where I needed to do something very specific. It was like, yep, go for it. And it was exactly what I had hoped for. Fixed C++ baloney, you're all familiar with that. The interop to C and C++ libraries was magnificent. It worked great. And I was able to like make, even when bindings didn't exist, I was able to write them relatively straightforwardly for most things. I'll go over a couple exceptions to that in the next slide. But it broadly worked really, really well. I also want to call out that like D has really good Windows support. And this isn't always the case with open source projects. And I totally understand why. But for me, stuck here in gaming, like we build everything basically on Windows because 98% of our user base uses Windows for games. And so we're stuck using Windows for better or for worse. So having a language that has good support is huge.
I wanted to expand on something when you talked about the incomprehensibility of the implementation of the standard library.
Yeah.
Well, I originally looked at Silicon Graphics implementation of the C++ standard library when I did the original C++ compiler years ago, and I never did figure out how it worked. And you know, I just compiled it and prayed that it would work, and it did. But that was one of the motivating things for creating D is every time I looked at implementations of library code, it was always incomprehensible. And I thought, this is crazy. There's got to be a better way to do this. So, yeah, you've noticed the same thing.
Yep, exactly. Yeah. Yeah, it was huge. And then the ability for D to drop me into to let me do low-level access or write a tiny little bit of assembly or do SymD work or whatever else I needed to do, or just like do some really bizarre Windows API call that I need to get the DPI set correctly for the screen or all sorts of weird stuff like that. Like, it was just really easy for me to trust that D would let me drop in and do whatever I needed to do wherever it was, including in a couple of spots make tiny little hacks or modifications to D runtime itself to support things like my weird hacky hot swapping implementation and stuff like that. Overall, super glad with the decision. Like, no regrets whatsoever. Things that these are the things that I'd love to chat with people here because I kind of learned a bunch about D as I was experimenting with it, and then kind of went into a hole to build the game. And I feel like there's stuff that's probably been either fixed since or improved since, or just I just missed that D supports a particular thing. And so I'd love to chat with people because I feel like there's probably better ways than some of the stuff that I did. I ran into broadly the fact that C++ name mangling and stuff is supported by DMD was huge, or by D was huge, and was really, really helpful for binding to C++ stuff. There were a couple of really gnarly C++ libraries. PhysX in particular does not have a C API and uses inheritance directly in the classes that it exposes to the user. And so I basically had to build D-side versions of those classes and had to get the vtables to line up with the C++ side, which meant sometimes inserting a dummy function for to cover the virtual destructor or something else that D didn't need but C++ had on their end. I don't know of what the solution is to that. It wasn't actually that hard to figure out, but it's a little gnarly to be lining up vtables and stuff as a regular way of setting up C++ interoperability. But it's also PhysX gave no accommodations whatsoever. So it's a kind of I think at least a hard problem. There's not a good solution to that I know of. Ecosystem size, everyone knows, it's always tough where every now and then I have to roll my own binding or something. That's hard. The only solution, get more people using D, which is part of why I'm up on this stage. I mentioned before the kind of DLL hackery that I had to do for supporting, for doing the hot swapping. And I'm left wondering, I was able to get it working, which was great. I mean, I'm left wondering whether there's a cleaner approach than what I ended up doing. And again, I would love to chat with people here if anyone knows of easier ways to do this or ways that are better supported, because that would be super useful and would let me clean up a bunch of my hacked code. And then every once in a while, I'd run into something broadly, debugger support was really good, and just worked as is in Visual Studio, which is what I was using to debug. Every now and then I'd run into like a weird thing, like often thread local storage variables didn't show up in the debugger and I couldn't get them to show up in watch windows. And there's like a couple other weird bits where it would like step over way more code than I thought when I was stepping. And just like the occasional bit of weirdness, but like none of it was deal breakers. All of it was stuff. And like honestly, when I remember debugging stuff in industry and C++, there was weird debugger behavior there too. There was definitely like times I remember where it's like showing me full on the wrong like data, but the wrong data in a watch window, and I'm like looking in the memory view, and I'm like, no, I don't know where you got that from, but like that's not right. Yeah, so my broad advice for using D for games is do it. It worked great for me. The few things that I was worried about, like the fact that it's a more unusual choice than C++ or the garbage collector and stuff, ended up being basically non-issues once I got into it, and it supported me really well in being able to build the game. Hopefully, the fact that I've been able to build a real thing that you can go play the demo now, and the game should ship later this year. That I was actually able to build a thing is hopefully evidence that this language is capable and mature enough for supporting this sort of work. I mean, everyone in this room already knows that, but for anyone else watching, hopefully this is another piece of evidence in favor of that. And then I talked about some weird hacks that I did. You don't have to do those hacks. Like you don't have to ship a game with DLL hot swapping, where you made a tiny little hack to D-runtime, or like built your own weird swap-in allocator thing. That's me doing me stuff to get things working in a very specific way. You don't have to do that. You can just do the plain stuff, and it'll be even simpler on you. That's it. Any questions?
I'm going to jump in first with a comment on that D runtime and a DLL thing, because that's something I raised in my talk on Quantum Break in 2016. It's been a while. We did have one guy working on it, but, classic open source community thing, he disappeared. So if anybody wants to pick up for that work, please do it. Attila.
You told us all the reasons why you picked D for this, but I was wondering how you even learned about D to be able to make that choice in the first place.
That's a great question. It was a while ago, and I'm not sure I exactly remember when I first learned about it. I know that early on, like before I left AAA, I was kind of examining. I knew I kind of wanted to roll my own thing. I actually originally thought it was going to be 2D, and then it ended up pivoting into 3D. But I was examining a few different languages at the time, because I was like, I'm frustrated enough with C++ working in industry. There's got to be something better that we've done in the last 40 years. And I think I just did like internet searches, or was like looking through Reddit or something. I don't exactly remember, and it just came up as one of the languages alongside like Jai, Odin, and a few others. And I did like kind of a brief look into each of those. I very strongly considered Jai for a while, but I was like, it's not out yet. I don't think I can wait for it. Sure enough, here we are 5 years later. It's still not public. So like, I guess that was the right decision. And yeah, no, D was the one that just stood out to me after looking through all of them as being like mature, something that I can reliably like build a foundation on top of, and has what I need to be able to ship the sort of thing I'm looking for.
Cool, thanks.
Relatively early in, you said that you're doing DLL hot swapping to reload for code reloading for fast iteration, presumably. And I was wondering, how does that stack up compared to just having very fast saving and loading?
Oh, good question. So the thing, one of the alternate approaches, kind of what you're calling out there. Correct me if I'm misunderstanding. Is that you can basically like dump your entire game state out to disk, and then when you boot the game and just load that state. That is an approach that can work. One of the downsides of that is that you also need to make sure that your game, you pay whatever your startup cost is in your game every time you boot it. And like you can optimize to get that fast, particularly in a game that's like, I'm not making Grand Theft Auto here. I'm making a pretty straightforward thing with like a total of a gigabyte of assets. Like it's very, very lightweight in general. But even with this, like, even if it's like 5, 6, 7 seconds to boot the game up, you pay that cost every time you do the save state hot swap. And then you also have to build the save state hot swap in that way, and figure out how you're going to serialize everything out to disk and back in. And I mean, to be fair, I don't think I fully like examined that as a possibility at the time I was doing this. I was just aware of this DLL technique for hot swapping and thought, that sounds neat, let's try it. And it ended up working. I think the save state thing could work. It sounds like there's probably a couple of costs in there. But like if your startup time is half a second, it might be totally viable.
You said you gave up on the no-GC attribute.
Yeah.
So did I. Are you aware of the -VGC switch, which lets the compiler, while it's compiling, print all the locations where GC allocations happen?
Yes, totally. I'm trying to remember whether, I think I didn't end up using that as much. But yes, that is a super useful tool to have. I think the thing that surprised me the most, I went into this with the usual game developer mindset that was very allergic to a garbage collector. That's just like, no, nowhere, anywhere near my code because runtime, blah, blah, blah. And what I came out with was I think a conclusion that a bunch of people in this room have come away with too, which is that you don't actually have to be that hard line even for games. You just need to broadly not be generating garbage, second to second. You can't be totally naive about how you do memory, but you can have the garbage collector be there and do some stuff and it's fine. And so what I ran into, VGC would print out all of the locations, and some of those locations would be in a function behind an if statement that only runs on startup or something. And so it would flag that location and that function, but I'm fine with it being there because it's only on startup. And so the tool that I ended up using mostly was just print for me actually at runtime when it happens. And then I go run around the world and be like, is anything coming up? Oh, that one, okay, fix that one. And then as long as it roughly looks good and I don't see any churn, I was happy enough with that, and it seemed to not be generating hitches in the game. So, yeah.
Right. Can I ask another question? When you look at something that makes noise in a mirror, the audio location, is it from within the mirror or still the original world position?
So in a mirror, I don't make audio emanate from something that you see in a mirror, because that's not how it works in real life either. But once you pass through a mirror and your view is flipped.
Yeah, so about that, I was wondering, doesn't that make a source just snap to the other ear? Is that jarring when you pass through a mirror and suddenly the location of audio flips?
Yes, so what ends up happening in practice, that's actually really funny. I never thought about that problem because I think now I'm thinking about it, I accidentally solved it. So the way that is solved is not in code, it's in design. When you do there were no sound effects because we don't have sound when I was demoing this, but when you do that teleport, there's actually this really loud blast that kind of happens. This sound effect that's it's just like a bang when you land, and that covers up any transitions that there are, right? And so if something was snapping over, you won't notice because it will be covered by that.
Hello? Oh, yeah. Great talk. Wasn't sure if we touched on the rendering side. Was this Direct 3D 12, and were you using any of the ray tracing API? And then the other follow-up was, I think I saw NVIDIA's Horizon-based ambient occlusion. Was that something you wrote a binding for as well?
Yeah, so this was all in vanilla D3D11. I used D3D12 when I worked in industry, and my experience with it was that it's a good API for what it sets out to do, and it's more complicated than I need for this game. Basically, I was confident that D3D has shipped games for decades, more than almost 2 decades now at this point, and I was like, okay, if it can handle those, I'm not going to be developing literally state-of-the-art rendering tech for this, so I can get away with D3D11 and it's simpler. And so that's what I ended up going with. And yeah, you probably caught it in the binding slide. I use NVIDIA's HBAO Plus or whatever, I can't remember exactly what they call it. And that one has a really, really clean interface, and they provide a C interface for it. So it was maybe an hour to get that bound and working in D, and it was really straightforward and worked great.
Awesome. Looks very beautiful. Thank you.
I have a question about the game state inspector.
Yeah.
Is there a registration mechanism, or you just display what you want to display?
What do you mean when you say registration?
Would your game state be usable for another project, or the game state is specialized for your game and it knows this game?
Gotcha. So, I mean, the game state, the structure itself is specialized for this game. There's some stuff that's probably common for a lot of games, a counter that's like how much time has elapsed, like every game needs that, and then a whole bunch of stuff that's specific. The game state inspector itself, though, should work pretty generally, I think, because it literally it iterates at compile time over the struct of the game state and goes through, like, every time it sees an int, it generates a little int spinner. Every time it sees a enum, it generates a dropdown with all the enum elements in it. And so that, I think, I've not tested it on a different game, but I think that should work without very much change in another game. There might be little bits of customization you want to do. So for example, I wrote a special 5 or 10 line thing for specifically dealing with entity IDs, which is my way of, like, keeping track of what entities are here. So it takes that entity ID and, like, does the lookup to give me an entity pointer so that I can then show the contents of the entity right there without me having to find the other place where that entity is located. That's custom for this game, but you could really easily, like, that sort of stuff I wrote in like 20 minutes, basically. You could very easily write that, I think, for a future game that maybe handled its entities differently or had some other weird custom thing it wanted to do.
Hey, great presentation. I'm pretty interested in how you built multi-threaded rendering with directed 3D11, because I'm more used to doing this with the state-of-the-art renderer, which I guess it's quite easier to do with another renderer.
Yeah. I mean, D3, D12, and D3, D11 are the only ones I have direct experience with. D3, D12 definitely has better support. It's like built more from the ground up for doing really, like, high performance, high intensity multi-threading work. D3, D11 just, like, supports kind of the basic version of it, but it turned out to be good enough for what I needed here. With D3, D11, with basically almost all the multi-threading I do, apart from the multi-threading I get for free from things like PhysX and Fmod, I do fork join for everything. So, like, I don't even have a separate render thread. I literally just, like, come up to the point where I render. I generate, like, the work that is needed. I go wide, I pound through that work, and then I go back together and I'm finished the render. And so basically just each one of those worker threads gets a deferred context in D3, D11 parlance, and records whatever work it needs to that deferred context. And then the deferred context is sent back over to the main thread, where it then gets submitted to the immediate context. And that's all there is to it. It's, like, relatively straightforward for the most part, but it's almost certainly not the most efficient thing I could do, but it was enough of a gain to be able to make things generally work. And so that's what I went with.
Yeah, so the game is awesome. I watched my son play it because I don't have a Windows PC, and I'm very jealous that I can't play it. Is there any kind of abstraction that you're doing with the low-level renderer that could possibly be ported to other platforms like Mac?
That is definitely one of the things that my list would love to do. I don't know, I can't guarantee whether I'll be able to get around to it, but it depends on kind of how well the game does and some other financial restrictions. But it's definitely something that I would love to do, just because the more people can play it, the better. I have, in terms of, like, rendering API abstractions, I have a really, really extremely simple version. Like, I do not have a very complicated rendering abstraction. I basically have all of the D3, D11 code that is specific to D3, D11 put in a separate folder. So there's, like, kind of a line between the two of them, so that if I wanted to swap that out with OpenGL or something like that, the hope is not that it would be seamless, but that it wouldn't be a massive headache. That's, like, kind of that's, like, honestly a design goal I've used in a lot of places, which is just, like, I'm not trying to make this perfectly interchangeable or perfectly common to everything, but as long as I make it so that it won't be a headache, it will just be normal work. If I have to do this in the future, then I'm fine with that, and I go ahead with it. And so, like, I directly make calls. I don't have my renderer in a DLL, so you could change out with an OpenGL DLL or anything like that. But hopefully there is enough of a boundary that I could, with not too much work, carve out that boundary and then re-implement with OpenGL. In the short term, I've heard that the game works well with Proton. So if on Linux, if that works for people, my plan is to, like, I have a Ubuntu dual boot on my computer at home, which I use to test every time I push out a new build. So I make sure that the Proton support is kept. So in the short term, that hopefully should work. But in longer term, I would love to port it to Mac and Linux and other platforms, ideally natively.
We've got 2 minutes left before midday, so if we got a really quick question, we can let it in. No? All right, I think we're done then. Thank you.
Thank you.
All right, so that means it is in fact lunchtime. We've got 1.5 hours scheduled for lunch. So eat, be merry, and then be back here without needing the loud Aussie to yell at you, and well, it might work out well for you. All right. Hey, is this actually? Yeah, all right, you can actually hear me. My voice is completely cactus, as you've heard. So I'm going to get off stage for the rest of the day, which means Razvan is taking over.
Hello.
It's his first time doing MC duties here, so be nice, applaud him, do all the things that the good audience does, like, say, DConf. There we go, you're all awake, perfect. So yeah, get the crowd going and then get them warmed up for Dennis here. Have good luck.
Thanks. So I just found out today that I have to, replace Ethan because of his voice. But fortunately, this afternoon we have veterans and well-seasoned speakers like Dennis here, who's gonna talk about saying no to save a language. So give it up for Dennis, please.
Hello, everyone. So today I'm going to talk about why adding features to the compiler is so hard. So the motivation for this talk starts with basically the origin story of D, where Walter created his C++ compiler, and he had his own ideas on how to improve that language. But the committee kept saying no to his proposal, so we still don't have slices in C, and there's still all these buffer overruns plaguing software. So he was like, OK, let's create my own language. He created D. And while it hasn't completely succeeded in completely supplanting C++, unfortunately, we're here, the D community is here. And naturally, we are opinionated programmers. We're not satisfied with the mainstream options, or we would just be coding C++ or Java. And when you have your own ideas, you also have your own ideas to improve the D programming language. And Walter tends to say no to a lot of them. He's given himself the nickname Dr. No, or maybe Mike was it who gave that nickname. And yeah, some people are upset with that, and so they start creating their own language. Here's 2 examples of those. Matthias, are you there? A neat language and sticks. So why is there this circle of life for programming languages? Can't Walter just say yes to all these proposals, instead of being a Dr. No, turning into a yes man? So I'm Dennis Gorpel. I've been pull request and issue manager for the D Language Foundation for about 3 years now. So I've been monitoring the issue list and fixing bugs, maintaining the compiler's code. And from my experience, I more and more want a small and stable programming language instead of a cutting-edge programming language which adds a bunch of features every week. So I'm also more and more inclined to say no to improvement proposals. And that's not a way to make friends. So I'm here to kind of explain my position, just give the perspective of why I'm so inclined to decline these proposals. So I'm going to divide this talk in 3 parts. First, I'm trying to explain, by delving into the compiler code, how features add complexity and why that's a problem. Then I'm going to make some tips, give tips to write better improvement proposals. And finally, I'm going to give some tips on how to refactor code to reduce technical debt, because that helps you, that allows you to then include new features to the language. So let's start with the first part. And I think D is currently too complex. There's too many features, and it makes it harder both for users to learn the language and for maintainers to fix all the bugs and implement new things. But how did it become this way? No one, like Walter, didn't set out to create a complex language. Well, there's this beautiful article by Alex Gaynor, which briefly explains how that happens. So simplicity tends to get dismissed. Features are naturally additive. I want something new to solve my problems while keeping all the existing behavior intact as to not disturb existing users. And so supporters of the new feature can claim concrete benefits, like how it solves their problem they currently have, while detractors have more abstract benefits, like saying, oh, this code won't be a maintenance burden, or the language gets less simple. that's kind of vague and easily dismissed. And whenever I bring it up, people think I'm exaggerating, like, oh, it's just 100 lines of code. How bad can it be? But the thing is, if you add just 1% to the size of something 100 times, you end up almost tripling the size. It's like exponential growth, maybe quadratic, I don't know exact mathematical curve fit, but it's more than linear, and it gets worse and worse. So now I'm going to, because it's still kind of vague, that exponential argument, I'm just going to show you firsthand how this complexity affects code maintainability. And but before that, I need to explain a bit about how the compiler is architected. So there are multiple stages in the compiler, and they're not equal. Parsing is the simplest one. It's by no means trivial. There's still improvements and research for better performance, better error messages, and occasionally there's bugs in there. But it's basically a solved problem. This doesn't stump development. Code generation is pretty complex, especially with modern optimizers. But it's usually outsourced to LLVM, GCC, or Walter Bright, who writes his own backend. And so like, they do their thing. And it's usually language agnostic, so it can be shared by multiple languages. So that leaves, it's only 100 lines of code in the DMD. That leaves semantic analysis, which is by far, which is like the complex part. This is where the heart of the D language is. This is the trouble spot for adding all these new features. But what is semantic? It's also the most unintuitive stage. When you're a new compiler contributor, you're often confused by what the code actually does. And I was like that. I had the same problem when I first started, but what helped me was writing my own expression parser and symbolic math expression simplifier. So if you have a basic expression here, like x plus y times 0, if you parse it, you get this tree. And then what semantic does is it walks the tree. It goes depth first, and it sees a pattern y times 0, something times 0 is 0. We can replace that node with, or that branch with a 0. And after that, the pattern on top becomes x plus 0, which can be simplified to x. And the code for that is just recursion and if statements. You start recursing down, do the depth first semantic, and then you recognize the patterns and rewrite them. But in the compiler's case, it's just multiplied by 20,000. It's not just doing constant folding. It's computing types for everything. It's computing struct layouts. And it doesn't have to be, even if you have many patterns, well, maybe you just write all those patterns once and then you implement all features. But the problem comes when these rewrites start messing with each other and they start interacting. So let's go over an example of a feature that I implemented, which should have been very simple, but in a complex code base was harder than expected. So there is a command to run unit tests for a single module. You need to combine various flags because unit test only compiles unit tests. It doesn't run them, so you need the run flag. But to run, you need a main. So there's the -main flag, which implicitly just adds an empty main, so the unit tests get run by the runtime right before that. But what if your module already has a main function? Well, it used to be the case that you got an error, only one main allowed. So there was an enhancement request. Why don't you just only do this when there isn't already a main function present? Sounds simple enough, right? But the first question here is, how do you find if there's an existing main in your program? Well, in C, this could be a simple check in the parser. You parse a function named main. Oh, there's a main symbol that's going to be generated, so don't add our own. But in D, it is not as simple as that, because you can mix in. You have string mix-ins, and those create a separate instantiation of the parser. And so if that finds a main, it also needs to bubble up that information to the compiler. A main could be guarded by conditional compilation. It could be inside a static if. It could be imported in a module that's not actually compiled into the program. Then it also doesn't count. So parsing is a bit too early to insert the code, detecting the pattern. Maybe we can check for it in the code generator. When the code generator sees I'm going to generate code for a main function, then flag something, and if you don't find something, add your own at the end. But that's too late, because the backend is language agnostic. It's separate from the front end. You don't want it to kind of get dependent on front end functionality. So the right answer is somewhere in between. But the problem is that this should have been very simple, but now you have to think about it, and this makes contributions less accessible. You need to have expertise of all these compiler stages to implement it. And in this case, there's another question which is surprisingly hard in a more complex code base. What even is main? Main has a special functionality, so the compiler already has code to check if something is main. But there's not just is main, there's also is cmain, is winmain, is DLL main. And the way these relate to each other is also kind of weird, because when you have a dmain, there's this template DCmain, which gets mixins, which generates a cmain, which calls underscore dmain, which calls, what is it, drun main. If main is so great, why isn't there a main too? Oh, look, there is a main too. Like something as simple as just an entry point function, like suddenly becomes a whole exercise in how to implement this stuff. And what makes this worse is that once something is in the compiler, it's usually there to stay. So when working on some final switch-related code, I discovered that a switch case, while usually it's just a constant like 0 or 1 or an enum value, it can also be a runtime variable, which I don't think many people know about or use. And enums can also be, instead of just an integer, counting up an integer, you can give them a base type of a custom number type implemented as a struct with operator overloading. I'm like, does anybody use this? Can we just remove these, please? Because it makes things harder. Now there's two distinct switch paths, ones where you have just a normal C-style switch, and the special one with runtime variables, where suddenly it has to be rewritten to a bunch of if-else statements. But once you ask, is anybody using this, then all the users of that feature come out of the woodwork and complain, like, yes, my store is set up around this. And it breaks existing codes, which I think is actually fair, because I'm very involved with D, so I can easily change my D code. But with other software, I sometimes have a setup that works, and then there's an update, and it just stops working. I'm like, why did you do that? I just had something that worked, and now you're making me jump through hoops just to keep things going as they are. So yeah, I think it's a pretty valid complaint. And on top of that, it's not just features, it's also just behaviors. So there's Hiram's law, which states, with a sufficient number of users of an API, it does not matter what you promise in the contract, all observable behaviors of your system will be depended on by somebody. And D is very powerful, which is great, but it also means like it exposes all of its compiler internals, like the string off property and mangle off. It exposes internal anonymous function names and how it debug prints rewritten expressions. And when I changed those, I found out through the test suite that D users unit test those symbols. They rely on mangle off or string off to give them something very specific. And that also slows down development. And even the -v output, like Steven once asked when the verbose output prints which modules get imported, but it doesn't print the import statement, like the reason why it got imported. So he was like, can you add that? I was like, sure, it's just a one-line change. Just add that to the command line output. And that broke the test suite. I was like, what? It's just verbose debug logging. This failure has to be like a fluke, but no. In our DMD, it runs DMD with -v and then has a very specific regular expression to extract information from it. And my change made that regular expression not capture it anymore, so I had to take that into account and write it out in such a way that this regex would still work, or I would have to update our DMD or something. So yeah, I can go on and on with examples like this, but this is kind of the nature of it. We add a bunch of features, it's hard to remove them, and then because of all these interactions, it becomes harder to develop the compiler, and development slows down. But of course, like, oh, poor compiler development, it's your job to, enable users to get things done. So just saying never add any features doesn't help either. It's trivial to maintain a program with 0 users, but yeah, then you have 0 users. And yeah, there's been many complaints about, oh, it's 2025, where are my tuples? And sometimes you're getting behind, get with the types. And I think Razvan is also doing a talk about the state of upcoming D features, so stay tuned for that. So now I'm going to go into 5 tips for improvement proposals. Before that, are there any questions about this section or comments already?
I just have to comment about how interesting it is that somebody else feels exactly the same way I do.
Yeah, I'm turning into a Dr. No myself, so I relate more and more to you. All right, let's move on. So, first of all, I said before that it's really easy to argue for additions because it solves your problem, but you'll be surprised by how many people just present a feature without any explanation why it would be beneficial to anyone. Like, this is a kind of a silly example. I don't want to single out any specific person. Your feature addition is dumb and badly motivated. But these are all based on like my experience from reading actual proposal examples. And so you ask why add that? And sometimes you get some weak answers that just repeat. Like, for when you want to know whether code is reachable, like, yeah, that's what it does, but why do you want that? Or, like, it could be useful, why not add it for when it turns out to be useful? But, yeah, as we've seen before, any addition has a cost. So what does make a proposal stronger is if you add code example using it in context of solving an actual problem. And it's even better if it's an actual link to production code that needs it, because it's often easy to say, oh, I'm definitely going to need this feature once I write my MySQL helper library, but then when you actually write your application, it might turn out that you don't need that feature, or you don't need a database at all, and then you have like the Yagni principle, you ain't going to need it. Only when you actually solve your real problems, you find out what the best tools and helpers are. So that's for a addition to the language, but there's also requests to remove certain compositions of existing features from the language. Like, unreachable code is useless, so it should be an error. And this kind of reasoning is often paired with a bit of a lack of imagination, because it assumes that code is always just written top-down perfectly in one go. It doesn't take into account all the weird situations that code can be in, like external factors, or it could be in the middle of debugging where you just added an early return quickly, or you're dust miting the code is in the middle of a reduction. Like, there's all these situations you don't easily think about. And yes, foot guns like using an assignment operator as an if condition exist. But if you want to forbid composition, it adds more complexity and like more code to the compiler. So the burden of proof kind of flips. Instead of asking, why is this combination useful, therefore just let's ban it, you should show that, no, it really can't be useful, or like 99% of the time when it's used, it actually causes problems. All right, so our hypothetical strawman feature proposal gets more and more annoyed, and now he's suggesting, well, if an error won't do, then we could make it a warning. But I've just had a conversation downstairs with Jonathan M. Davis. And yeah, Walter and Jonathan and I hope you don't like warnings, because either they just pile up into one big pile and nobody reads them anymore. Like what happened recently when I had a PR, which refactored something, and it had some really subtle change in how debug line counts were now starting at 0 and instead of 1 for a very obscure edge case. And the point is, it added a warning, but it was buried in like 6,000 lines of the CI log. Like I didn't notice it, but I would like to have noticed it. But it was only Steven who accidentally stumbled across it and told me, like, oh, this would have been nice to know. So the other option is, well, maybe we should treat them as errors, or maybe not always, but they're allowed during development, and then once it hits production state or you commit it, then it's an error, which is more fair. But when it's an error, like, just make it an error, because when you have, there has been this case where there used to be a warning for unreachable code, and I found that there's this piece of code, abort, and then a break statement after a switch case. And because of an improvement in how the compiler now noticed that abort just exits and it doesn't return, suddenly this was unreachable code. And this caused an error in one project. And you cannot remove the break, because then it works with the newer compiler, but the older compilers now think there's switch case fall through. And it's just a bunch of complexity. Like, there's no bug here. Like, this code is harmless. So, OK, maybe I and some people don't like warnings, but other people do. So let's give people the option. Options are always good. But I also disagree with that, because it just, yeah, it adds configurations. It adds all these new setups that may interfere with each other. Oh, I see Walter has a question.
Originally, D was going to have no warnings. And I said no to warnings for years. And the problem with a warning is once you add a warning to the language divides into two languages, which is what doesn't trigger the warning and what does. And the more warnings you add, the more it turns into multiple languages instead of one language, and it becomes difficult to test and difficult to explain to people. And unfortunately, I've failed at putting a stop to warnings being added, and now warnings are piling up. And I would really like to get rid of them all. C programs, C++ programs all tend to emit a blizzard of warnings. And then the developer is faced with, do I need to fix this warning or not? So they're always confused by that. The language becomes confusing, and I'd just like to get rid of them. Also, I want to refer to a previous slide. You never propose a feature with the justification of why not.
Yeah.
It should always have to be a positive reason for, not a, well, there's no reason not to implement this feature. So.
Nice. It's glad that you agree, because you're the actual arbiter of new D features, so these are just my opinions. But if you agree, that's good. Where were we? So yeah, my hot take, or actually I heard Walter say this as well, is that all command line switches are bugs. Maybe not per se bugs in the compiler. Maybe there's some hack or some behavior in the linker that we need to work around, or the operating system. But they do signify that there's like some kind of engineering failure, in my opinion. So an example of a piece of software with very many users is Google Translate. It has like over 1 billion. So every person is different, and with a service with that many users, you must have like millions of options for all of these people, right? But when you look at the actual interface that they present, it's just, oh, you enter the one language on the left, and a new language comes out on the right. A very legit translation here is, I think there's 2 Dutch people in the room, or 3. So I really like this interface, this simple interface, and I took it as inspiration for my own C to D transpiler, which is, it's not a natural language converter, but I felt like the philosophy still applied, that just a simple interface is going to be appreciated. And so far, I am glad with how it turned out. Now, C to D actually used to have a flag strip comments, which would remove GPL comments from a header file and make it like for licensed things. But I don't like options, and I remembered the Unix philosophy, which says make each program do one thing well. To do a new job, build afresh rather than complicate old programs by adding new features. So yeah, I feel like strip comments, it was easy for me to just hack it onto my transpiler because it already was parsing C, but a proper solution would be to have a separate program to strip comments from either a C file or a D file. Now, CTD now has 0 flags. Is this viable for DMD? Like for historical reasons? Obviously not. Maybe sometimes there are concessions and you have to add a new switch. But it should be a last resort, in my opinion. I see some proposals are like, oh, we need this, so let's just add these 3 new flags, or even these 2 new traits and attributes. Like, that should be like your last thing you think about, not the first thing. Let's add a bunch of options. Finally, my final tip, look for the root problem. Whenever people suggest new syntax, often the same could be achieved with library solutions, but saying, oh, it can already be done in the library, then can be upsetting because there's various reasons to dislike library solutions, like I don't want to import a big module just for this simple thing. It gives worse performance when I need to call a function. I want my debug builds. I care about debug build speed, and I want this to be inlined and not generate a call instruction. The error messages are worse, and the syntax looks worse. And these are valid complaints, but if you just solve them for this small case you're working at now, then you keep getting more and more of the similar in situations where you're like, oh, now there's a new problem, and now we need more new syntax and solve all these problems. So consider looking for, maybe we can look at the root of these problems, like why do people hate adding imports? Can we make that easier with better tooling, prelude modules or something like that? Can we solve these more core problems so we stop the bleeding of like all these situations? I feel like there's many historical trends also towards more general solutions. You know, early languages like Fortran and COBOL were very domain specific. They were good at business logic or number crunching, but weren't very composable. And then it was later languages like Algol and Simila, which then inspired C and C++, which are more familiar to us, where they had recursion and structs, which were just generic building blocks to model any problem in any domain. Same with graphics cards, which were originally made just to solve specific, I want to render 3D graphics, so I need a camera object or a light object, which then became more generic shaders, like vertex computations, pixel computations. And then people noticed like this general number crunching is just very useful even without graphics. They started formulating problems in terms of graphics just so they could use the graphics card. And so later developments made general programming on the GPU more useful. And today it's now used for AI and matrix multiplications, which basically like completely removed from its original rendering purpose. And finally, in languages, we used to have a complex number type in D, which was also in C, because there used to be some processors with special instructions for it. But then later developments also found more general problems and general solutions with operator overloading, better optimizers, and SIMD. So this special case of complex numbers is no longer necessary because we got better building blocks to just make any kind of custom number type more easy to implement. So that was my final tip, look for more general building blocks. To summarize this part, motivate your proposals by real-world problems. Try to find the root cause and try to offer a confident solutions. Warnings and options for alternatives should be like your last resort. Any questions about this part or comments before we move on?
Two comments and a question. First, I think it's hilarious and great you discovered being a doctor no, because when people ask me what it's like to be the co-leader of the language, I tell them I have to say no a lot, and then people yell at me. That's basically what that entails, so welcome to the club. Two, I agree with all of this, and I think this is great advice for dip writers. To the point, that leads me to the question: can we get a link to this in the dip repo, please?
Yeah, I can try to make a write-up version of this talk and.
Yeah, I mean, in the future, even the video, just so why repeat ourselves? Just point them to this. It's like, read this before.
Yeah, that was also part of the motivation of this talk. I don't want to repeat all these things to every new proposal. I just want to have one story that I can point to, like here's why. Yeah.
I agree.
All right, so the final part is reducing technical debt. Does anyone recognize this very normal version of a classic arcade game? No erotic undertones at all? My siblings know I'm very good at recognizing this kind of stuff. Anyway, this is whack-a-mole. I found this somewhere in London. And it's a good analogy that's used for how sometimes bugs are being fixed in DMD. You squash one mole, and then another mole or another bug appears somewhere else. And the problem, like this, you get this from bug fixes which have kind of this form, where people have an issue with a code example, this compiles wrong. So, oh, I know the fix. If the code looks like the one in the issue, before doing the wrong thing, do the right thing instead. And this might work for that case, but then if you repeat that, you get a bunch of incomplete, redundant solutions in the DMD code base. I sometimes find variables or mechanisms that seem like very redundant. Why is someone making use CTFE and then CTF only, CTFE block? Like, aren't those almost the same thing? Or maybe scope, do not infer scope, aren't those just the inverse of each other? And then when asked, I sometimes get an answer like, oh, well, the existing code was a hack, so I couldn't use it, so here's my own hack that I can use. But of course, this works in the short term, but it doesn't, it gives some problems in the long term, because now some say that, well, more passing test cases is progress, because we're closer to a correct implementation, but that's not always true. You're more close to a local optimum where the common cases that people tend to write at first work, but any more complex versions where things get composed, it starts to fall apart. And simple pattern detection can be useful for experimentation, because when you implement a new feature, you don't know the perfect algorithm, the perfect abstraction yet. So you might start with kind of simple version and then look if you can find a pattern and derive a complete solution for that. But you have to do that at some point. If you wait too long with that, you get an unmaintainable mess. And sometimes I also found a regression report which was introduced by a bug fix, which I then had to undo the wrong bug fix, which was just overfitted for that one test case, and then implement the correct solution after all. So the question, was that previous bug fix actually progress, or was it just some technical debt? So how do we make better code instead of the whack-a-mole bug fixes? Well, one place you can start is factoring out common code. This example of maybe scope and do not infer scope, I factored those out to be just one variable. And there's other cases in the compiler where there's like shameless copy pasta, like the semantic checks for arithmetic operators, and the slight differences between those are often bugs, so it shouldn't be duplicated. An example of that is the expression semantic for an unsigned right shift and a right shift. Here's the two versions of the code. Do you see any differences? Like, the only difference is the sure exp and the usher exp on top. It's doing the exact same thing, just copy-pasted in two places. And the left shift is also basically this, just with one extra comment somewhere. It's a lot of copy-paste, and this has since been factored out. However, reuse isn't always correct. Some people say there's the dry principle, do not repeat yourself. And I feel like I can fill a whole talk about how various ways that people misapply this as some kind of, whenever there's duplication, you must always factoring it out. It's always better. There are some considerations. consider an internal function has pointers. It's supposed to return a Boolean true if a type contains pointers or not. So for int, it returns false, int pointer true. If you have a struct, it's like the aggregate, the int not, it doesn't have a pointer, but the string has a pointer and a length, so that's true. What is a void 8? Does it have pointers or not? Who thinks it has pointers? See a couple hands. Who thinks it doesn't have pointers? Few less. So it returns true, but that's because it's being used for, it was originally written for conservative GC scanning. So when the garbage collector needs to scan for pointers, the spec says a void array can contain pointers, so those need to be scanned. But since then, it's also been used for safe checks, which just checks if any unsafe pointer operations can be done with the type, and then it actually should return false. But because this code was reused, now it has this wrong behavior. But you might think, oh, that's an easy fix. Just add a Boolean parameter to the function. You add a special case, and you can, at the call side, you put it true when you want to generate type info and false when you are doing safe checks. And you can get away with that probably in this case. But be very careful, because this kind of code returns in absolute spaghetti. So let's take a look at the code for operator overloading. So indeed, when a struct defines op binary, you can use the plus operator. And then this code is responsible for rewriting a plus b into a dot op binary with template plus string, etc. And the code for that is like 300. There's a 300-line function which handles this for op assign, op equals, op binary, and op unary. So all these 4 basically different code paths are all funneled through this one giant incomprehensible function. And here's a bit of an excerpt zooming in where you can see that inside that function there's a bunch of code paths that check, oh, if it's the plus plus or minus minus case, do this. And unless it's the op assign or equal case, then try op binary. And this is obviously hard to maintain. And we know that large functions are bad. So a naive fix is, oh, let's just cut it up into smaller functions. Oh, this looks like a nice boundary. Let's cut this up, move it into something, give it some kind of descriptive name. Your spaghetti function now has a spaghetti prologue, middle, and epilogue. And you recursively do this. Oh, there's another 10 lines that I can make into a smaller function, a helper, spaghetti check, spaghetti help. This doesn't work. You just now have 5 incomprehensible functions. The spaghetti is still there. It's just the order is now also mixed up. So how do you improve this situation? Well, what I did for it in this case a few months ago is try to separate the code paths through it. So how do you do that? Well, the 300-line function is kind of hard to fit on a slide, so this is a bit of a demonstration toy example, which is representative of what has been going on there. So first, you have this overload function, which does both op binary and op equals with some slight differences. First thing you do is you duplicate it. So I duplicate it for overload binary and one for op equals, which temporarily makes it worse, but we're going to fix that. Then for both copies, you partially evaluate the values. So now we know that because we have a specific version for op binary only, these if conditions are just trivially false or true, and then you can remove the false case and the true that result in this. And now the name is also a constant, and we can just inline it there. And if you repeat this process for the overload equals version, you get something like this. And now you have you separated the 2 code paths in 2 functions. And after separating, then you can look for a repetition again and try to factor out common things. So for example, this generation of the call expression, you can make a helper function. In this case, it's a bit larger now, but when you have not just op binary, op equals, but also op assign and all the other op unary cases, I think this the resulting code is a lot better. It used to look like this. This demonstration example is not too bad, but it's still kind of like what's going on? What are the 2 if statements doing? Here, I think it's pretty trivial. Binary, it uses a binary. It passes these arguments. Equals, it doesn't have template argument, but it does have the 2 binary arguments. So it's Walter has a question or a comment.
What you did was you removed if statements, and every time you can refactor code to remove if statements, you've removed bugs. Every if statement is a bug. So yeah, I want to congratulate you on this refactoring. It's pretty sweet.
Thanks. So this is just an example. I hope this inspires you to apply this and make code more straightforward. Instead of if statements, just make it readable from top to bottom. I think that's the easiest code to follow. And this refactoring reduces accidental complexity. So without simplifying the language, it does simplify the compiler and still makes it easier to implement new features. In this case, I used this refactoring to improve the error messages for operator overloading. So now when an operator overload fails, it doesn't just say, oh, couldn't find like the types mismatch. It says, oh, this operator overloading failed because this function couldn't be called, or there's no operator overload. Maybe you want to implement it with this. So by improving the code, I could enhance the code. And that's a big takeaway. So code duplication and premature abstraction can both be bad. There's no rule like always deduplicate code or always generate a nice OOP, object-oriented tree before implementing. Like both can be bad. When you can't get away with your whack-a-mole bug fixes anymore, I've just shown this technique where you expand the intertwined code path, you trim the dead branches, and then you factor out the common code again. I think this is a very powerful kind of set of steps you can do to improve your code quality. And I hope it's useful for your code as well. So now for the takeaways of the whole talk. There is a limited complexity budget for features. So we have to spend it wisely. And a strong proposal spends very little complexity budget and gives you a lot of bang for your buck. It solves not just this problem you have today, but the more general problems that users face across various disciplines. And when your code gets kind of messy, try to refactor it in time, pay off the technical debt, and that expands your budget to add new features. Also, a final comment, don't take the no personal when the feature proposal gets rejected. It's not because we hate you or you're a failure. Like, it can be kind of, we humans have kind of trouble with rejection. So, yeah, we still like you. There's just this hard, it's just, we don't want to add too many features and make the language worse for everyone. And that was my talk. Any questions?
Well, since nobody else has any questions, I thought I'd pontificate for a bit. But I really think this is a timely and great presentation for us, because I've gotten, people have gotten angry with me for rejecting their proposals, and they say, you never accept any of my proposals. So I looked through GitHub and came back with, well, I've approved 93% of your pull requests. So what do you mean I reject all your proposals? And they quit anyway. So this is a very difficult problem for us, and I'd like to congratulate Dennis on taking the slings and arrows of him. And I just see a lot of good stuff in his about how to write good code in your products. I think this presentation goes well beyond just compiler stuff. I'm surprised he didn't get into editions. Probably ran out of time there.
Yeah, I have so many more examples, but I just had to draw the line somewhere. I had a whole rant about the class structure in DMD, but it's also for another day.
Yeah, one of the problems is we can't do. one way to reduce the complexity of the language is to delete features that are no longer of any particular use. But every time I try to delete one, I find somebody who has built their entire life around this useless feature. And so that's where the additions comes in. Unfortunately, that doesn't make the compiler any simpler, but at least it makes the language simpler for the user. And so Dennis is in charge of the additions, so I hope that we get them in the language.
One thing I forgot to mention, by the way, about the operator overloading thing is that there used to be D1 operator style overloading, where instead of op binary with a template string for the operator, it has op add, op div, op minus, op. And those did successfully get removed after some time, and that was also a huge help into making the operator overload code easier to maintain. So that was a successful case of removing features to remove complexity in the code, and that enabled a lot of the refactoring as well.
May I ask maybe a comment to Walter? Have you considered D3?
Considering the disaster that the D1 to D2 transition was, no. Too many people had set too much of a store by the way D1 did things, and that was kind of a bitter pill for us to swallow. So people did not want to upgrade their code. They had set a giant store by it. I totally understood their issues with it. I don't want to go through that again. So the additions thing is going to be our way forward. Not gonna do the D3 thing.
Just a comment on the technique you were saying with pruning the dead branches. Can't back call that reconciling differences is one of the refactorings. It's basically make things look as similar as possible, then take away the common, exactly what you just described.
Dennis, you had a lot of interesting comments, interesting presentation. But a lot of your work was what I would call kind of like low-level architectural things, you know. And I'm wondering, did you see any opportunity for larger architectural changes in the compiler that would significantly reduce complexity, or do you think that we're kind of already there? I mean, I don't know forward references. I don't know the compiler. I'm just wondering are there some larger architectural issues which might significantly reduce the complexity? I mean, it's risky, but it might pay off. Just what do you think?
Yeah, that was also one of those things that had to be cut, like I wanted to include, so I'll try to briefly summarize what I was trying to say. I believe that 90% of compiler features are just functions. They just have some parameters and return something. And many, like the array index operations currently, they have all this code for checking if it's const compliant and whether it works with shared and escape checking. But if you lower those operators just, even without operator overloading, just internally to functions, well, not literally functions, just a general function construct, then those are handled automatically. And you don't need all this extra code basically doing the same as what function signature checks already do. And there's also been some progress with lowering various D-runtime hooks to templates, where many things like associative arrays have I think it's just been merged, where instead of, where it gets lowered to template instantiation. So you still get the syntax, and the user hopefully has like the same experience, but internally a lot of the bugs, a lot of the logic is handled by the template instantiations. And I think many bugs have also been uncovered from lowering it, where suddenly you see, oh, when you apply the function signature checks to associative arrays, which used to be a language feature, suddenly you see that this const check or the shared check was missing here. So I think that's basically just the key. Try to frame everything as a generic function that can be used throughout the compiler.
So I think one thing that would be helpful in terms of communication is to be a bit more open about technical debt being something that may influence decisions on language features. because sometimes I get the sense that instead of doing that, people instead like exaggerate the drawbacks of a feature. When you could just say, well, yes, this seems like a good enough way to do it, but it is really difficult to put this into DMD and not incur a lot of technical debt.
It is true. Like how easy it's to implement in the current DMD code base is a huge factor in how likely something is to get realized. And yeah, that is something that shouldn't be the case, but it's kind of like the reality of it. And you're right that we should make people aware that this is a big factor in how things go.
Yeah, I think it's good to not be ashamed about it, because then you can be honest.
Yeah.
Another example of unnecessary complexity, and this was an idea I got from Herb Sutter, is we have implicit variable declaration with this parameter. And so the code and the semantic code is rife with special cases for the implicit this parameter. And by making it an explicit parameter, we may be able to greatly reduce some of the complexity and the semantic routines. So I've thought for years that we should do that, have never gotten around to it. But I really like your work on the operator overloading stuff and fixing the implicit this to make it just like any other parameter, I think would be a significant complexity win for us.
So I think we'll have to stop here because we have our next talk in just a few minutes. So thank you again, Dennis, for your talk. And see you in 9 minutes. Okay, so we're going to move on with our next talk now. But before that, I just want to remind you guys that today we have at 6 at Trinity Bell on Mitre Street. I hope I pronounced that correctly. Mitre Street, M-I-T-R-E, Mitra. Mitra. Okay. Yeah, so it's called the Trinity Bell, and we're going to have a Weka happy hour, where for an hour we're going to have like free food and drinks. And there's also going to be a quiz, right? And if you win the quiz, you're going to get like a nice prize, which is also sponsored by Weka. So yeah, be sure to come there. Now, our next speaker is Jonathan. I think everyone in this room knows Jonathan. He's been working on Phobos v3. And yeah, he's going to share some of his work with us. So everyone, give it up for Jonathan.
Okay. For the past year or so, primarily what I've been working on with regards to Phobos v3 is the traits and meta stuff. Since everything depends on the traits and meta stuff, unless it's not doing any compile time anything, which there are some things in Phobos that don't do any compile time anything, but the vast majority of it does. And in particular, to finish the range work I started on, I need the traits and meta stuff, otherwise I can't finish implementing it. So I have been digging through this and porting and altering as appropriate the traits and stuff from Phobos v2 to Phobos v3, and hopefully overall improving the situation. So I'm going to talk about some of what's been going on with that in terms of problems I've run into and some of the design decisions. Just in terms of overall goals, I mean, this is basically the same for Phobos v3 as a whole, not just the traits and meta stuff, but we're looking to fix things that we could not fix in Phobos v2, because if we fix it, we break people. We don't want to break their code. And especially if you're talking about traits and meta, if you go and change that, that can do all kinds of subtle things to people's code, potentially not even causing compilation errors that could result in just doing the wrong thing and they don't realize it. And so we're looking to fix that kind of stuff as much as possible since we're getting a fresh start with this, and also apply lessons learned over the years in terms of how to do this better. And a lot of them doing is just thoroughly documenting everything that I'm porting over, so it's very clear what it does. Some of the documentation for v2 is not always that detailed. And in writing the documentation, in many cases, it becomes clear that it's doing the wrong thing, or it's just too confusing, or needs to be simplified, or whatnot. And I'm generally testing it all to death to make sure it does the correct thing. And in a number of cases, even if something's ported over pretty directly, we end up changing names in some cases because it doesn't follow the appropriate convention, or it just wasn't clear enough. And like, for instance, for the, you have, has elaborate destructor, I think is what it is in v2, and Adam wanted that changed to complex instead of elaborate because he thought that would be clear for non-English speakers. So I think it has complex destruction now or something like that. So there are various things that have gotten renamed. In terms of the modules we're talking about, for Phobos v2, it's standard traits and standard meta. Where that sits at the moment, Phobos v3 is Phobos sys traits and Phobos sys meta. I'm not going to go over all the structure of that at this point, and it's subject to change anyway, depending on what's going on with that, because it's not like it's been released. And just a quick overview in terms of the traits and meta stuff is, when we're talking about traits, we're either talking about the built-in compiler traits, which start with underscore traits, or templates, which are used to give you information about symbols, so that you can then use that generally for code generation. And for the meta stuff, it's meta programming, and that, generally speaking, is operating on alias sequences to do various algorithms, similar to what you would do with standard algorithm, except this is all compile time stuff. Some examples here is dynamic array, would tell you whether the type is a dynamic array. Whereas enum members would give you all the members of that particular enum. For some of the built-in stuff, you have is copyable, which would tell you whether a type is copyable, since not all types are copyable, even if most of them are. Or another one would be getting the overloads of a function, since there are cases where you very much want to do that. So there's a whole bunch of traits built into the compiler, and there's a bunch more sitting in Phobos as templates to provide additional information. An alias sequence, or alias seq is the template we use for this, is basically a template argument list. That's what the compiler uses internally for that kind of stuff. And we end up operating on these. Walt originally called them tuples, and there were arguments over that because they don't really behave like people would expect tuples to behave, nothing else, because they always expand, so you can't nest them. But at the end of the day, it's basically a template and an argument list that we then wrapped into an alias. And so standard meta and Phobos system meta generally operate on these alias sequences. And they're just basically a sequence of alias symbols, which is why that's what that's called. Some examples from, this would be the same with standard meta or Phobos system meta. The first one, we have an alias sequence just of types, and passed to the template filter, which is used to filter based on a template predicate. In this case, is dynamic array. So it takes all the types from this particular alias sequence and gives them in the result that all the ones that match that particular template predicate. Similarly, the one below doesn't deal with the template predicate, but it does, it's called reverse, and it just reverses the order. So there are cases where you might want to do that. Generally speaking, you don't want to be doing a whole lot of the stuff with metaprogramming with alias sequences because it's not particularly fast. But particularly if you're doing a lot of operations with types, you tend to have to do it because you can't do those with CTFE. Some general design decisions in terms of going about this. For traits, one problem we have in V2 is a number of them treat enums as their base type, which causes subtle issues because when you do an implicit conversion, it doesn't behave like the original. So code that compiles with what it implicitly converts to doesn't necessarily compile with the original. And so you need to be making explicit design decisions with that, not just saying, okay, you know, is some string would be one example. Actually, that one doesn't accept enums because we may not accept enums to fix bugs at the time. But some of the others, like is some char, I think accept enums, and we'll treat it as a char or whatever, even though it's not, it's an enum. But with the traits, in general, the other thing is we're looking to, in general, make them operate on types rather than both types and other symbols because that reduces complexity and makes it clear as to what's going on. There are traits that need to operate on the symbols themselves. For instance, get the names of parameters because that's not part of the type of a function. But for a lot of other things, if you're just operating on the type, it simplifies things. And just in general, we're looking to simplify traits and minimize how much magic they're doing because there's several of them that have issues precisely because they're trying to do too much and people kept adding things to try and make it do more and it just becomes a mess such that even if it works in the basic case, it's a problem overall. And so we're just trying to clean them up, make them as clear as possible and as simple as possible so that they're clear to use. And in a number of cases, we're stripping out some functionality and externalizing it so that you have better control over what it's doing instead of it doing whatever magic internally and you have no clue and just does what you think it does maybe, but not actually when you get down into it. And I found a number of those things that I wasn't aware of prior. I mean, some things I was aware of prior, but a number of things I wasn't aware of prior when just trying to explicitly document in detail what was going on. It sometimes showed bugs and design decisions that needed to be done differently to avoid problems. As for implicit conversions in general, I would argue that in almost all cases you don't want to do them with template constraints. It's very different from a normal function because the normal function you do, you know, if it takes a long, say, and you pass an int, it implicitly converts at the call side. That's not a problem. The same with most of that. So when the function itself isn't operating on whatever that type is, regardless of what the original was. But when you're dealing with a template constraint or template specialization, all you're doing with that, if you're checking for an implicit conversion, is deciding whether that template is allowed to be instantiated with that particular type. It doesn't actually change the instantiation. And so you might think that you're operating on that type because you had the test for, you know, the template specialization or a specific conversion, but the conversion doesn't actually happen, which causes a number of issues if you're not careful. And there's no way to actually force the implicit conversion at the call site with a template. You can do it internally with a cast or whatnot, but you can't do it at the call site. So this causes a variety of problems. If you're lucky, the problem results in code not compiling, which of course isn't fun, but now you know you have a bug and go fix it. If you're really unlucky, it compiles and does not do the right thing. And because this is templated code, unless you happen to test it with the type that has the issue, you don't necessarily know that you have a problem. Maybe a user down the line comes and complains, you have to go fix the thing. So while there are cases where you would want to do implicit conversions, you very much want it to be purposeful, not by accident. So we don't want to be doing things like having enums pass without you asking. So just looking quickly at template specialization here, this is taking long, so it's any type that implicitly converts to long would be accepted. However, this code is probably not going to compile with anything other than long because it's adding it to a long and returning it, which that is then going to become a long, but the type that's typed to return is the exact type you passed in. So if you pass it a long, it will compile. You pass it int, it won't. So this is a fairly straightforward one, but I've occasionally run into bugs dealing with template specializations where thought something was doing what it's supposed to, and when you actually try all the various combinations, you figure out it didn't because it was not behaving as you expected because of the implicit conversion not occurring. Just an example of a template constraint which allows enums is integral. In Phobos v2, tests whether something is basically an integer type in long, short, whatever. But it allows enums as well as long as their base type would pass. And so, like, again, this wouldn't compile because the result of the expression, if you pass an enum, would be int in this case, not the enum type, and yet you're trying to return the enum type, and there's no implicit conversion back to the enum. So this would fail to compile. One case that was pretty nasty is convertible to string. Got added a while back to, I think by Walter, to try and make it so that functions which were taking strings could be generalized to operate on ranges of characters, which is fine, but the attempted solution was to check the implicit conversions to make those still work, which in some cases is fine. But what happened in particular is static arrays, unfortunately, implicitly convert to dynamic arrays. And so you ended up with several cases where a static array would pass the template constraint because of the implicit conversion. But because it's a static array and the template is instantiated with that type, not the implicit conversion type, it copies the data into the function instead of slicing it like it would have before if it had explicitly taken dynamic array. And then there were functions that were then trying to reuse code, so it would slice the static array, it would explicitly do the conversion to string and pass it to the code that was operating on ranges. And that would work just fine, except in the cases where you actually return to slice. Like in this really simplified example, you pass in a static array, it slices it within there and passes it to the other function, and that returns the slice, and that gets returned out all the way. And so if you're passing it a string, it compiles just fine, it runs just fine, everything's fine. But if you pass it in a static array of char, you now have garbage on the stack because you have a slice of function that's now gone. So there were experienced developers writing this code and making this mistake. So as a general rule, I just think it is too dangerous to be dealing with implicit conversions and template constraints. There are cases where it is what you're going to want, but you have to be very careful with it. And I would say that in general, the two solutions should either be you check the implicit conversion and then force the implicit conversion within the function so that code is then operating on the desired type and not whatever the original was. But that still has the static array problem in that case. The better solution, which I don't think we used to be able to do because I don't think we used to be able to overload on templates and non-templates, but you can overload the function so that you have one that is not templated and one which is templated, and so that the implicit conversion you want, you do with a non-templated one. And so that works, it passes to that, it does the implicit conversion at the call site, not within the function, and you avoid all these problems. But the big thing with regards to standard traits here, and porting that to v3, is we want to avoid any of these traits doing the implicit conversion for you with the checks. Like if you choose to do the implicit conversion, that means you're right, you can do whatever you want as far as that goes, but we don't want the general tools to just automatically do it. So like in Phobos traits, here's an example with is dynamic array and is integer, where with the enum types of base type string, it does not pass as dynamic array, even though the string does, because the string's a dynamic array. Instead, if you want to get the base type of the enum, you have to use the original type template trait to get at the base type of the enum to then check the type. Same with is integer, which checks with int long, what have you. It's not going to pass is integer with an enum, but it will if you get it the original type. So you have to explicitly say that's what you want. It's not going to just do it for you, because there's plenty of people who are going to use some of those traits from V2 and not realize that it's doing enums and then end up with bugs without realizing it. So the next big issue, which is kind of painful, is it turns out type of is ambiguous in the general case. In the first example here, it's clearly an expression. You're adding two numbers. That's going to be int, not a question. Next one's a clear function call, and you're passing an argument to a function. That's an expression, no question of what it is. The third one is, again, clear function call. You're doing with the parens. But the last one, you are just passing the symbol. That may or may not be a function call. To look at this with some different things, if you have a variable of type int and you pass this to type of, that's going to be int. You really don't care whether you're talking about a symbol or an expression, because in both cases, it's int. The same with manifest constant. Again, it's the type it is. You're not going to use an expression. It is that type. But if you have a function, particularly if you have a getter function, getter property function, then it can be called with no parens and return value. So it can be used as an expression. And the compiler has to decide what it's going to do with this. And what it does in the normal case is give you the function type, which in some cases is not what you want, and in some cases is what you want. Where this really runs into problems is when you're dealing with properties. So, like all these cases here with foo are expressions, regardless of what foo is, but you have no way of knowing whether foo is a variable, an enum, a function, what have you, so long as this is syntactically valid. You know, in the last case, it could be a member function, or it could be, you know, a function with universal function call syntax, or it could be a variable. So what happens if you have a variable and you do type of on it, it does not matter whether you're talking about expressions or the type of the symbol itself, because they're the same thing. An int is an int is an int. However, with a function, this varies depending on the context. So if you're getting the type of a function as the symbol, you want the type of the function itself, the symbol, then that's the function type. But if you want the type of the function as an expression, then if it's a getter property, it will compile, it'll work. But if it's, you know, a setter property or some other function call where you actually need to have arguments, then it's not a valid expression on its own. So type of has to either give the type of the symbol or the type of the expression, and where you get the ambiguity then is these getter properties. And I'm not talking at properties specifically here. Talking about anything you are using as a property. It's acting like it's a field or a variable, whether it is or not. It could be a value, it could be a variable, it could be an enum, and you're getting its value, that's a getter property. On the other hand, it could be any function which is called with no arguments and returns value, which of course is what we want to be doing in many cases for getter properties, so that we can, can have a function instead of an actual field and change what it does in the implementation and all that kind of stuff. But this inherently creates an ambiguity, because for any other function, when you ask for its type, it's clearly not a valid expression. It's a symbol. But for these functions, it could be a symbol, it could be an expression, depending on the context. And where the problem enters is because of optional parens in that property. If parens were never optional, and specifically, if there was no way in the language to ever have a function act as a property, so functions always had to be called with parens, then you have no ambiguity, because when you call the function, it has to have parens, so it's clearly an expression. Whereas if you pass the function on its own, it's now the symbol. And so type of would know exactly what to do. There would be no ambiguity, no problems. But of course, we have optional parens and property. Now, property makes things considerably worse than it would be with just parens. Originally, we've been planning on getting rid of optional parens and making it so that you controlled whether you could do the parens or not with property. So you'd be explicitly saying, I want to treat this like a property function. And we never got that far and decided to keep optional parens, but that property is still there. And it affects type of. So what ends up happening if you have a function and it is not marked with that property is it gives you the type of the function. Which, of course, is annoying in the case where you are looking to treat it as a property, you want to know what it is, especially if you're like, okay, I have foo, I don't care whether it's a variable or function or whatnot, I'm just going to treat it as a property, give me the type. And so what happened with that property was it was changed so that to try and treat it more like a variable, if you have that property on a function, instead of treating it as the type of the symbol, it treats it as the type of the expression. Which for a getter property means now you have the return type instead of the type of the function. So any case where you actually are looking to do introspection on the function itself, this is a problem. And because of optional parentheses, there are still cases where you would be doing this type of introspection and looking to treat it as a property, and you get the function type instead because there's no app property to affect it. But it's arguably even worse with the setter function, because if you use app property on a setter function, then it's not valid with typos anymore at all, because the setter on its own is not a valid expression, and DMD is trying to treat it as an expression. It'd be a valid expression if you like assign to it, but on its own, it's not. So there's all this is that app property makes typo highly inconsistent in terms of your ability to get the type of something when functions are involved, and really it's solving the problem in the wrong place, because it's the type introspection code that actually cares about whether it wants the type of the symbol itself or whether it's looking at the symbol as a property and wants to know what the type is going to be within an expression. If we didn't care about adding keywords, I'd probably suggest something like getting rid of type of and adding type of sim and type of expr or something along these lines, where type of sim, you were saying, I want the type of the symbol. It did not take arbitrary expressions. It just took symbols, and it gave you the type of that symbol. And for type of expr, it would take arbitrary expressions, including a symbol on its own, but it would treat it as an expression in all cases. And so you'd be saying exactly what you wanted, and there would be no ambiguity. Which one you'd want to use would depend on the context. However, that would mean adding keywords or doing some other tweak to the language that I don't know if we can do or not. Stephen was suggesting yesterday when I talked about this, maybe parameterizing type of in some fashion to do this. I don't know. Either way, I treated this as a problem I had to solve in the library, so I came up with a library solution and added 2 new traits. Had a bunch of arguing over the names, but this is what we ended up with. Symbol type and property type. Symbol type gives you the type of the symbol as a symbol. So if you give it an app property function, it's giving the type of the symbol. It doesn't matter that app property is on there at all. Property type, on the other hand, is giving the type of the expression. Now, it can't take general expressions because you can't pass an expression to a template alias parameter. There's no way to have a template, as far as I know, except arbitrary expressions. They can accept symbols, which is really what we need here. So property type will only accept symbols, symbol type will only accept symbols. But what symbol type is telling you the type of the symbol, is property type is telling you the type of the expression. The reason it is property type and not expression type, aside from just trying to reduce confusion over it not taking expressions, is that the only context in which a function is a valid expression on its own is if it's a getter function. It returns a value and is taking no arguments when you call it. And so the only case you're actually going to purposely use this is if you have something you want to treat as a getter property, and you don't care whether it's a variable or a function or what have you. You're just saying, this is a property, tell me what its type is as a property. So what that means is if, in terms of just general usage, if you really want the type of the symbol, use symbol type. If you want to treat the thing as a property and get what the type would be in an expression, that would be property type, which should simplify various traits we have right now with like standard range. There's some really ugly stuff to get the type of front because of having to deal with this problem. And type of would still need to be used, of course, if you have any general expressions, because you can't use an expression with a template alias parameter. But it's a non-issue at that point if you're only using it for stuff that's actually expressions, because that's not where the ambiguity lies. The ambiguity lies with functions that are getters. So it's just some quick examples of what falls out from this. Phobos v2, we have isSum function, which will tell you whether a symbol is a function pointer, or delegate. And it has to deal with the property, at property mess. and work around that to tell you that a property function is a function. And it only works if you pass the symbol, not the type, because if you use typehov on it, you get the wrong thing. So this is kind of mucky and error-prone, because plenty of cases you'd use typehov and pass it in and get the wrong result. And so what this does is break out that whole problem. And so if you want to know the type of the symbol, use symbol type. And his expressions will actually tell you this already for whether if you want to know something's a function, function pointer, or delegate, you can just use the expression with equals return. So in that case, you've eliminated that whole template in many cases. Now, we still have isReturn as a replacement that only takes a type, just as a wrapper around this expression, just so that it can be used as template predicate, really. I wouldn't advise using under normal circumstances, but you can't pass, like, we don't have template lambdas, for the language. So if you want to pass something that requires a template predicate, you actually have to declare a template. So we do have various small wrapper templates like isReturn. But like has indirections is in Phobos v2 as well, and that's checking whether there's any indirections in the type, whether, pointer, class reference, what have you, and whether you use a symbol type or what you want with that is going to depend on the context. So if you are looking for the type of the symbol itself, you use symbol type. If you're really trying to use this thing as a property, use property type, and that then is up to the programmer with what they want to do based on their context, rather than this trait in Phobos trying to decide for them as to what it would be. Same with the assigned integer. Some context where you'd want to treat it as a symbol. You get the type of the symbol of the context where you want the property. So by pushing this out into a separate trait, pair of traits, that gives the programmer the ability to then just cleanly do that and make that choice and not have these various traits burdened with trying to deal with things like at property and whether this should be treated like a property function or not in that particular context. Another problem I ran into, more about meta than traits, is there are at least a couple of templates in standard meta which deal with symbol comparisons. Like no duplicates strips out all the duplicates is the idea from your alias sequence. So you only have what's left that's different. Or stack index of will give you the index of the one you're looking for within the alias seek. The problem is, how do you compare arbitrary symbols? There are a number of ways to do it. If they're values, you could just be using equality. On the other hand, if they're types, you'd be typically using is expression to compare them. Or we have the built-in trait is same, which will literally tell you whether these are the two are the same symbol. But what you want to use potentially depends on the context, not only with regards to what the symbols are, but what your goal is in terms of what you're doing. And standard meta internally has a private trait called isSame, which attempts to do this and does it in a rather wonky way that is rather error-prone. Just an example here, if you have an enum, so a manifest constant with the value, these all have 42 just to take the value out of the equation. And static immutable int and the enum can both be read at compile time. So they can be compared at compile time, whereas the static int without immutable cannot be read at compile time. So what the compiler is then able to do in terms of information with comparison differs. But what this happens with isSame is the cases where it can compare the values at compile time, it compares the values at compile time and says whether they're the same. But if you give it a variable here, even though it's actually going to have the same value, it's just going to compare the symbols and say, are these the same symbol? And so this gets to be very error-prone. And if you just change something from an enum to a static int or whatever back and forth, you can have code changing on you in weird ways. What's even worse is if it's a getter property, it calls it. So if you try to compare a manifest constant against a function that can function as a getter property, then it will do the comparison for you. On the other hand, a static immutable int, it won't, because it's an R value. And it's an L value instead of an R value, and it's making some of those decisions based on R values. So if you go back to the static immutable ints will compare against the enums, or the enums against themselves, and compare the value. But if you compare the two static immutable ints against each other, they will be false because they're not the same symbol, even though they have the same value. So this is just incredibly error-prone in terms of what's in there, and it's baked into standard meta. And my solution was to not bake it in anymore. So no duplicates, we ended up renaming a unique to be more like standard algorithm. But it takes a predicate, template predicate, instead of just assuming how the comparison works. So at that point, you can pass whatever trait you want to do that comparison in whatever manner you think is appropriate for your code, which could be exactly the same thing as what isSame does in standard meta, or it could be something that's more appropriate to whatever you're doing. But by breaking it out, it removes that problem, and you have the choice. Similarly, static index of, we renamed to index of, and now it takes a predicate, so you're asking for which element within the alias sequence matches, but it's based on your predicate. And so you have the choice as to what you're going to do with that. Some examples that I have in there right now is equal, just does the basic equality comparison that you would normally do at runtime. Same symbol is doing the underscore traits, see whether it's the same symbol. And same types, just doing the is expression, see whether the same types of these can all be used as template predicates. I probably need to add more variations on this for other context. When I was talking to Till about this the other day, he wanted something closer to isSame, so that he didn't have to think about it. But I'm going to have to sit down and see how possible it is to actually do that without it doing stupid things, because what's there right now is error prone. But regardless of what I come up with, what anyone wants to do with that, because it's a template predicate, you have the choice. So you can do exactly the same thing as it's doing before, or you can do something else. And just some quick examples of these being used. The first one, you got a sequence of types, and unique, you pass it isSame type, and then it's going to use that for the comparison. And so any of them where the type was the same, it's going to strip out the second one in the list, so it's only keep the unique ones. Or in the second case, it's just a bunch of values, and it's comparing them with as equal and doing the same thing. Or in the last case, it's using index of to find the one you're looking for, and it's asked for the same symbol as foo, and so it finds the first foo in the list and gives you that index. So it's basically the same kind of stuff you're doing in standard meta, except that it is a bit more flexible. Next fun problem I ran into, at least that I'm mentioning today, is there's a trait in standard traits called isCallable. In principle, what it's trying to do is check a symbol and see whether this trait, whether the symbol is quote unquote callable in the general sense. For some cases, this is really obvious. If it's a function, yeah, it's callable. Function pointer, it's callable. Delegate is callable. But in the general case, this doesn't actually work. The biggest example would be if you have a templated function and you pass that in, you're passing in a template, not the function. And there's no way for the trait to know whether an arbitrary template is callable. The thing won't even compile until you try and instantiate it with something. So you could pass a template instantiation to isCallable, but you can't pass, you can pass a templated function too. It's just going to say it's not callable. But there's no way to actually handle that appropriately. And it gets even worse because it deals with opcall. Like the first one, in this case, this would be the syntax for getting a default initialized value. So it looks like a default constructor. We don't actually have default constructors, but it will, an explicit way to get a default initialized value. And whether that's callable or not depends on whether static opcall was used. If T defines static opcall, then that is callable. If T did not define static opcall, then that's not callable, even though it's perfectly valid syntax. Similarly, just normal constructor call. Here, you pass a 42. If that's a normal constructor call, that's not considered callable. But if you did static opcall, it is considered callable. And then you have just the general problem with templated functions, where you can't really test that properly without an explicit instantiation. So in the general case, there are really two solutions to this problem. In most cases, what you care about is not actually that the thing's callable. You care about that it's callable in a specific piece of code. You have a specific set of arguments, a specific expression. Does this compile with what I'm looking to do? And if it does, then it's going to instantiate the template and the whole shebang, and so you don't have that template problem anymore. Doesn't matter, whether it's function, whether it's opcall, what have you. As long as the syntax works, you're good. Or in some cases, you might want to check whether the type is a function pointer, or delegate, because that's always going to be callable. Walter's got a question or comment. Microphone?
Oh, there we go.
Yeah.
It seems to me that maybe the real problem here is we don't define what callable is. Could that be the problem here?
Well, it's trying to see whether an arbitrary symbol is quote unquote callable, which means it's behaving like a function.
Well,
and you can argue about what exactly that means, but most people would consider a templated function to be callable, for instance.
well, you could have a template with compile time arguments, and is that actually being called as? I don't know.
No, but in this particular case, it would be checking whether it's a function, I believe is what it's doing. But the core problem is that if you have a templated function, like unless you instantiate it, you don't know that it's callable. You know, it could just be errors when you try to instantiate because you give it garbage.
Okay.
So, and the reality of the matter is, even if you checked this, even if this worked, you don't generally care in the sense that what your code is usually going to be doing is going, okay, I have this set of arguments that I'm going to be passing to this function, and I want to make sure that function call works. The fact that it's quote unquote callable in the general case doesn't matter. It matters that it's callable with these two arguments or whatever they are. And that obviates the whole problem, because then you're testing that exact expression and you've got past the template problem in the whole bit. So at the moment, I'm not porting anything like it's callable over because there's a better solution in terms of how you check it, and it gets rid of the whole question.
In the general case, I agree with you. But if you have something like map or filter, there are no arguments to try it out with.
Well, you try it with none then.
Yeah, but the thing you're passing still needs to be callable in a certain sense. My point is it's complicated. But in the general case, yes, normally you care about calling it with these parameters and that you can assign it to a variable type or whatever, sure.
Well, there may be corner cases where you have a specific thing where you want to do something closer to this, but I think at that point you need to be testing whatever makes sense for that specific case. I think we'd have to sit down and talk about exactly what's going on with that anyway. But certainly, I mean, we've had bugs reported on this where someone tried to do something because it's checking as callable and it doesn't work because they're passing a template. And if you just can rearrange the template constraint so it's checking that a specific call works, basically it's checking that the code that it's going to be using works, then you're fine. Another issue that popped up, I ended up spending like 2 hours giving a reply to someone at this point explaining why exactly it was the way it was and decided I needed a trait to fix the problem. But default initialization in D, in theory, is very clean and straightforward. And that every type is supposed to have an init value. And if you declare a variable of that type, it will be default initialized to that init value. This allows you to just get the default value for things with the init value all over the place, very clean, very nice. The problem is there are some corner cases where this doesn't work that were added somewhere along the way. First example would be you can actually disable default initialization. There are a variety of reasons that someone would want to do this. It hamstrings some things because like you can't then stick that type inside an array and whatnot because there are various language features that require the default initialization. But you can disable default initialization if you want to, which means now code can't actually rely on this working in the general case. And then a big problem is non-static nested structs have a context pointer. The init value has nothing to do with the context pointer. So what happens if you try and use the init value explicitly, in this case either by initializing a variable that way or by, say, passing it to a function, which to pass it to a function you really need an explicit value. You can't just rely on the default initialization. But if you use the explicit init value, this will compile even default initialization is disabled. And there are good reasons for this in cases where you need to do that. But in the general case, you don't want to be just initializing something with an init value when the type was not designed to work that way. Similarly, with the non-static nested struct, because of the context pointer, if you explicitly initialize it with an init value, you will have a null context pointer, and so hello seg faults. The workaround that people have suggested and sometimes used is to use the syntax we have for explicitly default initializing something, which then looks like a default constructor, even though no constructor is actually being called. So what happens if default initialization has been disabled is this won't compile. So you don't accidentally end up using the init value when you shouldn't be using the init value. And for non-static nested structs, this will actually initialize the context pointer. and so you don't have garbage. It doesn't segfault all that fun. So this works. It's clean, except for the fact that static off call exists. So someone can go and declare a static off call on a type, and therefore, if you then use that type in code like that, instead of getting the default initialized value, you get whatever the heck they do with static off call, which might be a type of the same, might be the same type. It might not. It might even be void. So generic code cannot rely on that syntax. My solution was to add a wrapper template. So it gives you a manifest constant essentially, but it just default initializes the thing and gets whatever that value is. So in all the cases where the init value would work just fine, it will work with this. For the cases where default initialization is not supposed to compile, this won't compile, so you don't hit that problem. For the cases of a non-static nested struct, it actually won't compile because those can only be initialized within the context of where they're declared. But that's still a good thing because it means that generic code that's given that type won't then try and use the init value on it in segfault. And if you're dealing with a nested struct, it's all within where it's declared, so you can know that it's not dealing with the static off call and the whole bit and avoid this problem. So just by using this wrapper, simple wrapper trait, it avoids the issue, and you can tell people to do that instead of using the init value. There are still cases where you would want to use the init value, but that's generally just low-level code and not what you would normally want to be doing. And a quick example of a bug I ran into and had to work around was the code for has elaborate destructor, which is now has complex destruction, was overly complex, and it was like checking all the members and things that it didn't actually need to do. Because the only thing with regards to structs that you care about is whether they have an __x detour, which is the destructor that then calls all the other destructors on the member variables if they have a destructor, or the detour that you declared. But either way, if X detour is there, this thing has a complex destruction. The main caveat with the whole thing is you have to worry about stack arrays, which gets kind of weird, because then you have to worry about, confusingly enough, whether the stack array has no length, because it is possible to declare a stack array with no length, at which point it has no members and there's nothing to destroy. Well, so I simplified this mess and made it so it just checked for _X detour. And that mostly worked, except for this reduced example. With enough layers of nesting and using a zero-length static array, this resulted in it not finding the X detour when it was, it didn't find the X detour when it was supposed to. I think is what it came down to, or the other way around. I forget. Either way, it did the wrong thing. And I had to alter it so that instead of using hasMember, it used all members with CTFE to go and look for X detour, because for some reason, all members actually correctly reports that X detour is there, but hasMember is not. But it's weird junk like this, where things mostly work, and then you get several layers deep with some weird corner case that doesn't compile or does the wrong thing, that makes it so that I have been very thorough with tests.
One of the issues is you have a zero-length struct in there.
Yeah, that's on purpose.
And if you have no members in a struct, it doesn't actually have a zero size. So you had the size of in there. As a struct with no members gets a size of 1, which is what C++ does. So there's that probably a sneaky aspect about the size.
Yeah, I don't know exactly what's causing the thing, but the bug ultimately is that hasMember in corner cases does not report that X detour is there, even though all members does. But I've run into a variety of weird bugs, both in the compiler and in the library stuff in doing this, which is part of why I've been very thorough with tests, because otherwise, who knows what stupidity I missed. Probably still missing stuff, honestly, because this is complicated, but yeah.
Is there a bug report for that?
Oh, yes.
Good.
And in fact, I think you saw it in the one that merged the fix for the workaround. But yes.
If you go back to the slide there with the has member right there.
This one?
Oh, that one, yeah.
Yeah.
So you're saying that fails, but you said that it's missing. This looks like it's seeing XDTR when it actually should not be seeing it, right?
That's what it looks like.
I was confused with your explanation.
I may have screwed up with the slide.
That's okay. Okay, so it is missing from.
That is what I remember the bug being. Either way, there was a bug report, and I had to work around the thing. It's either there when it's not supposed to be, or it's not there when it's supposed to be. I think it's missing is what it is, but it's reporting incorrectly.
Regarding earlier with symbol types, a type of a symbol, that's usually functions, right? Functions or member functions.
Well, like, there are plenty of cases where you want to know what the symbol type is because you want to know what you're dealing with, and you're not looking to trigger any kind of expression. You really want the type of that symbol. It wouldn't matter with non-functions because it's the same type, but in general, you would want to just use symbol type if you want the type of the symbol so that you don't shoot yourself in the foot and accidentally use type of in the wrong thing. If you know that your code is only dealing with variables and there's no way you're ever going to deal with, a function, you can use type of because you know you don't need the help. But
right now, but what I was wondering is there any situation where you're getting some property from a function via a symbol that you wouldn't get if you took the address and got it from the function type? From the function pointer type of that symbol.
Can you repeat that?
Is there actually, I'm not actually sure myself, is there any situation where you need the symbol or you need some property of the symbol type, the thing that is the type of foo, that you couldn't get from taking type of address of foo and taking it from the function type instead?
I'd have to think about it.
Because I'm sort of wondering, what is this actually for? Does this actually buy us anything?
I mean, the workaround, that is one of the workarounds to deal with that property is to go, okay, take the address and now it's a function pointer and then take it that way. But either way, in terms of what you're looking for, you're either looking to know what the type of the symbol itself is or you're looking to use it as a property and you want to know what the type of the expression is.
Yeah, no, and I mean, I'm just wondering, are there situations in Phobos 3 where you did end up needing the symbol type where expression type wasn't strong enough?
Well, any case where you're doing introspection on the symbol itself, because that's what you're doing. Because I want to know
what the
traits are on this thing. I want to know, most of the cases I've been dealing with thus far, what you care about is the symbol type, not the property type. Something like standard range, the range stuff is going to care more about property type because things like front, what have you. But for a lot of the introspection, you really want the symbol type, not the property type.
Yeah. Okay, sorry, I understand it. Can I ask a second question?
Okay, as long as they let you.
All right, yeah, that was my second question, technically. Okay, third question. Very, very, very at the beginning, when we're talking about implicit conversion for template parameters, and with the template syntax being T colon target type.
Yeah, it's type specialization.
Type specialization, right. So isn't the underlying problem here that there isn't actually a template syntax to check for a strict type match? I mean, you're using colon everywhere because there isn't anything else.
Well, there are two ways to do a straight type match. One, you just don't templatize the thing. You just go, okay, now you get the implicit conversion at that point, but arguably that's one. And if the case you don't want the implicit conversion, you just take the type and do an is expression in the if condition. In the template constraint. So in the general case, it's not really a problem. The issue is you don't want the implicit conversion being checked for and then not done. And in some cases, even if you check for it, you don't want to do it in the function you want the call say. And the solution for that generally is just don't templatize that overload.
So we have time for just one more question, and Walter has already booked the mics.
Okay.
A lot of these problems you discovered are my fault. And I'm really impressed with your thoroughness in rooting out these things. You're the perfect person to be working on this problem. And a big thank you from me to you, Jonathan, for taking care of this.
I wish I were faster at it, but I want it right, so.
So we have another 10 minutes before the next talk. So thank you, Jonathan.
Do I need to point on any screen?
No, you
no.
should just test it out while we're waiting. Hello, DConf. Guess who's back? DConf, I have a question for you. What's your favorite scary movie? Yeah, how good is this voice? Yeah, the more it gets fucked up, you know. Anyway, before we go any further, we should do you a little reminder about, say it, what are people meant to be signing up for? There's 8 slots available.
Oh, Lightning Talks.
Into the microphone.
Oh, sorry. Lightning Talks.
Yes. So we have 3 sign-ups for Lightning Talks, and we got 5 more slots left. So by all means, find Razvan with a topic. Off you go. Now, we have a returning DConf speaker here. Guillaume, take it away.
Thank you. Hello, and welcome to this new presentation. That's our title. So first we need a little bit of a starting point on an agreement. Let's talk about one basic fact that we can all agree on each other. Nature doesn't have low latency pitch shifting. So there's no instances in nature where a bird sings a note, then it goes through special materials that change a note 1 octave up or down. So you don't have that. So maybe you have the Doppler effect, but you could argue the Doppler effect works like in this room because it introduces latency. So nature doesn't have that. And the reason nature doesn't have low latency pitch shifting is because changing the pitch of a sound signal is a bizarre proposition, similar to changing at which rate time is flowing. So it's pretty hard. And it's especially harder with real-time latency, CPU constraints, if you want polyphonic input, if you want to preserve the stereo field like you should. So don't do it, guys. Don't try to pitch shift. Actually, it's so distinctly hard that this field is currently dominated by the Germans. So they are the real industry standard, folks. Nevertheless, I tried and released inner pitch in 2023. We'll see later why it was a quite painful algorithm to make, and that's how inner pitch was released. It's completely written in D, of course, that makes it different. And all of the state-of-the-art algorithms that we have seen, including the German ones, are all probably phase vocoders. So it's a strange word to mean to modify spectrum. What does a phase vocoder do anyway? So as you may be familiar with, phase vocoder is a spectral processor. So it first splits the signal into spectral frames, transforms them into a suite of components, usually by using a transform like the fast Fourier transform. Then it does something in the right box, and then it reconstructs the signal in all its temporal glory. The spectral frame is transformed back with an inverse transform and added. This is a bit of a simplified view. What happens in the white box is complicated stuff. So first we need to actually change the energy towards lower or higher frequencies, and then make a choice. So typically this choice is made for every bin in the spectral frame, but some algorithm favors the largest bins. And you have three choices basically. They are all about phase. So the first solution is to favor the continuity of sinusoids over time. So it will be good for a violin or guitar. The second choice is to do the same phase choice as the other neighbors do. So if you imitate the neighbor bins in the same frame that have already made a choice, then you will again keep temporal coherency, also for violin, for example. And the third choice is to ignore the neighbors, either in time or in the same spectral frame, to favor the percussive elements, so favor the phase information specific to a location. So most algorithms need to make a clear-cut choice between these three to have a phase vocoder. So implementing a phase vocoder is an excellent way to produce a brittle, complex, and hard to modify algorithm. So over time, I've been more and more isolating the magic constants that are contained. So this algorithm has about 100 of them. So it's more than I used to have. And most of the actual time in development is spent listening, tracking numbers. So this part is called tuning, and it's critical to make something worthwhile to hear. It's also quite reasonable to expect some degree of independence between all those magic constants / variable / constants. But it's usually very long to pursue and have this independence between parameters. And how are they obtained? This tuning process looks something like that. You update the baseline with new values that have proven to lead to better sonic results. So pick an ID, implement it, then test on several sources. The more diversified, the better. And then eventually update the baseline or discover that you need to split your variables more. So after a few months of doing this, it felt like a manual or a gradient descent, a bit with the same pitfall. So because you need to retune already tuned constants. And sometimes you will make big changes that will sound worse at first, but only to sound better then, once you have retuned everything or something. And some constants have obviously a wrong value, but are covering up the bad value of other constants. So a problem that is coming up, because I do this every year, is that the human audition does not age very well, especially with the high-pitched sounds. So I need some kind of exit from being a good listener. And listening seems to be the bottleneck of this process, is that sort of manual gradient descent. So what if we were able to automate this? That was my first idea. Maybe the machine can hear better than me in a more objective way, in a way. So I had a sudden realization. I realized that we are living in the future with AI and thinking machines, space travel, and flying cars. So surely there is a neural network somewhere that can listen in my stead. So I was desperately looking for that agentic savior. And sure, it exists. There are lots of audio perceptual objective measures. They exist because we need to make audio codecs. And the codec people, it turns out, they are also tired of listening. And, and they want to stop tweaking numbers, so they invented the objective measures. And as far as 1898, or even before. So I've settled on this one, which is an implementation of a Google measure, which is named viscol. I settled on viscol/rs, who builds right out of the box almost. It provides an objective quality measure according to the research, which is quite good. So I didn't evaluate much more than that. It is made that of the language, so I just built it and got away before anyone noticed. So that immediately meant I was an AI company now because some data was passing through weights. Now, it's important to realize that an objective audio measure can't tell if something sounds good or not in the abstract, because good sound is often the result of a genre-dependent and heavily contextual opinion. So we have to make it work in the context of pitch shifting, which sounds not doable at first. Because what the objective measure does is compare a baseline sound with its codec transform counterpart, and it will rate the similarity. So if it were a dwarf, it would be like a red dwarf that never tires of listening. So in your example, processed sound is 94% the same as the original. So there has been a 5% degradation. And this number says how much it sounds, good or not. So the better the codec, the better the rating. Those measures, however, have a very good idea of what the human ear can sacrifice, because they are made for this. Well, I didn't know if I agreed with this particular measure of viscol, but audio codecs in general sound very good to me, and I am pretty sure they do not tune everything by hand. And there is something you can do, because in the codec sense, because quality is meant as perfect reproduction, it gets a high score, means it's like the original. But phase vocoding is an effect. It changes the pitch of a signal. So what gives? And if you chain two pitch shifting operation, one reverse versus the other, you should get approximately the original. So we can choose to pitch by some amount back and forth to try to get back on the original sound. So we've solved the issue of automatic listening, perhaps. And then to perfect the measure, we take several sources, make a weighted sum, and then we get a number which will evaluate the algorithm. Yes, but guess what? You're going to want to modify all my magic constants, right? So my conscience was speaking to me. Well, yeah, that's what optimization does, usually. Take a look at the code base. There's no way to put them all constants in one place. Besides, they are constants, they can't change. I see. We'll find a way to just add some UDA. That was a conversation I was having with myself. But I was pretty much concerned. In my first vision, I would have a centralized place for all such tuning constants that make them vary dynamically. It was maybe looking a bit daunting, like work. The reason is that a lot of files in my project would have to point to a single place, or else register a lot of variables hand by hand. So that sounded like a bit of work, and I didn't want to do that. But you can do it differently. The main idea, which was spoiled by the abstract of this talk, was to instead gathering all parameters in one single place parse the project, select the constant to modify, override the source code, and rebuild. You just override the file and let Git handle the differences. So thanks to Dub, we can give you a list of packages and source files. All of it is not very complicated to do. And we waited enough, so let's present Evolve, a command line tool for doing just that. So in the Evolve tool I'll be showing, so, those are the 4 forms of variables you can parse, and they are parsed with regex because it's not a real parse. And then they will be packed and considered for evolution. So the Evolve tool can list all your variables, and it has a semantic user-defined attributes for ignoring some of them. And they ignore them in a way that you can specify, such as it is already optimal, it is only subjective variable, this variable does not affect the algorithm, but something else. So lots of reason to ignore something. And it's not magic. You have to write a fitness measure, so your own fitness program. So Evolve cannot work without you making some effort, and such as writing the program that compute or measure here. And then you return it in a special XML file where the Evolve tool can pick it up. So yeah. And there is more XML with this configuration file where you select the variables you want, which will be picked in your sources. Also provide a way to evaluate and build your program again. So in the end, Evolve is not really audio related. It can be used for any kind of optimization, provided you manage to build an objective measure. So this can be really interesting for speed optimization with the caveats we'll see later. So you can find the tool below if you want to. You can also ignore all the packages because it turns out tuning variables can be distributed in the whole code base, and you don't want to hear about the same thing over and over. And how does the evolution thing work? So you get 4 different algorithms in Evolve. So they are called meta-heuristic algorithm in the literature. The first one just gives you your current position, so your current fitness in the space of solutions. The second one is called the gradient algorithm. It will try a pattern of trying each variable a little bit lower or a little bit higher and record the best result. Then it will pick a single improvement across all your variables. It will only change one, so quite expensive. Contrarily, the whirlpool algorithm will immediately apply that pattern immediately, so you will progress, but along a dimension that was maybe not the right one. And finally, we have an actual meta-heuristic algorithm, which is called differential evolution. Very easy to implement and stuff like that. There's a large class actually of algorithms that maintain a certain population and cross over them. But this is usually more efficient than an actual genetic algorithm. It's like a mix of Bayesian and genetic. So I have a question for you now. You can wake up. Quick. What algorithm do you think has the most usefulness in practice? Who is voting for the A algorithm, gradient? 7. Who is voting for the differential evolution? Okay. Who is picking the whirlpool one? Okay, this is C. This is actually whirlpool. But why?
Because it's more random. Because it's more random. That's why I picked it.
Because it's more random. Any other solution? it's because it's faster. Because the problem with is you need to rebuild often. So it's a slower optimization algorithm all around, and it just it minimizes the number of rebuild plus fitness cycles while still descending the gradient. So even being a bit dumb, it gets results. Fitness evaluation may be fast eventually, but it doesn't matter since rebuilding is rather slow. So you get to use DMD to speed up that. Might as well use a slow fitness evaluation, which is the case when it's perceptual measure. So the evolve tool is applicable where the fitness evaluation is slow, such as perceptual measures. But that's good news since our pitch shifting was already really slow. So all of the chain became slow. So I did that, and then 26 days after starting the efforts, sound quality had actually decreased, and the project was scrapped for 1 year. And so you have noticed maybe things that could have gone wrong did go wrong. Everything that could go wrong had gone wrong in this project because it's like a boy scout trying machine learning. You need to discover it first. And do you remember in slide 33, we proposed to shift back and forth in order to have a comparison like that? So anyone sees a problem?
You're not evaluating whether it's the shifts.
Whether?
You're not evaluating whether it's the shifts in between.
Yeah, it's not shifting anymore because the pitch shifter quickly learned that if you do nothing instead, then you will have a top score. It's literally the first thing that happened. So it is learning the test suite to have the best score. So you need, what I did was fix one of the executable to avoid that, so that the pitch shifter still want to shift. And there is an Alan Perlis epigram about that. When we write programs that learn, it turns out that we do and they don't. So someone already encountered that. Do you remember, for the people that were alive, slide 19? We said we had almost 100 magic constants to try to evolve. And what could go wrong? High dimensions. Well, it's easy to make minor progress indefinitely along any dimension taken in random order, such as in the whirlpool algorithm, but make very little actual progress. First, because there is always a dimension that can make a minor bump, but also because the fitness function is often a bit noisy. So you don't really want the smaller steps because you will end up in an insignificant local maximum. And it turns out in high dimension, you have a lot of local maximum. You have you have a large neighborhood in high dimension. So by and large, it's better to make an imprecise step in the right direction than many small precise steps in a random direction. That was the whole lesson I learned that day. And most of the time, you don't really know the convexity of your fitness function because I didn't train this call myself. I just use it, so I don't really know how it reacts. So you must as well try to step over the noise and try only big steps and only one dimension at a time. And be very sure of your change. That's what I did later on. Something that we can also notice in the same slide is that each source was used for 4 different shifting. We used 11 different sources, which I believe were meaningful. So I believe that would be 44 different evaluation. What could possibly go wrong? That's not enough data. not enough sources, because if you use the same source for 4 different shifting, I figured it was not different enough, because many of the algorithm conditions were tied to the input. It was the same input. Also, you need a rule of thumb is that you need 5 training examples per variable being optimized. So reusing the same sources 4 times and 11 sources lead to being able to optimize approximately 2 constants at once. And it never was successful to optimize more than 1, I guess. So if I were to redo that, I would use much more sources. Epilogue. I'm a bit fast with talk, so it's almost finished. In the end, I had to test each of the machine learned changes manually one by one. So assessing one by one what was changed. So this part was replaced instead. It was not listening that was replaced, but having IDs, which is good because we tend to not see what should be retuned. Once we have done it once, we don't want to do it again. So it did make a lot of valuable change that were released 1 year later. But you need to be very conservative about what you allow or not, and don't let drift into the dimension. So it shipped in interop version 2 and made a significant difference, even though it wasn't enough. So one of the reviewers said they didn't hear a difference. But I feel like it was nicely dotting the I's and crossing the T's. There's still a lot of room to improve the very same algorithms that I don't fully understand myself. At the same time, there is no particular market pressure to do better. So tooling is on GitHub, and it's already finished. So if you have any question, I'm all ears.
First applause. Now, looking at the clock, you've got 25 minutes for questions, so it's all on you guys. Let's fill it up, hey?
Did you consider using either, so instead of using a round trip thing where you're going to shift it down, then shift it back up or whatever, instead using, say, a relatively rich or complicated synthesized sound at different pitches? So we start with an A and a B, and then you shift the A1 up by a tone, and then compare those. Or if you think, even with live instruments, if you had 500 samples of someone playing a B on a violin, or a piano is easier. 500 samples of someone playing B on a piano, and then 500 samples of someone playing C on a piano, and you do the shift, because obviously when you do pitch shift, a lot of the time what you want is it to sound like it was played slightly higher or slightly lower, right? Because then you don't have the sort of round trip problem, and it's more natural, connected to the purpose of the plugin.
I mean, some of the audio phenomenon on a piano do not really translate when you play a further note. So it's interesting to try to form and shift the sounds you would want, but no, I didn't try that, because to be really exact, you would need to synthesize of sounds, and if you synthesize of sound, you will insist of having the right phase. So I'm not sure it could work. Maybe if you sum sinusoids, and then what phase do you choose for the pitched sound you generated? It's a bit of an issue, I guess. But
maybe the objective measure wouldn't mind about the phase being different, right? So, unless I'm misunderstanding.
Because you would like to consider to save the temporal envelope as much as the pitch. So, but how can you decide that this is how the pitched sound should be like? Rather that if you get back on the same sound, you have an objective of fidelity to the original, so it's a bit less of a choice to make. But it's really interesting as a question.
I understand you're a one-man show, and you're competing against how many Germans, and how do you compare?
It's mostly 2 or 3 people, I guess, in each of these companies. I don't know. But I had my looks on Elastic, which is better for percussive, but a bit less good for natural C. So I got to match it in version 2. And it was really hard and took a lot of time to get it. But although they do temporal stretching, and I only do pitch shifting, but normally if you have one, you have the other, but you have to work a bit more to get the 2 of them. And but what the bigger companies cannot do is preserve some quantity of sound quality over time, because random change will accumulate. So it's very hard to always go in one direction. So I know Melodyne has had trouble like that users complain of loss of quality in one version, which they tend to do. They tend to complain.
I have maybe a dumb question over here.
Yeah.
I'm sort of missing. Is this a competitor to Auto-Tune or an effects pedal, or have I missed the boat completely and it's something else?
It's more for guitar octaver, actually. I put that in 2 Auto-Tune products. But yeah, it's a kind of a competitor. It's kind of a competitor, but if you have a vocal pitch correction, you can almost always focus only on monophonic input, which makes the temporal algorithm win. But the spectral algorithm are more for complex signal. So spectral algorithm will usually lose out in quality versus the temporal ones. So in this case, for an Auto-Tune product, it's not a good match.
Okay.
So you mentioned that there's about 100 parameters that you want to tune. That's starting to sound like a model. The usual way you would optimize this is if you have, you could write a loss function and take use backpropagation to take the gradient. I think you said that the grading algorithm was also a model. So in theory, would it be possible to, if it would be possible to implement the pitch tuning algorithm as
absolutely.
tensor graph?
Absolutely, because all of them are continuous. But it's not really differentiable inside, because you have this sort of choice that is a hard choice. I tried to make it a soft choice at one point, but it wasn't really sounding that great. But if you make something that can react to even those choices in a continuous way, you could make that a model, I believe. So traditionally, I have bonus slides. I do. There's a whole field of metaheuristic algorithm with funny names, because the researcher gets inspired by nature to. And last year, one of the most downloaded paper in all of science, apparently, was a hippopotamus optimization algorithm, which was already modified this year. So I didn't implement the really fun name stuff. But the cuckoo must be done something right in its life, because it's mentioned twice in the optimization algorithm. So yeah.
I might have missed something, but I was wondering, since you said that the rebuilding is a bottleneck for the performance of your optimization, can't you temporarily turn those enums into runtime variables and do the optimization without recompiling for different enum values?
So that was my initial plan, but the problem is they are not. Then you need a central place or a registration mechanism. So you would modify a large part of your program, and I just want to modify just at the, if you have just this UDA, you can be listed and registered this way. So it's much less modification in the end. So that was quite practical, but you do lose the fast compile time because you. But yes, at first I wanted a central place where even the user can modify those final constants, but not all were constants, variables. Some were enums, and you would need to adapt all the algorithm to remove enums, and that was too much for me. I didn't want to do that because some of the delay lines are capped by the enums. So yeah.
Yeah, I was thinking maybe with like traits all members or some like you could do something fancy, but I can also understand that it was just easier to recompile it. So okay.
That was my question as well. So.
Oh, you meant to load some file description of their values. But you have to pessimize every delay line, so it takes a bit more memory to pessimize everything.
One trick we used in Worms Armageddon was that we wanted to have two binaries that had the same offsets for everything. So I was wondering if you consider just building the program twice, tweaking a single value, then comparing the binaries to find the offsets of that constant inside the code. That'll allow you to patch the binary much faster than rebuilding the whole program.
So I don't have the English skill to understand your question. I'm sorry.
Maybe just an idea, and maybe there's a very obvious reason why that doesn't work. So just build the program once, change a constant, build the program a second time, then compare the binaries and find the offset of the change constants in the binary, and then you can just iterate by patching the binary directly instead of doing a full recompile.
Yeah. But you would have to need reproducible builds to not have all the timestamp stuff.
Yes.
But yes, that's a better idea that I had. Yes. Yeah, of course.
Hello? Yeah.
Hello.
Yeah, interesting as always. I had one comment and then a question. The comment was the constant thing like this. VMS used to have constants always as variables, so they could patch them directly like that. So basically, you never had literals. You could always go through the memory. So such a thing would allow you to patch in your code very directly. You'd have a table and hit it and be done. Anyway, at least if I understand your process correctly, you could do that, as opposed to having an actual literal.
I can't answer you because I didn't understand one thing.
I'll talk to you later. It's fine.
Okay, sure. Come to me later.
From the dark ages of computing. Did you have a survey of existing like PAE thing? Basically, there's a bunch of research out there for AI-assisted pitch shifting, all kinds of learning, sometimes hybrids and so on. Did you examine those? Did you find those inadequate? Or I don't know the state of the art here. I'm just wondering what you had seen with other AI-assisted kind of pitch shifting.
I have tried language models that modify voices, but it was some years ago now, and they didn't manage latency that well. And I did find there was a model noise because it's not really the same to have an algorithm which is very careful with the noise level and a model which will match. So the AI is good with pattern matching, but in audio effects, it only has a big of success with the guitar effects because it can learn the chain of a guitar chain you hear. So people have been doing lots of products with that. But for pure audio fidelity, I will be a bit worried, especially with all the activation function and stuff like that.
The last question, since we had 25 minutes, was you had
I need to share that time.
You were doing. You mentioned the curse of dimensionality, and you mentioned like 111 or something number of dimensions. And I'm thinking my gosh, you could match anything to that. You know, it's like, as you said, the maxima, right? There's got to be a bazillion of them. Is there any kind of systematic way to work through those so you have some notion of orthogonality or something where you can start to knock things down and get a more sparser representation?
You need better algorithms that I've done. There were better optimizers than that. All the meta heuristic we have seen at the end are way better than differential evolution, which is not even mentioned in the new papers. So you will need to implement those. And although I tried to get an interest in Bayesian optimization, but I didn't understand anything. That's why I resorted to simpler algorithm. And because my measure was so wrong, it couldn't really work with changing several stuff at once. But how Bayesian optimization works is that it will change every one of the variables at once and use covariance matrix to optimize correctly and find the right direction anyway. So it's way more clever than the small algorithm I've done.
We filled 15 minutes with questions. If we have, maybe we should cut it here. Yeah. All right. Thank you, Guillaume. That means you guys have 20 minutes to have a break and be merry for our last talk before the Weka happy hour.
Okay, so we now reach the final talk of the day. I know that by now you're already thinking about the beers and the food after this, but yeah, just wait a little bit because I promise you it will worth it. Because Eyal here is going to talk about the cool ways in which Weka uses D for the world's fastest data platform. So everyone give it up for Eyal.
So hi, everyone. I haven't done a full talk in any of the DConfs yet. I did do a couple of lightning talks. So I wanted to talk about the way that we've been using D for about 10 years at Weka, and for quite a big code base. So let's start with a bit of background. So first, Weka is basically the world's fastest file system. It's also distributed, it's parallel. You could say it's more than a file system because it allows various features of migrating your data around, backup, accessing your data with in many different ways. So it's more of a data platform. And the idea is that it basically should solve all of your organization's data needs. So it kind of abstracts it away, similarly to the way VMware abstracted the notion of compute away. You no longer think about specific machines to yield your compute. So Weka was founded in 2014, or maybe even December of 2013. It's a software-only solution. So if it comes, if you can touch it, we don't do it. Now, it comes with quite deep technical challenges. I'll touch on one of them in this talk. We have basically incredible scales. Like we run at some customers with, some are pretty small, let's say a few petabytes with a dozen or so machines. And some are running incredible sizes of tens of thousands of servers and hundreds of thousands of clients, some crazy scales. And when I say scale, I mean in multiple dimensions. There's the scale of capacity, the scale of the number of machines, number of processes, the network involved. So it's pretty insane scales. And our customers, I would say, and I've been at a couple more companies, are some of the most interesting in the world. They really are pushing on the limits of, I would say, humanity. But I think we'll talk a lot more about that tomorrow, so I'll leave that for later. Now, our use of D is not for any particular component. Basically, the entire product is written in D. And it's a very complex product, so we have networking, we have hardware, we have clustering, file system, RAID, Raft, hardware abstractions. We have a lot of different things that we do with D, and quite a few developers that are working on it to solve very, very interesting problems. So I can't really list all of them here. It's quite a few. Now, I want to focus about one aspect of complexity that I think D helped in a very unique way that I don't think any other programming language could have helped us in the same way. But to describe that, I'll start by first describing RPC. Even for simple RPC, D is quite nice. It's, I think, nicer than other languages. Basically, when I say RPC, I'm talking about remote procedure calls. And at Weka, we are running as a cluster. Basically, it's a cluster of machines, processes running our Weka code. And the way they talk to each other over the network is basically using RPCs. Pretty much everything uses RPCs. And because performance is so critical to our customers, and it's important to us to really be performant, the protocol has to be very efficient. It cannot be, let's say, a JSON-based protocol. Like a lot of the industry standard for RPCs are kind of textual, which is fine for most use cases. But when you're really trying to be give a million IOPS from very little hardware and squeeze every little bit of performance from your hardware, you need to be binary. We are also based on our homegrown network stack, optimized for latencies. We actually count the number of cache misses that we cause on receiving a packet. We really care about every nanosecond of processing time per packet. It's a very hot path because we want to be able to process millions of packets per second in every process, every machine. So it's a homegrown protocol optimized for latency and optimized for performance. And the RPC is built on top of that. So the way we want developers to use RPC, we don't want the developers, we don't want them to be aware of any of that complexity. We want to hide it all away. So we basically declare our RPCs as regular interfaces with regular methods and regular types. And you just implement a struct that has methods that implement those interfaces. It's to use the RPC is as simple as that. We also have the RPC client using kind of an op dispatch thing so that you can basically call an RPC transparently with almost the simplicity of a local call. Of course, their semantics are a bit more complex. It might time out. It might do stuff that a local call will not do. So it's not 100% as simple, but it's very close to being as simple as a local call. And basically, what we do is we serialize over the network all of the inputs. And then the server will serialize all of the outputs. And notice that some parameters in the interface might be marked ref, and we use that to indicate that it is a two-way parameter. Basically, it's going to be sent serialized to the server, and then the server will serialize it right back. Now, I won't be talking about Raft much, but I just wanted to bring a real-world example of our RPC, so it's a bit more concrete. So here you can see the iRaft service. It's almost verbatim an actual interface that we have. And basically, we have the methods used to implement Raft over the network. Again, I don't really want to dive into the complexities of Raft. I just wanted to show how an actual real-world RPC interface looks like. Now, I did omit this just to simplify, but for example, here you can see append entries is something that happens quite a lot. And we don't want that to use our logging system to be logged, just because it would spam way too much. Even our high-performance logging system has its limits. And we also basically have encryption support built into our RPC. So you can just enable that with a UDA. That's all I'm going to say about Raft or the RPC as its own thing. This was all background because what I really want to talk about is our upgrading support. That is the main topic I want to cover. So Weka has real customers, a lot of real customers. Now, before we had customers, upgrade was easy. You just change the code and you've upgraded. But once you have customers, you need to, and those customers have running machines with running data. You need to actually do the upgrade in a non-disruptive way. You need to allow the customer to continue working, start up with the current version, end up later with the version that has the features that they need, or the bug fixes that they need. So upgrading is essential for any real-world product that is not trivial. Once you also add scale to this equation, you have a customer that has thousands upon thousands of machines, and disruption is unacceptable. How do you upgrade them? Like, our very early attempts at upgrade were naive. You'd just say, OK, stop all the processes for a very short time, and start them up in the new version. And this worked fine for very small scales. But once you scale to huge clusters, if you try to do that, it won't end well. Basically, let's imagine you start 100,000 processes in the new version. 5 of them are having a bad time. Maybe the machine is broken. and that breakage only showed up now. Maybe we ran out of memory because of some other thing on those machines. And in such a case, basically we're going to have, let's say, 10 failures at the same time. And our system is very failure resilient, but there is a certain number of failures that will be too much. So the only practical way for upgrading at scale is to do it rolling incrementally, not do it all at once. So if we take this look, schematic look of a cluster, of course, it's super simplified. It's much more complex than this, but this is enough to illustrate. We have these Weka-node processes, and they have basically persistent data structures that they store in SSDs, and they talk to each other with RPCs. Now, we know that the exascale upgrade must roll. We have exascales of capacity. Obviously, that implies thousands of servers, and this must roll. So how do we roll that? We upgrade the first Weka-node. I used green to indicate that it's upgraded. But notice, once this Weka-node is upgraded, now you have a new version talking to an old version. And this implies that there are potentially compatibility issues, right? We may have changed structs, we changed the protocols, we added RPCs, we removed RPCs, and we have to handle compatibility. Now we upgrade an SSD, and the data structures change. But notice some SSDs are upgraded, some are not. So we're going to be able, we need to be able to read old structures from SSDs that weren't upgraded, read new structures from those that were. So we're going to have to handle all these inter-version compatibility. So we upgrade another and another. Eventually, they're all upgraded, and we're back to the simple case where everybody's of the same version. Just to emphasize, I used green here to mark where we have structs that may need to handle compatibility. So structs inside RPC parameters, return codes, and structs inside the persistent storage. So how do we retain compatibility? So if we have an old RPC old Weka-node process, it obviously cannot do any upgrade or downgrade itself because it's old. It doesn't have any of the new logic. It doesn't know the new logic. So all of the work has to be done by the new version. And this old Weka-node might be making an RPC call to a new Weka-node. And then it's up to the new Weka-node to upgrade those calls in order to allow us to seamlessly handle the upgrade. We don't want to write manual code for each and every case of every change. So what we want to do is want the new Weka-node to just upgrade these calls. But also, there is the less intuitive case of downgrade, because when the new Weka-node wants to do an RPC call to an old one, it needs to downgrade that call. So how do we achieve all of this? So first, metaprogramming comes to the rescue again. So today's talks, which were excellent, by the way, already showed a bunch of nice use cases for metaprogramming. So this is another case. Metaprogramming allows us to go over all of the data structures inside our RPCs, and that means recursive iteration. So maybe an RPC contains a struct, which contains a struct, which contains a struct. We need to basically include all of those nested structs in our schema, in order to basically remember all of their formats. Also, all of the persistent structures that we store on the SSD. We need all of them as part of the schema of the old version. So Weka-node, using metaprogramming, has kind of a command line option. Please dump all of those ref types, all of those reference types, so that later we'll be able to use them for upgrade and downgrade. And we store those. It basically dumps a JSON file, which we post-process into D files, which we commit to the repository. Every ref type that we commit allows us to support that version as a source version for upgrade or downgrade. And basically, it's very easy for us to commit to our repository not one old version, but many old versions into as many schemas. And then it's seamless upgrade or downgrade for many, many past versions. So to reiterate, to do automatic upgrade and downgrade, the server upgrades old calls, the client downgrades to old servers, and the persistent structures get upgraded. We want to automate this. So how does this automation work? Basically, it's metaprogramming again. This time, the metaprogramming allows us to take the old type from the ref types and the current type, and it allows us to compare them recursively. Every time, basically, you have the same field, let's say the same field of the same type, great, nothing to do. We can just copy it over. But every time, let's say, a field was deleted or a field was added, then our automatic upgrade code will basically require to add a UDA describing what happened. So, for example, you can see you can add a new field or a removed field. Otherwise, you get a compilation error. And the reason for this is imagine that you rename a field, right? A rename of a field, if you just use metaprogramming, it looks very much like a deletion of one field and an addition of another, right? If you try to compare the two structs. So you don't want to really automatically guess, OK, this field was deleted. Let's just delete the value and upgrade. This field was added. Let's just initialize it. You really want to be certain that the way you're upgrading it is correct. And it's not an accidental change. That's why the UDAs are required. So let's look at an example. So this is slightly less realistic, but it conveys the point. So let's imagine that we have a struct file which has these A times C times M time. Everybody who is familiar with POSIX file systems probably knows these 3 times that each file, each inode has. But now there is a feature request. We also want to store the birth time of a file, not just these 3 times. This is, by the way, a completely real feature request that we've recently added. So let's say we try to add this. And what we get is this error. Field btime was added to allow upgrade, use at new field, or add a custom upgrade method. So I cannot automatically upgrade. Now, notice that in one of the previous talks, using library-level features as opposed to language-level features, one of the downsides of that was mentioned to be bad error messages, right? Because the compiler can give you much better error messages. But notice here that we have a nice error message. A custom error message. We could make it as good as we want, even though we're just a library. So the infrastructure here has a way to give you custom error messages, and I'll actually dive into how we do that, because it's a neat trick that I think I can show. But this basically tells the developer, you just broke upgrade unless you do something, and we don't break compatibility accidentally. If you do this, you need to know what you're doing at upgrade. So now I can basically add, OK, add new field. And by the way, if more of these annotations are added, it's kind of a nice log of the changes that happen to the struct and what happens at upgrade or downgrade between versions. And once you add this, it compiles fine. And it's all good. Now, the semantics of new field are what you would expect, which is upon upgrade, just initialize the field to its default value, the init value of the language. So in this case, let's say the 0 time. And upon downgrade, just delete it. Those are the semantics of the @newField modifier. But then our product team comes and says, what? The 0 time is not a sensible value to use on upgrade. We want you to approximate the birth time of a file as the minimum of the 3 times, A time, M time, and C time. It's not correct, but it's much better than the 0 value. So how do we handle it so that in upgrade, we set it to be the minimum value? So instead of this new field annotation, we can add this custom upgrader. So the infrastructure allows each struct to define custom upgraders for fields or for the whole struct to handle upgrades and downgrades. In this case, I only added the upgrader because this is a persistent structure, so it doesn't actually get downgraded. But if it was part of an RPC, it would actually give me another compilation error on the lack of ability to downgrade it, and then I would have to add a downgrader as well. Now, for upgrades, we've basically successfully upgraded customers thousands of times, non-disruptively. So this rolling upgrade thing, it really works. Now, we allow our customers to keep their clients, which also run Weka code, unupgraded for long periods of time. So because for them, upgrading the clients is an explicit action that they need to do, and we prefer to allow them not to do it or postpone it for as long as they'd like, which means we actually have many more than 2 versions in the cluster. And we didn't have to do anything special for this. Basically, as long as the ref types of a version is in the repository, the upgrade, it just works. And also, there is no performance impact. This upgrade, downgrade, it's all binary, it's all seamless. I guess if you measure it precisely enough, you will see a performance impact because an extra upgrade method was run. But it's a trivial impact, so it's not measurable almost. And so our customers expect that when we upgrade their cluster, even during the upgrade, the performance impact will be minimal, if at all. Now let's dive in a little bit into these custom compilation errors that I showed. So the way we can implement such compilation errors is basically using this kind of struct location, file name, line, and column number. And now we basically have the ability to take any declaration at all in your source code, alias deco. This alias can be a field of a struct. This alias can be the struct itself or a function. It can be anything pretty much that is declared. And we can get the location of that using the traits get location. I'm not sure how well known this trait is, but it's pretty useful for this kind of thing. You can basically ask the compiler, give me where this thing is declared. And then let's say we can have this string message, which returns the message annotated with the file name and line number in the exact same way that the compiler annotates its own error messages, right? And on this example, for instance, we have the location of some struct that I defined, field, and it says hi. And when you try to compile this, you actually get something that looks very much like an error message, like a compiler error message that just says hi. Maybe I'll even switch to a small Godbolt demo for this. Let's see. So this is basically the same code, except I used this warning, be more creative with your field names. And notice that it actually gave a red squiggly line here. Be more creative with your field names. But it's not a compiler error, it's just a pragma message. So pragma message actually allows you to give those custom error messages, which are much, much nicer than like a static assertion failed, and then you get the line number of an assert in some infrastructure, and nobody knows what that line number even means. So here you get like nice errors that you basically write whatever you want on the line number of whatever you want. So basically, the reason, by the way, for the thank you slide is I wasn't aware of how long things will take. So now I have the better timings. So anyway, we do a lot of interesting, we use D in a lot of interesting ways beyond the upgrade and downgrade. It's a pretty big software project, and we also care deeply about our development velocity. And when we try to change a large subsystem, we want to run its unit test. But since it's a large subsystem, even linking it with all of its vast dependencies will take a long, long time. Now, D has quite amazing CTFE capabilities. And at some point, we realized that maybe 70 or even 80% of our unit tests can actually run in CTFE. Or if they can't, with a slight effort, they can. Because mostly when you're doing unit tests, or I don't know if mostly, but in many cases, you don't need to access file descriptors in your unit tests. You need to check your computational code, your data structures, your algorithms. And those are typically things that can be made to run in CTFE. Like maybe they have a global variable, and then they can't. So you can factor out that global variable into a parameter, so that in production code, you pass the global variable. But in your CTFE variant, you pass in a local variable, which allows it to run in CTFE. And this slight effort basically means that you can run your UT within the time it takes to just do a front-end -o' or -o- on your single D file. Now, it might be a huge subsystem. Linking it might take tens of seconds. But doing a -o- on this D file might take 400 milliseconds. And it can run the unit test within those 400 milliseconds. So it's a pretty amazing factor to the cycle time. And to do this, we have this nice combinator that I really recommend adopting, where we define this UT function, which takes an alias f. F is your UT code wrapped as a delegate. And basically what it does, it runs it in runtime and in compile time. And this allows checking that it works not just in CTFE, as I said, with a much shorter loop time. It also guarantees that the semantics in runtime, which may differ, you can easily do, if CTFE, do something else. And if you do that, you might easily break the code in one or the other cases. So this UT combinator makes sure that it works in both of those cases. So this check executes it in runtime, and the second one executes it in CTFE. And let's take an example. So I have the Fibonacci function. I won't dive into how it works, but I think it's a pretty simple example. So I have these assertions that Fib does what it wants. Normally, I would write my unit test this way. Now, if I only add this UT combinator around it, now it runs in both compile time and runtime. And if it's wrong, I just get a compilation error instead of a runtime error later. Now, Fib is a trivial example. If I compile and link it and run it, it'll only take, I don't know, half a second. But for larger examples, it's quite dramatic. So debugging in CTFE UT is actually, it can be painful because you don't have GDB. And Pragma message is actually not usable for that. Because if you run your runtime function in compile time, even though it's running in compile time, you can't really Pragma message the values of the variables inside it. Because Pragma message only works for enum values, for template values, not for runtime parameters that happen to be CTFE'd as values. So I think relatively recently, CTFE write was made to work. Like it existed for years and years, I think, but it didn't work. And we complained, and it was fixed, and now it works. So CTFE write lets you basically write, it's kind of like Pragma message, but it works for syntactically runtime values that are in compile time. And in runtime, it doesn't do anything. It's basically a no-op in runtime. But in compile time, it prints just like Pragma message. However, it might require GC string formatting. And I want to deviate from two previous people and say that we do use @nogc. Because if we accidentally add GC to our code, it can be pretty painful, a pretty painful performance bug that might actually cause trouble for our customers. And because our product is so complex, it has so many features and so many use cases, it's very possible that our QA, for example, will miss some performance degradation deep inside some corner case of some relatively rare use case, whereas for a customer, it will be painful. So @nogc allows us to basically make sure that we don't accidentally miss such cases. But just like here, CTFE write wants to do string formatting, but it wants to do it only for CTFE. It doesn't really care about runtime. So I have the same problem as the previous folks who said they don't use @nogc because it's overly strict. But instead of giving up on nogc, what we decided to do is basically cheat. Like we say, OK, A little lie here and there about no GC is better than just not having any error or warning whatsoever when we get accidental GC. And accidental GC, by the way, is not a hard thing to have. It's not like you accidentally call new. Accidental GC happens whenever you forget the scope keyword on a delegate that you pass to a function. It can easily happen, and it can be very painful. So we do want a no GC to catch those things, but we have the same trouble where sometimes no GC is overly restrictive. So here you're probably familiar with the Vegas clause of what happens in Vegas stays in Vegas, and the same is true of CTFE. So for these cases where no GC is being too much of a pedant and not really helping, we just cast it away with this as combinator. So we can say CTFE write at runtime is a no-op, so it's safe, no GC, pure, no throw. We don't really care what happens in compile time. And we do the same for things like assertion failed. Our assertion failed code that kills the process might do GC, but it will be at no GC, because we don't really care that when the node fails, it will lie and do GC even though it's not supposed to. So we'll use as no GC in all sorts of these edge cases. Another cool thing that I would say is slightly less specific to the D language. I think it can be done in many languages, but I really recommend doing it in any large project, is using these typed identifiers. Typed identifiers are basically wrapping a simple type, like a short, long, int, whatever, with a struct that the only purpose is to distinguish it to the type checker. So we have, let's say, a disk ID, an inode ID, a file system ID, and there are many benefits. Maybe the primary benefit would be that if you confuse two parameters, imagine you have a uint file system ID and a uint disk ID, and you confuse the two in a function call. You really want that to be a compilation error. You don't want to be, so this is really nice. But there are some side benefits, really nice side benefits. It's really great as documentation. The type of the function is documenting the function. You don't, even if your comments aren't great. When you stringify this, either in the runtime logging system, which Luis will cover later, but also in any toString, you get, instead of like some struct of 5 and 6, you get some struct of disk 5 in node 6. It's very useful for much, much more informative strings. And in our logging system, when we have these efficient binary searches, I can search, for example, I have a bug involving disk 5. I can go and search, give me all logs about disk 5. So it has a bunch of unexpected benefits. Another cool thing, which I think kind of relates a little bit to the previous talk, where people asked, why doesn't he use like a runtime variable instead of a constant? No, this isn't. I asked him. It's not particularly applicable for his case. But we also have these constants that we want to be able to override. While trying to run evolve on Weka node, I think, would be insanity in terms of compile times, and it's too huge to evolve that way. Cool project. We do need the ability to override specific, let's say, so-called constants once we discover some kind of problem. So you can imagine that any timeout that we hard code would turn out to be wrong in various cases. It could be too short and stuff explodes. It could be too long and stuff is slow. But not just timeouts. There are many, many things that we want to change at runtime. So we have this thing we call a manual override, where it's trivial to use in code. You don't have to declare anything. You just say manual override, get value, give it a name, give it a default value, you're done. But the thing is, it's behind the scenes, it's actually doing something pretty interesting. First, it registers, that's why it's a compile time string, by the way. it registers this string into a registry of overrides. This registry, you can actually list it. And this registry is statically typed. That is, for each registered override, we have the type of that override registered with it. Now, when you try to basically add an override and you give the wrong name, it will tell you this key does not exist. Or if you try to give an override of a string, when it's actually a duration, it will tell you you're giving the wrong type. So it's really nice that it's, on the one hand, trivial to use, and on the other hand, it's very strongly checked, and you get both of the benefits. You get all the declarative benefits without needing to explicitly declare. And I think this is really easy to do with D, and I'm not sure how easy it would be with other languages. Yeah, with that ado, let me go back to the thank you slide.
So we now have another, yeah. No, this is the last one. Yes. Well, I mean, we have questions now. Yeah, sorry about that. So yeah, if you have any questions, we have plenty of time for questions now.
You showed, excellent, thank you, by the way. You showed us the as cheat. How is it implemented? How can you cheat?
So behind the scenes, it's basically a delegate cast. So you give it the string of attributes and just creates, it uses an @trusted code that casts the delegate from the attributes it had to the attributes you're asking to cheat about. No, people normally do this kind of cast manually, but when you do it manually, the syntax is so cumbersome that I think it's a strong enough disincentive to just forget the whole thing. I'll just I'll just ignore this attribute altogether. But if you make it like syntactically nice with as, it's not that bad.
Looked very neat.
How do you know what parts of your CTFE are slow?
Sorry.
How do you optimize your CTFE?
You mean in terms of running the CTFE UT is taking too long?
Yeah, I wonder myself how to run CTFE faster, and I don't know what exists for.
So I think the work we're using was upstreamed to LDC and possibly DMD. I'm not entirely sure, but we have this time trace utility. Does anybody know if DMD has it as well? I'm not sure because it has it. Awesome. So if you use -f time trace, you basically get a tracey log, which you can open. You can open it with a nice GUI viewer, and it shows you kind of a flame graph of where you spend time. And it's pretty amazing. It shows you not just the CTFE itself. It shows you this import took a long time. And just yesterday, I was working on some code, and it showed me like a huge import taking a long time. And I'm like, why is this imported? This should not be imported in this. And it's really easy to find these kinds of slow things to eliminate.
Cool idea running the unit test compile time. I actually mentioned that a few years ago. As far as I'm concerned, that's what I want to. Is there any reason why you did the cast instead of using debug? Because debug also turns off no GC, no throw, and doesn't care.
Oh, actually, if you use debug, does that not require like passing a -debug?
Yes.
Yeah, so well, a few talks ago, they said passing compiler options would be a bug. So we also avoid like passing these extra options. I guess that's an alternative. But we just we have two modes. We either compile with unit test or not. And
Questions. We still have 20 minutes of questions. I guess everyone is hungry by now.
thirsty. So maybe I can. Is Tali here? Oh, sorry, there is another question.
We actually have a question. John's got his hand up.
So do you think your customers know that you use D? Like, how much of this information, like you're sharing here, how much of that leaks through the marketing and sales and so on?
I think it's not a secret in any shape or form. We do say we use D and that we love the language, but I think customers don't really care, so it doesn't get brought up. But the customers just have high expectations, and I think regardless of D, they learn that we can deliver on those expectations pretty well, and I think D has a lot to do with that.
How does binary RPC format compare to protocol buffer, for example?
How does it compare to Google protobufs? So the Google protobufs are, correct me if I'm wrong, are basically based on textual format, right? Or am I wrong? Or
No, it's binary on the wire. It's a textual format to describe your...
Yeah. So I think, as far as I know, I'm not an expert on the protobufs, but there are a few things that make it incompatible with what we're trying to do. One thing is, as I said, we're processing millions of packets per second, so we are, I think, optimizing it a bit more than even binary interfaces would. So we need to be compatible with our underlying optimized protocol, which I'm not sure protobuf would be. But also, I think protobuf has a lot of special casing. Like, it has these specific sets of types that it can serialize. And our RPC serializes any D type whatsoever. And it supports various upgrade changes. For example, if you add an INA member, then our upgrade infrastructure knows that it's upgrade compatible but not downgrade compatible. Because a new INA member that added a new value is fine, but the downgrade is not. And I think, I might be wrong, but as far as I know, protobuf wouldn't be usable with like the vast range of D types that we have, and handling all of these changes that can happen in upgrade. Again, I'm not an expert on protobuf, so I might be.
Okay, so you said huge code base. What is huge? 500,000, 1 million, 10 million? And sort of in addition to that, like when we talk compile times, like a release build, how long does it take if you're...
So the release build, we have, we can release build with, we have the by exa mode, which basically builds everything as one huge unit, so possible. That takes, I think, 90 minutes or so to build per architecture. We build multiple architectures. But there is also the per package release build, which would be basically a parallel build of many packages and then link them together. That is, I think, about 30 to 40 minutes. And it's usually good enough for most purposes. You don't need, the extra benefit of munging it all together is not that big. It makes compiling much slower for a tiny benefit, which is reasonable when you do a production release, but you don't need it when you're, even if you're trying to check performance stuff.
Is Weka hiring?
I did not plant him. But yeah, one thing I forgot to mention is that a lot of these things are really applicable outside of Weka, and we would love to make a lot of it open source. We just, it's hard for us to do it on our own with little touching base with the community, and also more DDevs would really make it easier to do. So if anybody finds it interesting, we'd love for you to talk to us.
So what is it, seeing as you've got tools to understand compile times, what's making the build take that long? Because, like, I mean, presumably you don't have like 100 million lines of code, right? So, and even if you did, 100 million lines of code shouldn't take 90 minutes. So what's, like, there must be something in it that is like really upsetting the compiler.
Yeah. So one area where I think we would love to have some better support from the compiler is understanding which templates are costing us. So it's obviously we have a lot of templates. We use, in some cases, we overuse templates. There are many templates that we could and should eliminate. The problem is that there is no good way today to easily find out which templates are really costing us. That's something that we wish we might work on it ourselves. We would love help from the community. But basically, if you look at the -v CGAST, it does have millions upon millions upon millions of code. Like each tiny module can easily become millions of lines with some templates. It doesn't take much. And so I guess that's the culprit, but it's really hard to figure out which ones are the ones to focus on and fix.
I'm risking drinks for everybody and saying it's STD format.
Sorry?
I'm risking drinks for everybody and saying it's STD format.
It could be.
I mean, STD format is really, really awesome, but it's so slow to compile.
You mentioned you had a custom network stack, and I was just wondering if that's layer 2, layer 3, at what level are we speaking of?
So we are on top of, we use DPDK for the network. We're on top of UDP. Sometimes people mention DPDK as an alternative to UDP. Like technically it is UDP. So that would be the underlying layer we're at. And it's all the way up to making full RPC calls end to end. So basically the protocol is tailored to serve RPCs. There's not much else going on. So you could say it's together with the RPC, it is one unit. So I guess it's from UDP all the way to the application layer.
Okay, but even the UDP stack?
The UDP, I think, is handled by, like, with DPDK, you basically format, I think, a UDP packet.
Okay. Yeah.
So as far, yeah, it's not my area of expertise, but. Yeah.
So I just want to say I really like that template that you had for the location.of. Having nice templates and nice syntax like that, you know, as a library, it's like, oh, this just reads perfectly well, and underneath it's doing all this cool stuff. I think that's an awesome
thanks
way to create an API.
Any other questions?
I mean, that is a high note to end things on. So.
Yeah, actually, I have one thing to add. So, Eyal, maybe you can, I don't know, make up some numbers to prove that STD format is not the culprit, and that way we all get free drinks from Robert. Yeah, and before we go, Shimon here wants to announce like where you should go for the free drinks and food.
Yeah, hi. So we're going for drinks and food and snacks in the Trinity Bell. So you have the address on your invite also. Is Eden here?
No, she's at the venue.
She's out because she's going to lead all of us over there.
No, she's there already, but we can work it out from there. We've all got Google Maps and we've done the walk before.
So. Yeah, are we technical enough to open Google Maps here?
No, we did the walk last year. We can sort it out, yeah.
Awesome, awesome. No, she's supposed to be here, but maybe she didn't come yet. So see you there. Let's go over.
Yeah, so thank you, everyone. Another round of applause for Eyal. Thank you for the awesome talk.
Thank you.
So what do we call it? We can't call it beer conf. It's like Weka conf.
Weka happy hour.
Weka happy conf. I don't know. You guys work it out. But yeah, I guess that's it for today. We'll see you here tomorrow. We're a 9 a.m. kickoff again. So what did you all think of the first day of the conference this year? Good? Hell yeah. Yeah, you see everybody on the internet, even with a scratchy voice, we're having a good time. So make sure you book your tickets for next year in advance. All right, but yeah, let's wrap it up. Pack your stuff up. We do need to be out of here by 6 p.m., but that's also when we have the room at the Trinity Bell, so I'm sure we won't have that problem this year. All right, so catch you all tomorrow.